Welcome. Over the next 5 hours, we're going to cover every fundamental building block of system design from the ground up. We'll start from how the internet actually works, and by the end, you'll understand how real production systems serve hundreds of millions of users every single day. So let's get started. So, system design is part of interview process at almost every major tech company. Whether it's Google, Amazon, Meta, and hundreds of others, they all use system design as part of this interview process. In this round, you'll be asked questions like, okay, how would you design a URL shortener that handles millions of requests? How would you build a chat system that will deliver messages in real time? And questions like, how would you store and serve photos for a billion users? To be able to answer these questions well, you need to understand the building blocks that sit behind every large system. Things like databases, caches, load balancers, sharding, replication, and content delivery networks form the foundations of every system design. Once you understand how these different pieces and components work together, you can reason through whatever design question an interviewer puts in front of you. This is exactly what this course will prepare you for. Now here's exactly what we'll be covering in this course today. We'll start with how the internet works, where we go through the client server model, DNS, TCP, UDP, HTTP, TLS, and the full life cycle of a web request from start to finish. This section will run for 45 minutes. Then we'll spend 30 minutes on our servers and application architecture, covering concepts like stateful versus stateless servers, reverse proxies, API gateways, and when to choose monolith versus microservices architecture. After that comes the biggest section of this course, which is databases. We'll spend 80 minutes over here to cover concepts like SQL and NoSQL databases, indexing, asset properties, normalization, denormalization, replication, and sharding. Then 45 minutes on scaling, where we'll walk through the complete journey of taking a system from 0 users all the way to 1 billion users step by step. We'll also cover backup envelope and estimation, which comes up in almost every system design interview. After that, we'll spend roughly 50 minutes on caching, covering cache patterns, eviction policies, Redis, and the common failure modes that interviewers ask about. Then we'll spend roughly 35 minutes on load balancing, covering algorithms like round robin and least connections, layer 4 versus layer 7 balancing, and health checks. And finally, we'll spend 25 minutes on content delivery networks, covering how CDNs reduce latency for users around the world, push versus pull models, and cost structure. Before we start designing systems, we need to understand how the internet actually moves data between machines. Every system you'll ever design, whether it's a chat application, a video streaming platform, or a payment processing service, they all rely on the same underlying foundations and fundamental concepts. In this section, we are going to cover 7 foundational concepts. The first is the client-server model, which is the foundation of all network communication. The second is DNS, which is the domain name system, which translates domain names like, let's say, youtube.com into IP addresses. The third is IP addresses and ports, which tells us how to find the right machine and the right application on that machine. The fourth is TCP and UDP, so these are the two transport protocols that actually move data across the network. And the fifth is the HTTP and HTTPS. These are the application layer protocols that defines how web requests and responses are structured. After that, we'll cover the sixth concept, which is the complete request response lifecycle, where we trace the single request from start to finish. And then we'll wrap up by covering the seventh concept, which is the latency and round trip time, so which drives almost every architectural decision that you'll be making in system design. Now here's the thing, none of these 7 areas are just purely academic concepts. Actually, every single one of them is very important for system design interviews. So, for example, DNS concepts, they show up when you talk about CDN routing, global load balancing, and failover strategies. TCP versus UDP shows up in your interviews, let's say when you're choosing protocols for your chat, video streaming, or gaming applications. HTTP and HTTPS shows up in API design, REST endpoints, and status codes. And then latency shows up in performance budgets, caching decisions, and server placement. So here's the key question that this entire section cover, which is that when you, let's say, open up YouTube on your phone and a video starts playing, what actually happens between you tapping the screen and pixels appearing on your display. That journey involves DNS resolution, TCP connections, TLS handshakes, HTTP requests, load balancers, application servers, databases, CDNs, and object storage. Every single one of those components is something that we'll cover in this course. So let us start this journey and let's cover it step by step. Now let us start with the client-server model because that is the foundation of every system design interview that you'll encounter. The concept is pretty straightforward. A client is any device or application that initiates a request. A server is any machine that receives that request, processes it, and sends back a response. When you open your browser and go to, let's say, youtube.com, your browser is the client. YouTube server receives the request, queries the database, builds the page, and sends it back to your browser. Now, clients can take many forms. A web browser like Chrome or Safari is a client. A mobile app like Instagram app or WhatsApp, they're also a client. A desktop application like Slack or VS Code, they're also a client. So here's the one thing that surprised people, which is that another server can be a client too. For example, when server A calls server B's API to fetch data, server A is acting as a client in that interaction. On the server side, there are also different types. A web server like Nginx or Apache serves static files like HTML, CSS, and images. An application server running Node.js, Django, or Spring Boot executes your business logic. And a database server like PostgreSQL or MySQL stores and retrieves your persistent data. We'll go much more deeper into these server types in section 3. There are the few key characteristics that distinguish the clients from servers. The client is the one that initiates communication. The server waits and listens for incoming requests. In terms of quantity, there are typically millions of clients, one per user, but only hundreds to thousands of servers. Clients, they live on the user's device, while servers, they live in data centers. And here's a critical difference. Clients can go offline anytime. However, the servers, they should be always on because if the server goes down, every client that depends on it will be affected. So the key takeaway here is that every system you will ever design follows this model. The client sends a request, the server processes it, and the server then sends back a response. Everything else we'll cover in this course, which is areas like load balancers, caches, databases, CDNs, all of those components, they sit between or behind this interaction as well. Now at its simplest, a client-server system looks like this. You have millions of clients connecting to one server, and that server connects to one database. Imagine 1,000 users, they open youtube.com simultaneously. All 1,000 of the requests, they will go to the same server. The server queries a database for each request, and the server then sends back the response to each client. This works fine at this smaller scale, but at YouTube scales, which is like roughly 2.5 billion monthly active users, a single server simply cannot handle the load. And this is a fundamental problem that system design solves. How do you serve millions of clients reliably and fast? To understand why a single server fails, let us look at what a typical web server can actually handle. A mid-range server supports around 1,000 to 10,000 concurrent connections and can handle roughly 500 to 5,000 requests per second depending on the complexity, and it comes with generally 8 to 64 GB of RAM and has 1 to 10 terabytes of storage. Now compare that to YouTube's actual load. YouTube handles over 500,000 requests per second. Over 500 hours of those videos are uploaded every single minute, and users watch over 1 billion hours of video per day. When you do the math, a single server handles roughly 0.1% of YouTube's traffic. The remaining 99.9% is what system design is actually about. And this is where the rest of the course comes in. Every section builds on this basic client-server model and solves a very specific scaling problem. Load balancers, they'll distribute the clients across multiple servers so no single server gets overwhelmed. Databases, they get separated onto their own machines so the application server is not competing for resources. Caches, they reduce the database load by storing frequently accessed data into the memory. And CDNs, they serve the content from locations physically closer to the client, cutting down the latency. The client-server model itself does not change. It just scales with more traffic and more users. And learning how to scale it is exactly what this entire course is about. Now let's talk about DNS, which is the domain name system. This is the very first thing that happens when you try to visit any website. When you type, let's say, youtube.com into your browser, your computer needs to figure out the IP address of YouTube server. Computers do not communicate using human readable domain names. They communicate using IP addresses, which are numerical addresses like, let's say, 142.250.80.46. DNS is a system that translates the domain name you type into the IP address your computer needs. The simplest way to think about DNS is as a phone book. You know a person's name, let's say youtube.com, but you need their phone number, which is 142.250.80.46, to actually be able to reach them. DNS performs this lookup for you. So youtube.com will resolve to the IP address we just said, which is 142.250.80.46. And let's say Instagram will have their own IP address starting with 157.240, and then Amazon will have their own IP address, which starts, let's say, from 205.251. So the key point here is that every domain name maps to one or more IP addresses. So now you might be actually wondering that, okay, why not just use IP addresses directly? Why do we need this translation layer at all? There are 4 key reasons. The first is obviously human readability. YouTube.com is a lot easier to remember than the IP address, let's say like 142.250.80.46. The second is that IP addresses, they actually do change. When companies they move servers or change infrastructure providers, the IP addresses changes, but DNS absorbs that change. The domain name stays the same and DNS just points to the new IP. The third reason is that a single domain can have multiple IP addresses. YouTube has hundreds of servers and DNS can return different IPs for different users. And the fourth reason is load distribution. DNS can route users to geographically nearest server, which reduces the latency. There are also different types of DNS records that serve different purposes. So an A record maps to a domain to an IP4 address. A AAA, which is 4A record, maps a domain to an IPv6 address. A CNAME record maps a domain to another domain, acting as an alias. For example, www.youtube.com might point to, let's say, youtube-ui.google.com. An MX record specifies the mail server for a domain, and an NS record identifies the authoritative name server for a domain. For system design interviews, A records and CNAME records are the most relevant ones. Now that we know what DNS does, let us walk through how DNS resolution actually works step by step. When your browser needs to resolve, let's say, youtube.com, it does not just ask one server. It goes through multiple levels of lookup, and each level either has the answer cached or forwards the query to the next level. The first thing that happens is your browser checks its own cache. If you visited, let's say, youtube.com 2 minutes ago, the browser already has the IP address stored locally and skips the entire DNS lookup. If the browser does not have it, the operating system checks its local DNS cache. If the OS does not have it either, then the query goes out to your ISP's recursive resolver. This is a DNS server operated by your internet service provider, and its job is to resolve the query on your behalf. Now the ISP's resolver may have the answer cached from a previous lookup by another customer, so if it does, it returns the IP address immediately. If it does not, then it starts a chain of queries. First, it asks one of the 13 root name server clusters. There are 13 of these distributed around the world, and they are the starting point for all DNS resolution. The root server does not know YouTube's IP address, but it does know who is responsible for .com domains. So it responds with the address of the .com TLD server. Then the resolver asks the .com TLD server, and that server responds with the address of Google's authoritative DNS server, the server that actually knows YouTube's IP address. Finally, the resolver asks on Google's authoritative DNS server, and it responds with the actual IP address, let's say 142.250.80.46, with a TTL or time to live, so for example 300 seconds. Important. It means every server in this chain will cache the result for roughly 300 seconds, which is 5 minutes. For the next 5 minutes, anyone else who looks up youtube.com will get the cached answer without going through the full resolution chain. This is how DNS scales to handle billions of lookups per day without the root servers being overrun. Now, here is where DNS becomes directly relevant to system design interviews. DNS is not just internet plumbing that you set up once and forget. It's an active, powerful component in system architecture that enables three important capabilities. The first is global load balancing through something called GeoDNS. This is where the same domain name resolves to different IP addresses depending on where the user is located. So let's say a user in India making a DNS query for youtube.com will get the IP address of the Mumbai data center, something like, let's say, 3493.150. A user in the United States will get the IP address of, let's say, Iowa data center in US, which might be, let's say, 142.250.8046. And a user in Europe will get the IP address of the Belgium data center. Same domain name, but they will have different IP addresses based on the user's geographic location. This is how YouTube and other global services serve content from the nearest data center, minimizing latency. The second capability is failover and high availability. Suppose your primary server is at IP address, let's say 10.0.100, and your backup server is at 10.0.200. Under normal conditions, DNS resolves the domain to the primary server. If the primary goes down, you update the DNS record to point to the backup server. When the primary is restored, you update the DNS back. Now there is an important trade-off with the TTL value here. A low TTL like 60 seconds means clients will pick up the DNS changes quickly, so the failover is fast. But it also means that more DNS queries because the cache expires frequently. A high TTL, like let's say 3600 seconds, means fewer DNS queries but slower failover because clients are still using the cached, now stale IP address for up to an hour. The third capability is CDN integration. A CDN record can point your domain to a CDN provider like Cloudflare or Akamai. When a user resolves youtube.com, DNS actually redirects to the CDN's edge server closest to the user, not YouTube's origin server. This is fundamentally how CDNs intercept and serve traffic. One important thing to keep in mind is that DNS is not real time. Because of TTL based caching, changes to DNS records propagates over minutes to hours, so they are not instant. So if you are designing for instant failover, DNS alone is not sufficient. You need additional layers like load balancers and health checks, which we will cover later in this course. Okay, now let us talk about IP addresses and ports. Once DNS gives us the IP address of a server, we actually need two pieces of information to establish a connection. The first is the IP address, which identifies which machine we are connecting to. The second is the port number, which identifies which application on that machine should receive the request. An IP address identifies a specific machine on the internet. So there are two versions. IPv4 addresses look like, let's say, 142.250.8046. They are 4 bytes long and they support roughly 4.3 billion unique addresses. IPv6 addresses, they look like something 2607 colon F8 B0 and this long string that you see on the screen. They are 16 bytes long and they support a virtually unlimited numbers of addresses. IPv4 is running out because 4.3 billion addresses is not enough for 8 billion people plus all of their devices. So IPv6 addresses actually solve this problem, but adoption has been gradual, so most systems currently support both. Now the port number. Think of the IP address as a building address and the port number as the apartment number. A single server can run multiple applications simultaneously, and the port number tells us, the operating system, which application should receive the incoming request. There are well-known port numbers that you should be familiar with. Port 80 is for HTTP, unencrypted web traffic. Port 443 is for HTTPS, which is encrypted web traffic, and this is what virtually all modern websites use. Port 22 is for SSH, which is for secure remote and terminal access. Port 5432 is for PostgreSQL, port 6379 is for Redis, port 3306 is for MySQL, and port 27017 is for MongoDB. Browser connects to YouTube. It first resolves youtube.com to IP address like 142.250.80.46 through DNS. Then it connects to the IP address 142.250.80.46 on port number 443 because it's an HTTPS connection. The combination of IP address plus port gives us a full address, just like the building address plus an apartment number gives you the full physical location. In system design interviews, this is why you see architecture diagrams with labels like PostgreSQL on port 5432 or Redis on port 6379. Each service on a machine listens on its own port, and other components connect to the right port to reach the right service. Now that we know how to find a server using IP addresses and ports, we need a protocol to actually send data between the client and the server. There are two fundamental transport protocols, TCP and UDP. They solve the same problem, moving data between two machines, but they offer very different guarantees. Let us start with TCP, the Transmission Control Protocol. TCP guarantees that your data arrives completely, in the correct order, and without corruption. It achieves this through a connection-oriented approach, which means the client and server must establish a connection before any data can flow. The connection is established through what is called a three-way handshake. First, a client sends a SYN packet to the server, which essentially says that, hey, I want to connect. Then the server responds with a SYN/-ACK, which says like, okay, I acknowledge your request. And then the client sends back an ACK request, which is the, okay, great, connection established. Only after these three-step handshake can the actual data start flowing. This handshake adds latency, roughly 1.5 round trips, which translates to about 50 to 150 milliseconds, depending on the distance between the client and server. Now, TCP provides several guarantees in exchange for this overhead. It guarantees that order delivery, which is, meaning packets they'll arrive in the same sequence that they are sent. It guarantees reliable delivery, meaning lost packets are automatically detected and retransmitted. It performs error checking, so corrupted packets are detected and re-requested. It also implements flow control, so the sender slows down if the receiver is overwhelmed. And it implements congestion control, so the sender slows down if the network itself is congested. But all of these guarantees come at a cost. Beyond the handshake latency, there is 20 bytes of overhead per packet for headers. The receiver must acknowledge every packet it receives, and if a packet is lost, it gets retransmitted, which adds even more latency. For most web applications, this overhead is perfectly acceptable. But for something like, let's say, a live video call, a retransmitted packet from 2 seconds ago is not very useful. And the conversation by that time has moved on, so the user needs the current video frame, not an old one. And this is exactly where UDP comes in. So UDP, which is the user datagram protocol, takes the opposite approach from TCP. It sends data without establishing a connection and without guaranteeing the delivery. It is essentially a fire and forget protocol. With UDP, the client just sends a data packet directly to the server. There is no handshake, no acknowledgement, no retransmission. If the packet is lost, neither side actually knows about it. If the packet arrives out of order, the application has to handle that itself. UDP provides no connection setup, no delivery guarantee, no ordering guarantee, and no congestion control. What it does is actually provide is minimal overhead. It's just an 8-byte header compared to TCP's 20 bytes and immediate data transmission with no handshake delay. So now, when should you use each of the protocol? Let me walk through common use cases. Web browsing over HTTP and HTTPS should use TCP because web pages must load completely and correctly. API calls using REST or GraphQL should use TCP because the request response must be reliable. Database queries should use TCP because data integrity is non-negotiable. And file transfers should also use TCP because every byte must arrive correctly. On the other hand, live video streaming should use UDP because a dropped frame is better than a delayed frame. Voice and video calls over Zoom or Teams should also use UDP because real-time communication matters much more than perfect quality. Online gaming should also use UDP because low latency matters much more than occasional packet loss. And interestingly, DNS lookups use UDP as well for the initial small query, but they fall back to TCP if the response is too large. Now, in most system design interviews, your services will communicate over TCP because you're designing HTTP APIs, database connections, and gRPC services. You would specifically mention UDP when designing live streaming services, real-time multiplayer gaming backends, or IoT telemetry ingestion where millions of sensors are sending small packets. One thing worth mentioning is that modern video services like YouTube and Netflix, they actually use TCP for their video delivery, not UDP. They use HTTP based protocols called HLS and Dash that break the video into small chunks of 2 to 10 seconds each, download them over TCP, and buffer them on the client side. This works because the video is pre recorded, so a small delay for buffering is acceptable. Live video calls, on the other hand, use UDP because there's no buffer window. You need the audio and video right now. Okay, now let us move up the stack to HTTP, which is a Hypertext Transfer Protocol. HTTP is the application layer protocol that runs on top of TCP and it defines how clients and servers structure their communication. Specifically, it defines what a request looks like, what a response looks like, and what metadata travels along with each. HTTP is a request response protocol. Every HTTP interaction follows the same pattern. The client sends a request that includes 4 components: the method, which specifies what action to perform, like let's say get or post; the URL, which identifies which resource to act on, like let's say /video/abc123; then the headers, which carry the metadata like authentication tokens, content type, and caching instructions; and optionally a body, which carries the data payload for operations like post or put. The server then sends back a response that also has 4 components: a status code that indicates what happened, like let's say HTTP 200 for OK or 404 for not found; headers with metadata like content type and cache directives; and a body containing the actual data, whether that is an HTML page, JSON data, or image bytes. Now let me give you a concrete example. Let's say when you load a YouTube video page, your browser sends a GET request to youtube.com with a path -watch $v equal to followed by the video ID. It includes headers like host, accept, an authorization header with your auth token, and a cookie header with your session data. The server processes this and responds with the HTTP 200 OK status, a content type header indicating HTML, and the body containing the full HTML page for that video. Now, HTTP has evolved over time through several versions. If you look over here on the screen, HTTP 1.0 released in 1996, it opened a new TCP connection for every request, which was pretty inefficient. HTTP 1.1, which was released in 1997, it introduced keep alive connections, meaning the same TCP connection could be reused for multiple requests. HTTP 2, released in 2015, introduced multiplexing, which allows multiple requests to flow over a single connection in parallel. And HTTP 3, which released in 2022, uses a protocol called QUIC that is built on UDP instead of TCP, which reduces the latency even further. Most production systems today use HTTP 1.1 or HTTP 2, and HTTP 3 is actually adoption is growing, especially at Google and Cloudflare. Now let us talk about HTTP methods because each method signals a different intent, and using the correct method is not just convention. It affects caching behavior, idempotency, and how intermediaries like proxies, CDNs, and load balancers will handle the request. There are 5 HTTP methods that you need to know. The first is GET, which is used to retrieve a source. GET is idempotent and does not have a request body. An example would be, let's say, get/users/123 to fetch a specific user's profile. The second HTTP method is POST, which is used to create a new resource. POST is not idempotent and it does have a request body. An example could be, let's say, post users to create a new user. The third is method PUT so which replaces a resource entirely. Put is idempotent and has a request body. An example is, let's say, a request put request slash users slash user ID 123. That will replace all of user ID 123's data. The fourth is patch, which actually partially updates a resource. Patch is not idempotent and has a request body. An example request would be patch slash users slash 123 to update just, let's say, the email address in the profile. And the fifth method in the HTTP methods list is delete, which removes a resource. Delete is idempotent and does not have a request body either. An example would be, let's say, delete slash users slash 123. Now let's talk more deeply about what idempotency means in system design. An operation is idempotent if calling it multiple times produces the same result as calling it once. So let's say get request users slash 123 returns the user 123 every time you call it. If you call it 10 times, you'll get the same user. That is idempotent. Deleting a user, let's say delete user slash 123 will delete the user, and if you call it again, the answer is still deleted. Same result. And that is also idempotent. Now if you put a user, let's say put users slash 123, it replaces the user with the same data, and again it will be same result every time, so that's idempotent as well. But posting a users, which is post slash users endpoint, it creates a new user every time you call it. So if you call it 3 times, you get 3 users. That is not an idempotent operation. So why does this matter in system design? Now consider this scenario. Let's say a user clicks on submit order button and the network is slow. They get impatient and they click it again. If post orders endpoint is not idempotent, 2 orders are now created and the customer will get charged twice. In distributed systems, network failures and retries happen all the time. Non-idempotent operations need explicit duplicate protection like idempotency keys or unique request IDs. That is exactly why payment APIs like Stripe require an idempotency key with every post request. What in system design interviews is, let's say if a candidate is using post endpoint for everything. Let's say if an interviewer is using, the candidate is using post for, let's say, get user or delete post in the API design, that will signal that, the candidate might not be that familiar with REST conventions, and that's not a good thing. The HTTP method should convey the action and the URL should identify the resource. Now let us cover HTTP status codes. Status codes are grouped in 5 categories based on the first digit, and you do not need to memorize all of them at all, but you should know the ones that come up in every system design discussion. The 5 categories are the one starting with 1 for informational responses, meaning the requests were received and processing is continuing. The second category is status codes that start with 200, like with, let's say, which is for success, meaning the request was successful. The status codes that are in 300 categories, they mean redirection, meaning the client needs to take additional action. The HTTP codes in the 400 range are there mean for client errors, meaning the client sent a bad request. And the HTTP code range in 500 range is for server errors, meaning the server failed to process a valid request. Now let me walk you through the specific status codes you should know. In the 200 range success category, 200 OK means the request succeeded. The 201 created means a new resource was created, and there is a typical response to a post request. 202 accepted means the request has been accepted for asynchronous processing and the job is queued but not done. And 204 means no content, means like the operation succeeded but there is no body to return, which is the typical response to a delete operation. In the 300 category, 301 move permanently means the resource has a new URL and the old one should no longer be used. 302 found means a temporary redirect, and 304 not modified means the cache version is still valid, so there is no need to download the content again. Now in the 400 range, which is for client errors, so 400 means bad requests, which means the client sent invalid data like missing a required field. 401 unauthorized means authentication is required, either no token is provided or the token has itself expired. 403 forbidden means the client is authenticated but not authorized, so they do not have the permission. And 404 not found means the resource does not exist. 409 conflict means the request conflicts with the current state, like trying to register a username that already exists. And 429 too many requests means the rate limit has been exceeded. Now, if you look at the 500 server error category, 500 internal error means the server crashed or hit an unhandled exception. 502 bad gateway means an upstream server behind the load balancer returned an invalid response. 503 service unavailable means the server is overloaded or in maintenance mode. And 504 gateway timeout means the upstream server did not respond in time. Now, here is where it actually matters in system design specifically. In microservices architecture, where you have a client, a load balancer, an API gateway, let's say service A, service B, and database, a 502 or 504 usually means service B is down or slow because the gateway received a bad response from the upstream. A 503 will mean that the server is deliberately rejecting the request, perhaps because a circuit breaker has tripped. A HTTP 429 will means that the rate limit is working correctly, and that is actually a good thing because it's protecting the system itself. And 301 and 302 are critical for URL shorteners because the entire product is built on redirect status codes. Or TLS, which is transport layer security. When we say HTTPS, what we mean is HTTP plus TLS. TLS encrypts the communication between client and server so that nobody in between, not even your ISP, not the Wi-Fi operator, and ideally not the attacker on the network, can read or modify the data. TLS protects against three specific threats. The first is eavesdropping. Without TLS, anyone on the network can read your data in plain text. With TLS, the data is encrypted and unreadable to anyone who intercepts it. The second threat is tampering. Without TLS, data can be modified while it's in transit. With TLS, integrity checks detects any modification. And the third threat is impersonation. So without TLS, an attacker could pretend to be the server. With TLS, the server proves their identity with a certificate issued by a trusted certificate authority. So now let's talk about how does TLS actually work. So before encrypted data can flow, the client and server, they perform what is called a TLS handshake. So let me walk through the steps. First, the client sends a client hello message telling the server which TLS versions and cipher suites it supports. Then the server responds with a server hello plus its certificate saying, for example, okay, let us use TLS 1.3 with AES 256 encryption, and here is my certificate signed by Let's Encrypt. Then the client verifies the certificate. Is it valid? Is it from a trusted certificate authority? And does the domain name match? And has it expired? Then the client and server perform a key exchange where they agree on a shared secret key using asymmetric encryption. And finally, all further communication is encrypted using that shared key with symmetric encryption. The performance cost of this handshake is worth knowing. TLS 1.2 adds 2 additional round trips, roughly 100 to 300 milliseconds. TLS 1.3 improves this to just 1 additional round trip, roughly 50 to 150 milliseconds. And TLS 1.3 with 0 RTT resumption, which works for returning visitors, adds 0 additional round trips. For system design, there are 3 important things to remember about TLS. First, all external traffic should be HTTPS. Second, TLS is typically terminated at the load balancer, meaning the load balancer decrypts the incoming HTTPS request, inspects it, and forwards it as an unencrypted HTTP to the backend servers. This is the most common production pattern. And third, internal service-to-service traffic within a data center is often unencrypted for performance, though zero trust environments use mutual TLS or MTLS, where both sides verify each other's identity. Now that we have covered all the individual pieces, which are DNS, IP addresses and ports, TCP, HTTP, and TLS, let us put them all together and trace the complete HTTP request from start to finish. When a user's browsers want to load a page, the first step is DNS resolution, which looks up the IP address. And this takes roughly 0 to 50 milliseconds and is usually cached from a previous visit. Then the browser performs a TCP handshake to establish a connection, which takes roughly 20 to 50 milliseconds. Then a TLS handshake to negotiate encryption, which takes roughly 50 to 150 milliseconds. At that point, the connection is established and the browser sends the actual HTTP request. Now the request reaches the server infrastructure. If the request is for a static asset like an image or a CSS file, a CDN edge server has it cached, then the CDN will respond directly. This is the cache hit path and the total latency is around 30 milliseconds. If the CDN does not have the content cached, it forwards the request to the origin server. The request goes through a load balancer which routes it to a healthy application server. The application server processes the request, queries the database, builds the response, and sends it back through the load balancer and CDN to the user. This is the cache miss path and it takes roughly 200 to 500 milliseconds total. Now let me break down the timing. DNS resolution is 0 to 50 milliseconds, usually cached. TCP handshake is 20 to 50 milliseconds. TLS handshake is 50 to 150 milliseconds. And request transit from client to server is 10 to 100 milliseconds depending on the physical distance. Server processing, including the application logic and database queries, can be from 10 to 200 milliseconds, and response transit from server back to client would be 10 to 100 milliseconds. Total end-to-end will be roughly 100 to 650 milliseconds. The important insight here is what dominates that latency. At smaller scale, server processing time is the biggest factor. At global scale, network latency due to physical distance between the user and the server is the main reason. And this is exactly why CDNs exist. Serving content from a server 50 km away instead of 10,000 kilometers away eliminates hundreds of milliseconds of latency. Now let us answer the question we posed at the beginning of the section, which is what happens when you type youtube.com in the browser. This is one of the most common technical interview questions and it touches every concept we have covered in this section. Let me walk you through the complete sequence. Step 1. The browser parses a URL. It identifies the protocol as HTTPS, the domain as youtube.com, and the port as 443. Step 2 is DNS resolution. So the browser cache checks its cache, then the OS cache, then the ISP resolver, which queries the root name server, then the .com TLD server, and then the Google's authoritative DNS. The result is an IP address like 142.250.80.46, and this takes roughly 0 to 50 milliseconds if cached. Step 3 is TCP connection. So the browser performs a three-way handshake with 142.250.80.46 on port 443. Then it does SYN acknowledge, and then connection is established. This takes roughly 20 to 50 milliseconds. Step 4 is TLS handshake, in which the client and server exchange messages with certificate key exchange and they establish the encrypted channel. That takes roughly 50 to 150 milliseconds. Step 5 is the browser sends the HTTP request. The get, let's say HTTP2 with host, accept, and cookie headers are the main components. And for step 6, it's the server-side processing. So the load balancer routes the request to a healthy application server. The application server then validates the session cookie, queries the database for personalized list recommendations, queries the caches for trending videos, builds the HTML page with video thumbnails, and returns the response. This will roughly take idly from 50 to 200 milliseconds. And then in step 7, the server sends back the HTTP response, status 200 OK, content type text HTML, and the full HTML page. Step 8 would be the browser start rendering, so it parses the HTML, discovers references to CSS files, JavaScript files, and image thumbnails. So it fires the parallel request for each of these assets, and because they are static files, they are typically served from the CDN in about 30 milliseconds each. There might be 50 to 100 additional asset requests. In step 9, the page becomes interactive. CSS is applied, JavaScript is executed, and thumbnails are loaded. The user sees the YouTube homepage now, so the total time from typing the URL to seeing the page would be roughly around 1 to 3 seconds. Now, if an interviewer asks you this question in a system design interview, you don't need to recite every detail, but you do need to cover all the layers, which is DNS, then TCP, then DLS, then HTTP, then server processing, then response, and then rendering. Then offer to go deeper on whichever layer the interviewer will be interested in. Now let us talk about latency and round trip time because this concept underpins almost every design decision you will make. Latency is the time it takes for data to travel from one point to another. Round trip time or RTT is the time for requests to travel from client to server and for the response to come back. And there is a hard physical limit on how fast data can travel, which is the speed of light. In fiber optic cable, light travels at approximately 200k kilometers per second, which is about two-thirds the speed of the light in vacuum. So let me put some real distances to this. From Mumbai to Mumbai, same city, roughly 10 kilometers, this will be one-way latency is about 0.05 milliseconds. From Mumbai to Singapore, that will be around 4000 kilometers, the one-way latency is about 20 milliseconds. From Mumbai to London, that will be roughly 7,000 kilometers, which is one way is 36 milliseconds. And from Mumbai to San Francisco, that will be 13,000 kilometers, and one way is about 70 milliseconds. Now, the round trip time is double the one way, so Mumbai to San Francisco round trip will be around 136 milliseconds. And these are the theoretical minimums. Real world RTD is typically 2 to 5 times higher due to routing hops, network switches, and processing at each intermediate point. Now let me share a table of latency numbers that every system design person should internalize because these are numbers that explain why we make architectural decisions that we do. A reading from L1 cache on a CPU takes roughly about 0.5 nanoseconds, L2 cache is about 7 nanoseconds, RAM access is about 100 nanoseconds. A reading from an SSD takes about 150 milliseconds, which is 150k nanoseconds, and reading from a hard disk drive is about 10 milliseconds, which is 10 million nanoseconds. A round trip within the same data center takes roughly around 0.5 milliseconds. A round trip within the same continent takes roughly around 50 to 100 milliseconds. And a cross-continent round trip roughly takes 100 to 300 milliseconds. Now, the key insight from these numbers is the magnitude of differences. A reading from RAM takes 100 nanoseconds. A reading from disk takes 10 million nanoseconds. That is a literally 100k difference. And reading from an in-memory cache like Redis in the same data center takes about 500 microseconds compared to 10 milliseconds from the disk. This is why caching works. It's not that caching is a little faster, it's operating at a fundamentally different time scale. 5 orders of magnitude faster, which is very important and very useful for system design and building systems. Now let me also give you a practical example. Say the requirement is that YouTube homepage must load in under 500 milliseconds at P95. You can break this into a latency budget, so that will be 0 milliseconds for DNS because it is cached, 50 milliseconds for TCP and TLS with connection reuse, 100 milliseconds for server processing, 100 milliseconds for network transit assuming CDN for static assets, 200 milliseconds for browser rendering, and 50 milliseconds of buffer. That totals 500 milliseconds. So now if your server processing takes 300 milliseconds instead of 100, you have already blown the budget before the browser even started rendering. This is why capacity estimation and caching decisions are super important. And this is a deeper point I want to make about latency. Every major system design decision is, at its core, a latency optimization. Let me walk you through this. So why do we use CDNs? To solve cross-continental network latency by serving the content from one edge server near the user. Why do we use Redis caches? To solve database query latency by serving data from RAM instead of disk. Why do we use read replicas? To solve the database overload latency by distributing reads across multiple copies. And why do we use load balancers? Because to solve single server overload latency by distributing requests across many servers. And why do we shard databases? To solve large table scan latency by making each table smaller and faster to query. And similarly, why do we use async processing with message queues? To solve the problem of long operations, blocking the user by returning immediately and processing in the background. And then why do we use connection pooling? Because to avoid paying the TCP and TLS handshake latency on every request by reusing the existing connections. There's a hierarchy to these latencies that is worth memorizing. At the fastest end, in-memory application cache takes about 1 microsecond. Then, in-memory Redis is the same data center is about 500 microseconds. Then, an SSD database read with an index hit is about 1 millisecond. A database full scan without an index is 10 to 100 milliseconds. A cross-service call within the same region is 55 to 50 milliseconds, and a cross-region call is roughly 50 to 200 milliseconds. An external API call is roughly 100 to 500 milliseconds, and a data disk-based sort of a large data set is 1 to 10 seconds. The goal of system design is to keep your operations as high up this hierarchy as possible. So when you're discussing performance in a system design interview, you should be referencing specific latency numbers. Saying something vague like, let's say, okay, caching makes it faster is not ideal. But if you say something like a Redis cache, it takes about 500 milliseconds versus about 10 milliseconds for database query with an index, which is 20x improvement, that demonstrates quantitative reasoning and will set you apart in interviews. Let us recap everything we have covered in this section on how the internet works. We started with the client-server model, which is the foundation of all network systems. The client sends a request, the server processes it, and sends back a response. Then we covered DNS, which translates domain names to IP addresses and plays an active role in global load balancing, CDN integration, and failover. Then IP addresses and ports, which together forms a full IP address of a specific application on a specific machine. Then we covered TCP and UDP, the two transport protocols, where TCP provides a reliable order delivery for web traffic and database connections, and UDP provides a fast delivery for live video and gaming. Then we covered HTTP and HTTPS, the application layer protocols that structure all web communication through methods, status codes, headers, and bodies. And then we covered TLS, which encrypts the communication and is typically terminated at the load balance in production. Then we trace the complete request response lifecycle end to end. And finally, we covered latency and round trip time, which drives the caching, CDN, replication, and sharding design decisions. So let us start section 3 by talking about servers and application architecture. This is where we move from the network layer into the actual machines that run your application. So what is a server? A server is just a computer that listens for incoming requests, processes them, and sends back responses. And I want to be clear about something right away. There is nothing special about the hardware. Any laptop can even also be a server. So what makes machine a server is that the software running on it and the role it plays in the architecture. If your laptop is running Nginx and is listening on port 80, okay, that's a server as well. So in this section, we are going to cover 6 core topics. We'll start with the single server architecture, which is the simplest possible setup. Then we'll talk about stateful versus stateless services, which is one of the most important concepts you need to understand for scaling. After that, we'll look at different types of servers, which is web servers, application servers, and database servers. Then we'll cover reverse proxies and API gateways, so two of the components that sit in front of your servers and handle cross-cutting concerns. And finally, we'll compare monolithic versus microservices architecture. So when people say the word server, they could mean very different things depending on the environment. The first type is bare metal. This is a physical machine sitting in a data center and you own the hardware. Think about like Dell PowerEdge or HP servers. The second type is a virtual machine or VM. This is a software-defined server running on shared physical hardware. For example, this could be AWS EC2 instances, Azure VMs, or Google Compute Engine instances. So these are all examples of virtual machines. The third type is a container. A container is a lightweight, isolated process that shares the host operating system's kernel. Docker containers running on Kubernetes are the most common example. And the fourth type is serverless. With serverless, there is no server for you to manage at all. The cloud provider runs your code on demand. So examples for that is AWS Lambda and Azure Functions for this, so which are like the very popular serverless examples. 4 of these are just computers essentially running software. The abstraction level changes, the operational responsibility changes, but the fundamental concept is the same. Something is listening for web requests and sending back responses. So now let me give you a feel for what a typical production server looks like in terms of specs. A mid-range cloud server, let's say an AWS M5.2x large instance, would have 8 virtual CPUs, 32 GB of RAM, 500 GB of SSD storage, and network throughput of up to 10 Gbps. This will cost roughly $280 per month on demand and about $170 per month if you commit to a 1 year reserved instance. A single machine like this can handle somewhere between 1000 and 5000 concurrent connections, 500 to 200 HTTP requests per second, depending on the complexity of each request, and each request might involve, let's say, 10 to 50 database queries. So these are pretty solid numbers for a single machine. But to put it into perspective, let's say for a big website like youtube.com, that handles something like a scale of 500k requests per second. At that scale, you need hundreds to thousands of these machines working together, and the rest of the section will cover exactly how to organize them. Okay, now let us start with the simplest possible architecture, which is a single server setup. In a single server architecture, everything runs on one machine. The web server, the application code, and the database are all in the same box. You have multiple clients, maybe a browser, a mobile app, or another browser. They all send requests to this one server at a single IP address. So what exactly runs on this single server? There are three components. The first is the web server, typically Nginx or Apache. This listens on port 80 for HTTP and port 443 for HTTPS. It serves static files like HTML, CSS, JavaScript, and images directly. And for dynamic requests, it forwards those to the application code. Now the second component is the application code itself, something like a Node.js, Django, Spring Boot, or whichever framework you are using. This is where a business logic lives, for example, user authentication, API endpoints, and data processing. It typically runs on an internal port like 3000 or 8080. And now if you talk about the third component, which will be the database, so for example, PostgreSQL or MySQL, so this stores all of your persistent data. It runs on your own internal port, which is 5432 for Postgres and 3306 for MySQL. And all of that data is stored on the local disk of that same machine. So this setup works perfectly well in certain situations. If you're building a personal project, a prototype, or an early MVP, this is the right choice. If your traffic is low, let's say under 1000 daily active users, and your dataset is small, let's say under 10 GB, a single server will be able to handle it. And when you are a single developer with no team coordination needed, let's say in a startup environment, this simplicity is a huge advantage. But this architecture actually breaks in predictable ways as you grow. For example, CPU exhaustion is the first thing that you will notice. Requests start to queue up and the response types will start to spike up once you're above the 70% sustained CPU usage. Then there is a memory exhaustion. So for example, your processes start crashing with out-of-memory kills when RAM usage exceeds 90%. Disk I/O can also become a bottleneck, so where database queries slow down to seconds because the disk queue depth is actually too high. Network saturation will cause a packet loss and timeouts when you exceed 80% of your bandwidth. And the biggest problem of all of this is that it's a single point of failure. Let's say if this one server crashes, your entire system will go down. There is no backup, there's no failover, nothing. So the first scaling step is always the same. That we'll cover this in detail in section 5 as well. Is that you need to separate this database server from the application server. That one move immediately will give you the ability to scale them independently. This brings us to one of the most important concepts in all of system design, which is the distinction between stateful and stateless servers. This concept determines whether your application can scale horizontally. So if you do not understand this, scaling will always feel a pretty difficult thing to do. So a stateful server stores the client-specific data in its own memory. The server will remember each client between the requests. So let me walk you through an example for that. Let's say a user logs in and their request goes to server A. Server A stores the session in its own memory. So for example, the user ID is 123, the shopping cart has item 1 and 2. Now when request 2 comes in and it also goes to server A finds the session in its memory and everything works correctly. But now here's the problem. If request 2 goes to server B instead of server A, because maybe you added a second server to handle more traffic, server B has no memory of this user. The session is not found, the user will appear to be logged out, and their shopping cart will be empty. So from the user's perspective, the application just broke for no reason. Now if you contrast this with a stateless server, a stateless server stores no client-specific data in its own memory. All state lives in external shared storage, let's say a database, a cache, or the client itself through tokens. Here's how the same scenario will play out. The user logs in and receives a JWT token. Request 1 goes to server A. The client sends the JWT token in the request header. Server A validates the token, queries Redis for the card data, and serves a response. Now request 2 goes to server B, a completely different server. So the client sends the same JWT token. Server B validates the same token, queries the same Redis instance for the card, and it works perfectly. Any server can now handle any request, and that is the key insight here. Now let us look at why this distinction matters so much in practice, especially when it comes to scaling. With horizontal scaling, stateful servers make it difficult because you need session affinity, meaning you have to route each user to the same server every time. With stateless servers, scaling is pretty simple compared to stateful servers. So you just add more servers. For load balancing, stateful servers require what is called sticky sessions, where the load balancer must route each user back to the same server. Stateless servers have no such restriction. Any server can handle any request. So when a server fails in a stateful architecture, the user loses their session data and has to log in again. In a stateless architecture, there is no impact at all. The next request will just go to another server. So for deployments, a rolling restart in a stateful system loses all active sessions. In a stateless system, rolling restarts are completely seamless, and for memory usage, stateful servers consume more memory as the number of active users grow because each user's session lives in the memory. Whereas for stateless servers, they have constant memory usage because there is no user per user state in the memory, so it's much more easier to manage. So where does the state actually go in a stateless architecture? It moves to external stores. Session data goes to Redis or memcached. You store a key like let's say session ABC123 with the user ID, card data, and login time, and you set a TTL of something like 30 minutes. Authentication is handled through JWT tokens stored on the client. The token contains a user ID, roles, and an expiration timestamp, and the server validates it cryptographically without needing any database lookup. The user data goes to database like PostgreSQL or MySQL for persistent storage that survive the server restarts. And temporary data like async jobs and event processing goes to the message queue like Kafka or SQS. As you can see the diagram on the screen here, multiple clients connect to a load balancer. The load balancer then distributes the traffic across server A, server B, and server C, and all three servers connect to the same Redis session store and the same database. No server holds any unique state. They are completely interchangeable. So here's an important interview tip. When you propose adding servers in a system design interview, always explicitly say that your application servers are stateless. If the interviewer asks you, okay, what happens if server B goes down? Your answer should be that, okay, that nothing will be visible to the user. The load balancer will route the request to server A or server C, and they can serve it identically because all the state lives in Redis and the database. Now that we understand stateful versus stateless, let us look at the different types of servers you will find in a production architecture and what each one is responsible for. In production, different types of servers handle different responsibilities. Separating them allow each to be optimized and scaled independently. There are the three main types. The first is the web server, which is Nginx, Apache, and Caddy. These are the most common examples. The role of the web server is to handle HTTP connections, serve static files, and forward dynamic requests to the application server. Its responsibilities include accepting incoming TCP and HTTP connections, serving static files directly like HTML, CSS, JavaScript, and images, and forwarding dynamic requests to the application server as a reverse proxy, and do the TLS termination where it decrypts the HTTPS and forwards plain HTTP internally. It also does the compression using a gzip or broadly for text message responses and does the connection management including keep alive and timeouts. In terms of performance, Nginx can handle over 10,000 concurrent connections. Serving a static file takes roughly 1 millisecond, whereas forwarding a request to the application server adds about 1 to 2 milliseconds of overhead. The second type is the application server. This is where frameworks like Node.js, Django, Spring Boot, and ASP.NET live. The role of the application server is to execute business logic, process requests, and return responses. It routes the request to the correct handler, validates the input data, execute business logic like computing a feed or processing a payment, and it also does things like querying the database or cache, and then it builds the response as JSON or HTML. In addition to that, it also handles authentication or authorization. A typical API response will typically take 10 to 200 milliseconds. CPU bound work like image processing or ML inference can take up to from 100 milliseconds to 10 seconds, and an IO bound work like database queries will take roughly 5 to 50 milliseconds per query. Now, the third type is the database server. PostgreSQL, MySQL, MongoDB, and Redis are the common examples here. The role of the database server is to store, retrieve, and manage persistent data. So it executes queries like select, insert, update, and delete, and maintains the data integrity through ACID properties and constraints. And also manages the indexes for query performance, handles the concurrent access through locking and transactions, and it also handles the replication and backup. For performance, a simple index key lookup will take less than 1 millisecond. A complex join query will take roughly around 10 to 100 milliseconds. And a full table scan with no index can take roughly 100 milliseconds to 10 seconds depending on the table size. Walk you through how all three work together on a single request. Let's say a client sends a GET request to API/user/123. First, the web server, let's say Nginx, receives the HTTP request on port 443. Second, it decrypts the TLS encryption and forwards the plain HTTP request to the application server on port 8080. Third, the application server validates the JWT token and makes a call to the database. Fourth, the database server returns the user data. And fifth, the application server formats that data into a JSON response. And sixth, the web server then sends that response back to the client over HTTPS. Each of these three service types can be scaled independently, and that is one of the key reasons we separate them. Okay, now let us talk about reverse proxies because we have been mentioning this concept for a while and it's time to understand it much more deeply. A reverse proxy sits between clients and your backend servers. The client sends requests to the reverse proxy and the proxy forwards them to the appropriate backend server. The client never communicates directly with the backend servers and it actually doesn't even know where they exist and how do they exist. A reverse proxy does several important things. The first is load distribution, where it distributes requests across multiple backend servers. The second is TLS termination, where it handles encryption and decryption so the backend servers do not have to deal with that overhead. The third is compression, where it compresses responses using gzip or broadly before sending them back to the client. And the fourth is caching, where it caches the static responses to reduce the backend load. And the fifth is rate limiting, where it limits the number of requests per IP address per user. It also does security, where it hides the backend server IP addresses from clients and can block malicious requests. Now, one thing that confuses people is the difference between forward proxy and a reverse proxy. A forward proxy sits on the client side, so the flow goes like this: client, then forward proxy, then the internet, then the server. A corporate proxy or a VPN is a forward proxy. It protects and hides the client. A reverse proxy is the opposite. It sits on the server side and the flows goes like this: client, then the internet, then the reverse proxy, and then the backend servers. Nginx sitting in front of your application servers is a reverse proxy. It protects and hides the server, so the simplest way to remember is this: forward proxy protects the client and reverse proxy protects the server. In terms of technologies, Nginx is the most popular choice. It is a high performance and has very low memory usage. HA proxy is another option that offers more advanced load balancing capabilities for both TCP and HTTP traffic. Envoy is very commonly used in microservices service meshes, and Terraform is a container native and auto discovers services, which makes it very popular in Kubernetes environments. And Cloudflare operates as CDN plus reverse proxy delivered as a managed service. In practice, Nginx is the default choice for most production systems. It can handle tens of thousands of concurrent connections with minimal memory overhead. So unless you have a specific reason to choose something else, Nginx should always be the right starting point. And once you scale, you can definitely consider other options as well. Exactly where API gateways come in. An API gateway is essentially a specialized reverse proxy, but one that is designed specifically for API traffic. It adds application level concerns on top of the basic proxying that we have just talked about. So let me explain the difference between a plain reverse proxy and an API gateway. Both do load balancing and TLS termination, but a reverse proxy like Nginx only does basic request routing through URL path matching, while an API gateway supports advanced routing based on headers, query parameters, and HTTP methods. A reverse proxy has no authentication, or at best, very basic auth. An API gateway validates the JWT tokens, supports OAuth, and manages API keys. For rate limiting, a reverse proxy can do basic per IP limiting, but an API gateway does per user, per endpoint, and even per plan rate limiting. Meaning your free tier can get, let's say 100 requests per hour, while your premium tier will get 10,000. A reverse proxy, cannot transfer requests, but an API gateway can modify headers, request bodies, and query parameters. API gateways also support API versioning, so routing, let's say /v1 or /v2 to completely different services. They also provide detailed API usage metrics instead of just basic access logs, and they can also implement circuit breaking, which means automatically stopping calls to a service that is failing. Microservices architecture, the API gateway becomes a single entry point for all your client traffic. The client sends every request to the API gateway, and the gateway routes it to the correct service based on the URL path. Let's say request to API/users will go to the user service on port 8081. Request to API/post will go to post service on port 8082. And request to API/feed will go to the feed service on port 8083. And just like that, request to the API/media will go to the media service on port 8084. So let me walk you through exactly what happens at the API gateway when a request comes in. So the client sends a GET request to, let's say, endpoint API/feed query parameter page equal to 1 with the bearer token in the authorization header. The API gateway first validates that the JWT token, let's say, okay, is it valid? Is it expired? And then it extracts the user ID from the token itself. And then it checks the rate limit. Has the user exceeded, let's say, 120 requests per hour? Then it routes the request to the feed service based on the URL path. Then it adds internal headers like, let's say, x/-user ID, let's say u12345, so the downstream service knows who the request is from. And then it logs everything, the timestamp, user ID, endpoint, and response time. By the time the feed service receives the request, the user ID has already been validated. The feed service does not need to handle authentication itself, so this is a huge win because you do not want every single microservice re-implementing the authentication logic. For technologies, Kong is a popular open source option with a strong plugin system for self-hosted setups. AWS API Gateway is a managed service that works well in AWS native architectures. Azure API Management is the equivalent of Azure, and for APIG from Google is the GCP native enterprise option for API gateways. In addition to that, for Kubernetes native gateway option, that will be Traffic. That works pretty well as well. Here is a pretty important interview tip. In system design interviews, you should always include an API gateway in your architecture diagram. It shows the interviewer that you do understand cross-cutting concerns like authentication, rate limiting, and routing, and that you know these as responsibilities that should not be duplicated across multiple services. So it's ideal to put them and implement them as part of the API gateway. So now that we have covered the infrastructure layer, which is servers, proxies, and gateways, now let us talk about how you actually organize your application code. And we'll start with the most straightforward approach, which is the monolithic architecture. A monolith is a single deployable unit that contains all of the application's functionality. All features, all business logic, all data access code lives in one code base and deploys as one process. So let me describe what this looks like in practice. You would have one application directory. Inside it, you would have separate folders for each feature area. Let's say users handle registration, profiles, and authentication. Posts, they handle the post creation, deletion, and retrieval. Feed folder will handle the feed generation and ranking. Media folder will hold the code that handles image upload and processing. Notification folder will hold the code that handles push notifications and email. And just like that, search folder will have the code that deals with the user and content search. And there is also a shared folder with database connections, utilities, and models that every other folder will use. In this architecture, you also have a single database folder with one schema file containing all of your tables, and you would have one deployment script that deploys to one server. So when this application runs, it is one process on one server listening on port 8080. Request to endpoint like API/users get routed to users module. Request to API/post endpoint will go to the post module. Request to endpoint like API/feed go to the feed module. And request to endpoint like API/media will go to the media module. All of these modules share the same database connection pool, the same memory space, the same deployment lifecycle, and the same programming language. Now, the advantages of these approach are pretty significant and should not be underestimated for certain scenarios. Number one is that it's simple to develop because you have just one code base, one IDE, one build process. It is simple to deploy because you build one artifact and deploy it on one server. It is simple to debug because you have one process, one log stream, and stack traces that span the full request. It is simple to test because the integration tests run against a single process. There is no network overhead because modules call each other through function calls, not HTTP requests. And you get full transaction support because you have a single database with asset transactions across all tables. A monolith is the right choice in certain scenarios. For example, when you have a team of 1 to 10 engineers, let's say when your product is in early stage with uncertain requirements and rapid iteration is required. The third reason could be, let's say when you have less than 100,000 daily active users and when you have a single deployment environment. Okay, now let's talk about microservices architecture. A microservices architecture splits the application into small, independently deployable services. Each service owns a specific business capability and its own data. The last part about owning its own data is very important and we'll come back to it soon. The structure looks very different from a monolith. So instead of one repository with everything in it, you would have separate repositories for each service. The user service has its own source code, its own database that stores the users, its own Docker file, and its own deployment configuration. The post service will also have its own repo, its own database for posts, likes, and comments, its own Docker file, and again its own deployment config. Similarly, the feed service will have its own repo, its own Redis cache for pre-computed feeds, its own Docker file, and its own deployment configuration. And similarly, the media service will also have its own repo, its own object storage in S3 for images and videos, its own Docker file, and similarly, its own deployment config. Each of these services is owned by a separate team. They can be now built in different programming languages, they can be deployed on different schedules, and they can be scaled to different sizes based on their own individual traffic patterns. Now, when you split an application into separate services, those services need to communicate with each other. So there are three main patterns for this. The first pattern is the synchronous communication using REST or gRPC. You use this when you need an immediate response. For example, the feed service calls a user service to get user profile information. It needs that data right now to build the feed. The second pattern would be asynchronous communication using a message queue. You use this when the work can be processed later. For example, when a post is created, the post service publishes a post created event to a message queue like Kafka, and the feed service picks it up and regenerates the relevant feeds whenever it can. The third pattern is event driven pub/sub, which is like publisher subscriber pattern. You use this when multiple consumers need to react to the same event. A new post might trigger a feed update and a notification and an analytics event, all from a single published event. Now let me come back to the critical principle I mentioned, which is that each service owns its own data. The user service is the only service that reads from and writes to the user's database. The post service is the only service that reads from and writes to the post database. The feed service is the only service that reads from and writes to the feed cache. If the feed service needs user's data, it will call the user service API. It will not query the user's database directly. This is called database per service and is fundamental to microservices. Without it, your services are coupled at the data layer and you cannot deploy or scale them independently. At that point, you just have distributed monolith, which gives you all the complexity of the microservices without none of the benefits, so we should ideally not do that. Now let us put these two architectures side by side and really understand the trade-offs, because this is not a case where one is always better than the other. For development speed early on, the monolith is faster because you do not need to define API contracts between services. But at scale, microservices are faster because each team works in a small, focused code base with fewer merge conflicts. For deployment, a monolith is all or nothing. One deployment, everything goes out together. With microservices, each service deploys independently. Now for scaling, a monolithic means you scale the entire application even if only one feature is under heavy load. Whereas for microservices, you let you scale individual services. So then it's easy to scale that way, and you only scale the services that have higher traffic load. For failure isolation, a bug in one module of a monolith can crash the entire application, whereas in microservices, a bug in feed service will not affect the user service code. For data consistency, monolith architecture have it easy because you have a single database with ACID transactions. Whereas in microservices architecture, it's much more harder because you're dealing with distributed transactions and eventual consistency. For debugging, monolithic architecture is much more simpler because you have one process and one log. Whereas for microservices, they are much more complex because you need distributed tracing across different services. For team structure, a monolith is one team with a shared code base, whereas the microservices enable separate teams per service. For technology choice, a monolith means one language and one framework, whereas the microservices, it lets you each service use different technology. And for operational cost, monoliths are low because you have one server and one deployment pipeline. Microservices, it's high because you have many servers and orchestration platforms and monitoring tools. Let me ground this in a real example. So for example, Instagram launched in 2010 as a Django monolith written in Python. By 2012, when Facebook acquired them, they had 30 million users and they were still a monolith. Between 2013 and 2016, they gradually decomposed into microservices. And by 2024, they were running hundreds of microservices. The lesson here is clear. You should always start with the monolith, split into microservices only when you have a specific scaling or organizational problem that requires it. Because premature microservices is also one of the common architectural mistakes that people do, so you should also avoid that. So now let's talk about when should you split the monolith. There are 5 signals to watch out for. The first is the team scaling pain, where your teams are having merge conflicts daily and deploys are blocked by other teams. The second is when independent scaling is needed. So for example, when let's say feed generation needs 100 servers, but user authentication only needs 5 servers. The third is the deployment frequency mismatch, where the payment team ships weekly, but the feed team, they need to ship daily. So in that case, you need to split the monolith architecture as well. The fourth signal is different reliability requirements. So for example, media upload can tolerate some downtime, but the feed must always work. So this is also a good case for splitting into microservices. And the fifth signal to watch out for is technology mismatch. So for example, where the ML team needs Python and the API team, they probably prefer Java or Python or like C Sharp. Now let us combine all of this into a clear decision framework that you can apply in interviews and your own projects. You should choose a monolith when you have a small team of under 10 engineers, when you're building a new product with unclear business requirements, or when your domain is simple without many distinct business capabilities. You should also consider monolith when speed of initial delivery matters most and when you do not yet know which components will need independent scaling. You should choose microservices when you have a large team with multiple squads and let's say 20 or more engineers, when you have a well understood domain with clear service boundaries, or when components have very different scaling requirements. Microservices is also ideal, when let's say teams they need to deploy independently and when fault isolation is critical, meaning one component failing must not bring down the entire system. Now, let me walk you through three common interview mistakes related to this topic because these come up pretty often. The first mistake is defaulting to microservices for every design. Candidates in interviews they say something like, "Okay, I will use microservices because they are the industry standard." The problem with that is that most interview questions do not require microservices. A URL shortener server serving let's say 1 million users does not need 5 separate microservices from day one. A better answer in that case would be, let's say candidates should at least say something like this. They should say like, okay, for this scale and complexity, a modular monolith should be sufficient. I would consider splitting it into microservices if the user base goes beyond let's say 100 million users or if the team grows to multiple independent teams. Now the second mistake is not acknowledging trade-offs. Candidates in interviews are like, okay, sometimes they say microservices are always better than monoliths. This actually shows kind of like lack of real world experience because every architecture has its trade-offs. A better answer from a candidate would be something like, okay, microservices they do give us independent scaling and fault isolation, but they do add complexity in service communication, data consistency, and operational overhead. At this scale, the benefit outweighs the cost. So again, it depends using the business case to business case. Now, the third mistake happens in interviews is like, okay, by spreading the technical layer instead of the business capability. The wrong approach would be creating a front-end service, back-end service, database service. However, the right approach would be creating a user service, order service, payment service, notification service. Services should be organized by business domain, not by technical layer. This aligns with Conway's laws as well, which says that system architecture tends to mirror team structure. Now let us wrap up section 3 with summary of everything we covered in this section. We start with server types, which is physical machines, VMs, containers, and serverless. All of them are essentially just computer running software. We then looked at the single server architecture, the simplest setup that works well for under, let's say, 1,000 daily active users. Then we covered the stateful servers that store session data in memory and cannot scale horizontally. And then we moved to the stateless servers that do store state externally in Redis or database, so any server can handle any request. Then we talked about the three server types, which is web servers like Nginx that handle HTTP and serve static files, server application servers like Node.js, that execute business logic, and then database servers like PostgreSQL that store and retrieve persistent data. Then we cover reverse proxies that sit in front of the backends and handle TLS termination, load distribution, and caching. We also covered API gateways that add authentication, rate limiting, routing, and analytics on top of what a reverse proxy does. And then we compared monolithic architecture, a single deployment unit with all features in one code base, against a microservices architecture where independent services each own a specific business capability and their own data. Welcome to section 4, and this is one of the very important sections of this entire course, which is databases. Every system you ever design in an interview or in production will have data stores and databases at its core. Every user account, every post, every transaction, every relationship between entities, they all live in the database. Without databases, it will be very hard to do system design. So in this section, we're going to cover relational databases, also known as SQL databases. We'll walk through schema design, including keys, joins, and indexes. We'll also cover asset properties, which are the guarantees that make relational databases trustworthy for critical operations. Then we'll explore non-relational database, also known as NoSQL databases, and understand the different types. We'll build a decision framework for choosing between SQL and NoSQL, and we'll also cover normalization and denormalization and why production systems deliberately break the rules of normalization. Then we'll finish with replication and sharding, which are the two techniques that allow databases to scale to billions of users. Before we dive any more of that, let's first answer a fundamental question. Why do we need databases in the first place? Why can't we just store data in normal files? At first glance, files seem perfectly reasonable. You could technically store data in JSON file or CSV, and at small scale that might actually even work. But a configuration file or small CSV with a few hundred rows, those are perfectly valid use of those files. However, at the scale of any production system with thousands of concurrent users and millions of rows, files do fall apart pretty quickly. So let me walk you through why. The first problem is finding data. If you need to find a user by their email address in a file, you would have to read the entire file and then search line by line. That is a linear scan. In a database, you create an index and the lookup happens in overflow login time. The second problem is updating data. If you need to update a single field in a file, you would have to rewrite the entire file. In a database, you update a single row in a place. The third problem is concurrent access. If two users try to write to the same file at the same time, you run into file locks and corruption risk. Databases handle this with transactions and isolation levels. The fourth problem is structured queries. With files, you have to write custom parsing code for every query. With a database, you would write SQL, something like, let's say, select all from users, where email equals a value. So they are more specific in that way. The fifth problem is data integrity. Files have no enforcement whatsoever. There is nothing stopping you from inserting bad data. Databases give you constraints, foreign keys, and type enforcement, so it's very hard to put bad data in databases. And the sixth problem is crash recovery. If your stress system crashes while you're writing to a file, you can end up with partial writes and data loss. Databases use write ahead log and provide automatic recovery. So the takeaway here is that files do work for small, simple, single user scenarios, but the moment you're building anything that needs to serve real users at a real scale, a database is not optional. It is a foundation, and now let's look at the most common type of database you will encounter in system design. Okay, now let us talk about relational databases, which are also called SQL databases. These are the workhorses of the software industry and have been there for decades. A relational database organizes the data into tables, which are also called relations. Each table has a fixed schema, meaning a defined set of columns with specific data types, and each row in the table is also a single record. Let me go through the core terminology here. The first is a table, also called relation. A table is a collection of related data organized in rows and columns. For example, a user's table. The second is a row, also called a record or a tuple. A row is a single entry in a table. For example, one user, let's say one row could be a user with ID 123 and name of, let's say, John Doe. The third is a column, also called a field or attribute. A column is a name property with a specific data type. For example, email as a varchar of 2255 characters. And the fourth is schema. The schema is the structured definition of a table, meaning the columns and their data types, and typically defined through a create table statement. And the fifth is a query. A query is a request to read or write data using operations like select, insert, update, and delete. Now you might be wondering which relational databases are actually used in production and which are more popular. Let me walk you through the most popular ones. PostgreSQL is used by companies like Instagram, Uber, Reddit, and Stripe. It is known for being feature-rich, extensible, and having strong standards compliance. MySQL is used by Facebook, Twitter, YouTube, and Shopify. It is mature, high performance, and has a very large community. SQL Server is used by Microsoft and Stack Overflow and is known for its enterprise features and deep window integration. Oracle is used by banks, telecoms, and large enterprises. It is enterprise grade, but it comes with expensive licensing. And SQLite is used in mobile apps and embedded systems. It is serverless, file-based, and requires zero configuration. So when should you reach for a SQL relational database? You should use when your data has clear relationships, like users who have posts and posts that have comments. You should use one when you need transactions with asset guarantees, which we'll cover shortly. And this is especially important for systems involving payments and inventory. You should also use one when you need complex queries with joins and aggregations, and you should definitely use one when your schema is well defined and relatively stable. One important note for system design interviews. So ideally, you should be starting with PostgreSQL should be a default recommendation, and the interview, unless there is a specific reason to choose otherwise, is the most commonly referenced relational database in system design discussions, and it covers a wide ranges of use cases as well. Now let's look at what an actual schema looks like in practice. And this is exactly where schema design comes in. Let us walk through a real example. We're going to design a users table, the kind you see in, let's say, a system like Instagram. The table starts with the user ID column, which is a big int and serves as the primary key with auto increment. Then we have a username as a varchar of 30 characters marked as unique and not null. Then we have a email as a varchar of 255, also unique and not null. And then we have a password hash as a varchar of 255, not null. In addition to that, we have fields like full name as a varchar of 100, bio as text, profile pic URL as a varchar of 500, follower count and following count as integers defaulting to 0. And finally, we also have created at and updated at as timestamp columns that automatically set themselves. Now, every single one of these column choices is a deliberate design decision, and understanding why it matters a lot in interviews. So let me walk you through the key ones. The user ID column is a big int, not an integer. Why? Because big int supports up to 9.2 quintillion rows, which is 2 to the power 63. Integer only supports about 2.1 billion rows, which is 2 to the power 31. Instagram already has 2 billion users, so if you use integer, you would literally run out of IDs for Instagram's use case. The username column is a varchar of 30, which enforces a maximum length constraint at the database level itself, not just in the application code. The email column is a varchar of 255 because that is the RFC standard maximum email length. The password hash column stores a hash password that is the output of something like bcrypt and never plain text. The bio column is text because it has variable length with no practical maximum needed. And the profile pic URL column is a varchar of 500 that stores a URL pointing to an object storage like AWS S3, not the image itself. Now let me highlight 3 common schema mistakes that come up again in interviews. So you want to avoid them when you're doing the system design interviews. The first mistake is using integer for IDs on a large scale system. As I just explained, integer maxes out at about 2.1 billion. So for any system that could reach billions of records, you should always use big int. The second mistake is storing passwords as plain text. You should never have a column called password that stores the raw password. It should always be a password hash using an algorithm like bcrypt or argon2. The third mistake is storing images directly into the database as blobs. Databases are not designed for large binary data. Instead, you should store the URL that points to where the image lives, which is something like an object storage like AWS S3. These 3 mistakes are surprisingly common in interviews, and avoiding them immediately signals that you understand production level schema design. Now that we have a table, let us talk about how rows in different tables relate to each other. Okay, now let us talk about primary keys and foreign keys, which are the mechanisms that give relational databases their power to model relationships between entities. A primary key uniquely identifies every row in the table. No 2 rows can have the same primary key value, and it cannot be null. The simplest form is a single column primary key. In our users table, user ID is a primary key, meaning each user has a unique user ID. But there's also something called a composite primary key, where 2 columns together form the key. A great example is a follows table. In a follows table, you have a follower ID and followee ID, and the primary key is a combination of both. What this means is that the pair of follower ID and followee ID must be unique. User A can follow user B exactly once. The pair A and the B can only exist once in the table. This is an elegant way to enforce business logic at the database level. Now let's talk about foreign keys. A foreign key creates a relationship between two tables. It references the primary key of another table and enforces that the reference row must actually exist. For example, in a post table, the user ID column is a foreign key that references user ID in the users table. This enforces three things. First, every post must belong to a valid user, meaning the user ID must exist in the users table. Second, with on-delete cascade, if the user is deleted, all of their posts are automatically deleted too. And third, you simply cannot insert a post with a user ID of 999 if user ID 999 does not exist in the users table. So why does this matter in system design? So without foreign keys, your application code must manually check if a user exists before creating a post. If a user gets deleted, then the orphan post they will remain in the database forever. And then the data integrity depends entirely on every developer writing correct code, which is fragile and error prone. With foreign keys, the database enforces the relationship automatically. It is impossible to create invalid data regardless of application bugs. And cascading deletes keep the data consistent without any extra application logic. There is an important trade-off, to be aware of, so you should keep that in mind. Some systems at extreme scale, systems processing let's say billions of writes per day, actually disable foreign key checks for performance. When you have that volume of writes, the overhead of checking referential integrity on every single insert becomes significant. In these cases, the application layer handles consistency instead. But this should be understood as a deliberate trade-off at extreme scale, not as a default design choice. Now that we have understood how tables relate to each other through keys, let us now look at how we actually query across these relationships. And this is exactly where joins come in. Joins are the core strength of relational databases. They allow you to combine rows from two or more tables based on a related column, all in a single operation. Let me walk you through the main join types. The first is an inner join. An inner join returns only the rows that have a match in both tables. So if you join the users table with the post table on user ID, the result includes only users who have posts. Any user with no post is excluded from the result. The second is a left join. A left join returns all the rows from the left table and matched rows from the right table. If there is no match, the right side comes back as null. So if you left join users to post, you get all the users even though who have never posted. For users with no post, the caption column just shows null. The third is a right join, which is the mirror image. It returns all rows from the right table with matched rows from the left. In practice, right joins are less commonly used because you can usually rewrite them as left joins by swapping the table order. And the fourth is the full outer join, which returns all rows from both tables with nulls wherever there is no match on either side. Now let me make this a concrete with an example. Now imagine a users table with three users, Alice with ID 1, Bob with ID 2, and Carol with ID 3. And a post table with three posts, post 10 and 11 belong to Alice, which is user ID 1, and post 12 belongs to Bob, which is user ID 2. Carol right now has no posts. If you do an inner join, you get three rows, Alice with hello, Alice with world, and Bob with hi. Carol is excluded because she has no posts. If you do a left join, you get four rows, the same three as before, plus Carol with null for the caption. Carol is included because left join, you keep all rows from the left table even when there is no match in the right table. The distinction between inner join and left join comes up constantly in system design, so understanding it well is pretty important. Now let us see how joins work in real production scenario. So now let us build something real. We are going to construct the SQL query that generates an example Instagram feed. To build a user's feed, we need to combine data from multiple tables, who they follow, what those users posted, and whether the current user has liked each post. I'll walk through this query step by step. Query starts by looking at the follows table, filtered to the follower ID equals to 1 to 3, This gives us all the users that user 123 follows. Then we inner join to the post table matching on the followee ID equals to the user ID. This gives us all the posts from users that user 123 follows. Then we inner join again to the users table matching on the post user ID. This gives us the author's username and profile picture for each post. Then we left join to the likes table matching on both the post ID and user ID 123. This checks whether the user 123 has liked each post. Then we use the left join here, not an inner join, because both posts will not have been liked by this user and we still want to include them in the feed. Finally, we order by created at descending so that to get the newest post first and then limit it to 20 results. The output of this query gives us everything we need to render a feed: the post content, the author information, and a boolean flag for whether the current user has liked each post. Now here's a critical performance concern. This query touches 4 tables and joins across potentially millions of rows. Without proper indexes, this query would take seconds to return. With proper indexes, and we are going to cover indexing in detail next, it will run in milliseconds. This is why indexing is not optional. It is the difference between a usable application and one that times out. So let us dive deeper into indexing. Okay, now let us talk about database indexing, which is one of the very important concepts for system design. An index is a data structure that the database maintains alongside the table to speed up lookups. Without an index, the database must scan every single row in the table to find matching records. This will be called a full table scan. With an index, the database can jump directly to the relevant rows, so that's why indexing is super important. Let me give you an analogy. Imagine a textbook that has 500 pages. You would want to find every mention of the word TCP. Without an index, you would have to read all 500 pages and note every mention. The time is proportional to the total number of pages, which is O of n. But if you use an index, you can flip to the back of the book index and look up the word TCP, and it will tell you exactly which pages to go to. For example, pages 34, 89, 156, and 312. So to find the word TCP now, you can just go directly to those pages. The time is proportional to the logarithm of the total pages, which is O of log n. So that is the difference an index makes. Now let me show you what this looks like with real SQL. Without an index, if you run a select query on users table filtering by email, the database reads all the rows. For a platform like Instagram with 2 billion users, that will take like a really long time. But if you create an index on the email column with, let's say, the create index command, idx_email on users in bracket email, the same query now will uses an index lookup and can complete in as less than 1 millisecond. That is the difference between a query that times out and then one that feels instant. Now there are different types of indexes as well, and you should know the main ones. And the first is a B tree, which is a default index type. It uses a balanced tree structure and works well for both equality and range queries, meaning queries that use equals, less than, greater than, or between. The second is a hash index, which uses a hash table and is optimized only for exact equality lookups. The third is GIN, which stands for Generalized Inverted Index, and it is used for full text search and array columns. And the fourth is GIST, which stands for Generalized Search Tree and is used for geospatial queries with post-GIS. For system design interviews, B-tree indexes cover 95% of the use cases. Unless you're specifically designing a geospatial or full text search system, B-tree should be your default. Now let us look at how a B-tree actually works under the hood. Now that we know what indexes do, let us understand how a B-tree actually works, because this will give you intuition for why indexes are so powerful. A B-tree is a balanced tree data structure where each node can have multiple children. The database keeps the tree balanced so that every lookup takes the same number of steps, regardless of which value you are searching for. Let me walk you through a lookup. Imagine we have a B-tree index on user ID. The root node contains the value 500. Below that, there will be a left child has 200 and the right child has 800. Each of those has further children, all the way down to the leaf nodes, which contain pointers to the actual rows on disk. We want to find user ID 700. Step 1 would be we start at the root node, which has value 500. 700 is greater than 500, so we go right. Then for step 2, we reach the node with value 800. Now 700 is less than 800, so then we go left. For step 3, we reach the node with value 600, and now step 700 is greater than 600, so now we go right. And for step 4, we reach the leaf node with the value 700, so that's where we have found it. We follow the pointer to the actual row, so the total steps now we have taken is number like 4, and that is regardless of how many rows there are in the table. The scaling properties here are remarkable. So with a B tree that has a branching factor of 100, a table with 1000 rows need only 2 levels, and the lookup tables take less than 0.1 milliseconds. A table with 1 million rows needs only 3 levels, and the lookup takes less than 0.5 milliseconds. And a table with 1 billion rows needs only 5 levels, and that lookup just takes less than 1 millisecond. Even with 1 billion rows, a B-tree index lookup touches only 5 nodes. Each node is on one disk read. Compare that to a full table scan of 1 billion rows, which would have required millions of disk reads. There is one more concept worth understanding here: composite indexes. A composite index is an index on multiple columns. For example, you could create an index on post with the columns user ID and create it in descending order. This single index efficiently serves a query like, let's say, get all posts by user 1 to 3 ordered by most recent. The index first narrows to user ID 1 to 3, and then the results are already sorted by created at descending. No additional sorting step will be required here. Composite indexes follow what is called a leftmost prefix rule. An index on columns A, B, and C can serve queries filtering on A, or A and B, or A and B and C. But it cannot serve queries filtering on B alone or C alone. The leftmost column must always be present in this query. So now let us look at the real performance numbers to understand just how dramatic the impact of indexes can be. Now let me put some concrete numbers on the impact of indexing, because the difference is not incremental. It's orders of magnitude. Finding a user by email in a table with 2 billion rows takes about 30 seconds without an index. With an index, it takes less than 1 millisecond. This is a 30,000 times improvement. Finding post by user ID in a table with 10 billion rows takes about 90 seconds without an index and less than 1 millisecond with an index. Again, that is a 90,000 times improvement. Finding likes on a post in a table with 50 billion rows takes about 180 seconds without an index and less than 1 millisecond with if you have indexing applied. Again, that is roughly around 180,000 times improvement. These are the kind of performance differences that determine whether your application loads in under a second or it will time out due to not having indexes. Now, how do you actually verify whether a query is using an index? In PostgreSQL, you use the explain analyze command before your query. Without an index, the output will show a sequential scan, meaning a full table scan, and you will see actual times in the range of tens of seconds. With an index, the output will show an index scan, and the actual time will be fractions of millisecond. Here is an important system design interview tip. When you design a database schema in an interview, always mention which indexes you would create and why. A schema without indexes is incomplete. For each table, identify the most common query patterns and create indexes to serve those patterns. This shows the interviewer that you think about performance, not just the correctness. But again, indexes are not free, and this is exactly what we need to talk about next. So we have established that the indexes dramatically speed up the reads, but there is a cost. Every index must be updated whenever data is inserted, updated, or deleted. This means the indexes speed up reads, but they do slow down the writes. Let me make this concrete. When you insert a new post into the post table without any indexes, that is one write operation, just inserting the row into the table. But if you have 3 indexes on that table, it becomes 4 write operations, inserting the row plus updating each of the 3 index structures. Each index adds roughly 10 to 30% overhead to write operations. So 3 indexes means approximately 30 to 90% slower writes. Now whether this matters depends on your specific business use case and entirely on your system's read to write ratio. For a social media feed like Instagram, the ratio is about 100 to 1, meaning reads heavily dominate the write operations. In this case, you should create as many as indexes as possible because the massive read performance gains far outweigh the relatively small write overhead. For a logging or analytics pipeline, the ratio is about 1 to 100, meaning writes, they heavily dominate the reads. Here you should have few or no indexes because bulk inserts are the priority and you do not want anything slowing them down. For an e-commerce platforms like Amazon, the ratio is about 10 to 1, which is pretty mixed. You should create selective indexes on the critical query paths but not index everything. And for chat application like WhatsApp, the ratio is about 1 to 1, so which is more balanced. You should use moderate indexes and carefully balance read and write performance. So the general guidelines are index columns that appear in where clauses for filtering, in join conditions for combining tables, in order by clauses for sorting, and in frequently accessed lookups like finding a user by email. Do not index columns that are rarely used in queries, like columns with very low cardinality like booleans that only have true or false, tables that are almost exclusively write heavy like logs and events, and do not index every column just because just to be safe, because that wastes storage and degrades the write performance. The key takeaway is that indexing is not about creating as many as indexes as possible. It is about understanding your access patterns and creating indexes that match those access patterns. Now let us talk about the guarantees that make relational databases trustworthy for critical operations. Okay, now let us talk about asset properties. Asset is a set of 4 guarantees that relational databases provides for transactions, and understanding asset is essential for system design interviews because it is one of the strongest arguments for choosing a relational database. First, let me define what a transaction is. A transaction is a group of operations that must succeed or fail as a single unit. You cannot have a half a transaction complete and other half fail. For transactions, it's all for nothing. The 4 properties are atomicity, consistency, isolation, and durability. Atomicity guarantees that all operations in the transaction succeed or none of them do. And if any operation fails, everything is rolled back. Consistency guarantees that the database moves from one valid state to another valid state. Every constraint and rule you have defined is maintained. Isolation guarantees that concurrent transactions do not interfere with each other. One transaction cannot see the partial results of another. And durability guarantees that once a transaction is committed, it survives crashes and power failures. That data is permanently saved. So now, why do these asset guarantees matter? Now, consider a bank transfer. You need to deduct money from account A and add it to account B. These two operations must happen together. If the system crashes between these two operations without asset guarantees, money either would disappear from the system or just gets duplicated. Neither outcome is acceptable. Asset properties are is actually what is preventing this. So let us walk through that exactly how that happens. Now let me walk through a concrete example of asset in action. We are going to transfer $500 from account A, which has a balance of $1,000, to account B, which has a balance of $200. The SQL for this is pretty straightforward. We begin a transaction, update account sales balance by subtracting 500, so it goes from $1,000 to $500, and then we update accounts B balance by adding 500, so it goes from $200 to $700, and then we commit. Now let us see how each asset property protects this transfer. So atomicity, imagine the server crashes after deducting from account A but before adding to account B. Without atomicity, account A will lose the $500 and account B will get nothing. Money has essentially vanished from the system. With atomicity, the entire transaction is rolled back, so account A still has $1,000 and account B still has $200. Nothing has changed, and the data is still safe. Now for consistency, for our business rule says that the total money in the system must remain constant at $1,200. Before the transfer A, account A has $1,000 plus B has account $200, which equals to $1,200. But after the transfer, A will have $500 and B will have $700, which still should equal to the $1,200. If any constraint would be violated, the transaction is rejected entirely. Now let's talk about isolation. While this transfer is running, another transaction tries to read account A's balance. Without isolation, it could read $500, which is the mid-transaction value, or $1,000, which is the pre-transaction value. The result is unpredictable. With isolation, it reads either $1,000 if the read happens before the commit, or $500 if the read happens after the commit. It never sees a partial or intermediate state. Now let's talk about durability. The transaction commits successfully at exactly, let's say, 10 a.m. The server crashes at, let's say, 1 second later, and when the server restarts, account A has a balance of $500 and account B has $700. The committed data is preserved, and this is implemented through what is called a write ahead log, or WAL. The database writes every change to a log file before applying it to the actual data files. On crash recovery, it replaces the log to restore the committed state. Now here's an important interview tip. When an interviewer asks why you would, let's say, choose SQL or NoSQL, asset compliance is a strong reason for any system involving money, inventory, or critical business transactions. If the system can tolerate occasional inconsistency like social media feeds or analytics, then NoSQL becomes a viable option. And this is exactly what we're going to cover next. Okay, now let us talk about the other side of the database world, which is the NoSQL databases. NoSQL databases are a broad category of databases that do not use the traditional relational table model. They trade some of the SQL guarantees, things like joins, full asset compliance, and rigid schemas, for advantages in specific use cases. Those advantages include higher write throughput, flexible schemas, easier horizontal scaling, or optimized access patterns. Now, one more important clarification. NoSQL does not mean NoSQL, it stands for not only SQL. These databases are not replacement for SQL, they are specialized tools for specific data patterns where relational model is either insufficient or unnecessarily complex. There are four main types of NoSQL databases. The first is the key value stores, which use simple key to value pairs. Examples for that would include Redis, DynamoDB, and Memcached, and they are the best for caching, sessions, and simple lookups. The second is the document stores, which use JSON or BSON documents. Examples for that would include MongoDB, CouchDB, and Firestore, and they are the best for flexible schemas and nested data. The third is wide column stores, which have rows with dynamic columns. So examples for that would include Cassandra, HBase, ScalaDB, and they are best for write-heavy workloads, time series data, and IoT. And the fourth is graph databases, which model data as nodes and edges. So examples for that would include Neo4j, Amazon Neptune, and ArangoDB, and they are best for relationship-heavy data like social networks. Each type is optimized for a different access pattern, and the next few slides will cover the three types most commonly referenced in system design interviews. So let's start with the first one. Now, key value stores are the simplest data model of all. You store a value under a key and you retrieve the value by that key. Think of it as a hash map that either persists to disk or lives entirely in memory. The operations are as simple as it gets. So you use a set operation like a key, like let's say user :123 session with the JSON value containing the session data. You get the same key and the value comes back. You can set a key like let's say rate limit a user :123 post with an integer value of 8, and then you can delete the key and to remove it. The performance numbers here are pretty remarkable. Redis, which is an in-memory key value store, has get and set latency of about 0.1 to 0.5 milliseconds and throughput of 100K to 500K operations per second on a single node. The data is stored in RAM, which makes it fast with optional disk persistence for durability. DynamoDB, which is a persistent key value store from AWS, has get and set latency of about 1 to 5 milliseconds and virtually unlimited throughput because of auto scaling. The data is stored on SSDs with built-in replication. Now let me walk you through the most common use cases you'll encounter in system design. The first is session storage. The key pattern is something like, let's say, session colon, followed by the session ID. The value is user session data in JSON, and you set a TTL of 30 minutes so session expire automatically. The second is caching. The key pattern here is something like cache colon user colon, followed by the user ID, and the value is the user profile as JSON, and you set a TTL of 5 minutes to keep the cache fresh. The third is rate limiting. The key pattern is rate limit colon followed by the user ID and the endpoint. The value is a request count of as an integer and you set a TTL of 1 hour. The fourth is feed caching. So the key will be something like feed colon followed by the user ID. The value is a list of post IDs with a 5-minute TTL. And the fifth is leaderboards. The key will be something like leaderboard colon global and the value is a sorted set of scores and there is no TTL because leaderboards should be persistent. Now the limitations of key value stores should be clear from this model. There are essentially no joins and you cannot query across keys. There are no complex queries since you can only look up by exact key and there are no relationships between records and your query patterns are limited, so you need to design your key structure carefully upfront. The takeaway is that key value stores are incredibly fast for what they do, but what they do is intentionally narrow. They are the right tool when your access pattern is simple key-based lookups. So now let's look at the slightly more flexible NoSQL model. Now let us talk about the document stores, with MongoDB being the most well-known example. A document store organizes data as a collection of JSON-like documents. Each document can have a different structure, and documents can contain nested objects and arrays. This is fundamentally different from a relational database where every row in a table must conform to the same schema. Let me walk you through an example where what a document looks like. A user document in a collection might have an underscore ID field of, let's say, user123, a username, an email, and then a full nested profile object containing full name, bio, and location. It could also have an interest array with values like system design, distributed systems, and machine learning, and a follower count field. Notice how the profile is nested inside the documents as an object and interest is an array. In a relational database, you would need separate tables and joins for this. In a document store, everything lives in one document. Similarly, a post document might contain the post ID, author ID, caption, and then a nested media object with the type, URL, and nested thumbnails object with small and medium versions. It could also have a tags array and an embedded comments array where each comment is its own nested object with user ID, text, and timestamp. Advantages of this model for certain use cases are clear. The first is flexible schema. Different documents in the same collection can have different fields. The second is nested data. You can embed related data inside the document, eliminating the need for joins. The third is schema evolution. You can add new fields without running alter table migrations. And the fourth is document structure, which maps naturally to JSON APIs since the document format is essentially the same as API response format. Document stores work well for content management systems where particles have varying metadata, product catalogs where each product has different attributes, user profiles with dynamic fields, and prototyping where the schema changes frequently during the rapid iteration. However, the document DBs they do not work well when your data has many relationships because joins either do not exist or are very expensive. They struggle with transactions across multiple documents as they have limited asset support, and they are not ideal for reporting analytics with complex aggregations. The key insight here is that document stores trade the relational power for flexibility. If your data naturally fits into self-contained documents without many cross-references, a document store can be an excellent choice. Now let us look at a NoSQL type designed for a very different problem. Now let us talk about wide column stores, with Cassandra being the most prominent example. Wide column stores are designed for one thing above all is massive write throughput with predictable performance at scale. A wide column store organizes data by partition key and clustering columns. Each row can have a different set of columns. Data is distributed across nodes by partition key, which makes horizontal scaling straightforward. Let me describe the data model. Imagine you have a partition key of user ID and a cluster key of created at in descending order. All the data for user 1 to 3 now lives together in one partition, and their posts sorted by created at, with each row having a post ID and caption. User 456 data now lives in a separate partition with their own posts sorted the same way. The key insight is that data within a partition is co-located and sorted by the clustering key, which makes queries within a partition extremely efficient. Now let me walk through the key characteristics. Write throughput is extremely high, in the range of 100,000 to 1 million writes per second per cluster. Read performance is fast when you query by partition key, but slow for ad hoc queries that do not use a partition key. Scaling is linear and horizontal, so you add more nodes and capacity increases proportionally. Consistency is tunable, meaning you can choose between levels like 1, quorum, and all depending on your needs. Joins are not supported, and transactions are limited to lightweight transactions only. Now, wide column stores work well for time series data like IoT sensor readings and application metrics. Write heavy workloads like logging and event tracking, analytics ingestion, and data that is naturally partitioned by user, device, or tenant, and systems requiring predictable performance at massive scale. The real-world usage is pretty impressive. Netflix uses Cassandra to store viewing history, processing billions of events per day. Discord uses it to store the chat messages partitioned by channel ID and clustered by timestamp. And Apple stores over 10 petabytes of data in Cassandra. So takeaway is that wide column stores are the go-to choice when your primary concern is handling extreme write volumes with linear scalability. Now let us step back and build a comprehensive framework for choosing between SQL and NoSQL. Now that we understand both SQL and the major NoSQL types, let us put them side by side and compare them across the dimensions that matter in system design interviews. Starting with the data model, SQL uses fixed schemas with tables organized in rows and columns. NoSQL is flexible and varies by type, key value, document, wide column, or graph. For query language, SQL uses a standardized SQL language. NoSQL databases each have their own database-specific APIs and query languages. For schema, SQL is pretty rigid and defined upfront, and changes require alter table statements. NoSQL is pretty flexible with what is called a schema on read, meaning the schema is interpreted when the data is read rather than enforced when the data is written. For joins, SQL has native support and handles them pretty efficiently. NoSQL either does not support joins or has very limited support. For transactions, SQL provides full asset support, whereas the NoSQL varies, with some databases supporting single document asset, but most offer, weaker guarantees. For the scaling model, SQL scales primarily vertically with manual sharding when you need horizontal scaling. NoSQL databases were designed for horizontal scaling from the start. For consistency, SQL provides strong consistency by default. NoSQL is often eventually consistent, though this is usually tunable. For relationships, SQL treats them as first-class citizens through foreign keys and joins, whereas in NoSQL, relationships must be handled in application code. And for ecosystem maturity, SQL has been there for decades, and there's been a lot of tooling, optimization, and accumulated expertise, whereas NoSQL is still pretty newer with less standardized tooling. So this comparison gives you the landscape, but does not tell you which to choose for a given system. So this is what the decision framework is for, and that we'll cover just next. So how do you actually decide between SQL and NoSQL in a system design interview? Let me give you a clear decision framework. Choose SQL when your data is relational, meaning entities like users, orders, products, and payments that have clear relationships to each other. Choose SQL when you need asset transactions, which is essential for financial systems and inventory management. You should choose SQL when you need the complex queries with joins and aggregations, and you should also choose SQL when data integrity is critical and you need constraints and foreign keys enforced at the database level. Choosing SQL is also ideal when your schema is well defined and it does not change frequently. Now let us talk about NoSQL. You should choose NoSQL when your data access patterns are simple and based on key lookups, or when your write throughput requirements are extreme, let's say in the range of 100K or more writes per second. Also, you should choose NoSQL when your schema evolves frequently or varies between records, or when your data is naturally denormalized, meaning self-contained documents that do not need cross-references. You should also consider NoSQL when you need horizontal scaling without the complexity of manual sharding. Now let me map this to real systems so you can see how this framework applies in practice. For Instagram, which deals with posts, users, and follows, the recommendation is PostgreSQL because the data is relational and you need complex joins for feed generation. For shopping cart, the recommendation is Redis because it's temporary data that needs fast access and can expire with the TTL. For chat messages like WhatsApp, the recommendation is Cassandra because it is write heavy and naturally partitioned by a conversation. For product catalog like Amazon, the recommendation is ideally sometimes with MongoDB combined with SQL because products have varying attributes per category. For social graph like Facebook, the recommendation is a graph database like Neo4j because the relationship traversal is a primary operation. For session storage, the recommendation is Redis because sessions are short-lived, need high throughput, and benefit from being in memory. And for analytics, the recommendation is Cassandra or ClickHouse because it is write heavy, time series, and append only. The pattern you should notice here is that the most production systems use multiple database types. The question in the interview is not SQL or NoSQL, it is actually which database for which part of the system. But there are some common misconceptions about this choice and let's clear them up as well. So let me address the 4 most common misconceptions about SQL versus NoSQL because getting these wrong in an interview can really hurt your chances. The first misconception is that NoSQL is faster than SQL. The reality is that speed depends on access pattern, not the database type. For a key lookup, where Redis is about 0.1 milliseconds is faster than PostgreSQL at about 1 millisecond. But for a complex join across 4 tables, PostgreSQL handles it while MongoDB simply cannot. Neither is universally faster, so it is about using the right tool for the right job. Now the second misconception is that NoSQL scales better than SQL. Well, the reality is that NoSQL databases were designed for horizontal scaling from the start, which means the operational effort to scale them is lower. But SQL databases can absolutely reach the same scale through sharding. With Cassandra, you add a node and it auto rebalances, which is pretty simple. With PostgreSQL, you set up sharding logic and a shard router and manage cross-shard queries, which is much more complex. Both can reach the same scale, it's just that the operational effort differs. The third misconception is that you should pick one or the other. The reality is that in most production systems, you actually use both. Instagram uses PostgreSQL for relation data like users, posts, and follows. They use Redis for caching, including feed caches and session stores. And they also use Cassandra for high volume writes like analytic events. The pattern using multiple data types together is called polyglot persistence, and it is the standard approach in modern system design. And the fourth misconception is that NoSQL means no schema, but the reality is that NoSQL means no schema enforced by the database. Your application's code actually still needs to understand the data structure, so the schema just moves from database level enforcement to application level enforcement. This can be a benefit because it gives you more flexibility, but can also be a risk if your application code has bugs that introduce inconsistent data. The key interview tip is that never say that okay, I will use NoSQL because it is more modern, or the SQL is not it's kind of like outdated. Those are not valid answers in interviews. You should frame your choice around specific access patterns, consistency requirements, and scaling needs. You should show that you understand the trade-offs, not just the buzzwords. Now let us shift to a different but equally important topic, which is how do you organize your data within a database? Talk about normalization. So normalization is a process of organizing a database schema to reduce data redundancy and prevent update anomalies. The fundamental goal is to store each piece of information exactly once. Let me show you why this matters with a concrete example. Imagine now you have a flat denormalized table called orders flat. Each rows contain the order ID, customer name, customer email, product name, product price, and quantity, all in one table. So you might have order 1 for Alice with Alice at example.com buying a laptop for let's say $999. Then for order 2 For Alice again, same email, buying a mouse for $29, and then for order 3 for Bob, buying a laptop for less than $999. This design has serious problems. Alice's email is stored twice. If she changes her email, you would have to find and update both rows, and if you miss one, the data is now inconsistent. The laptop price of $999 is also stored twice. If the price changes, you would have to find every row that contains it. And if Alice's only order gets deleted, her customer information is lost entirely because it's only existed as part of the order row. Normalization solves all of these problems through a set of rules called normal forms. The first normal form, or 1NF, says each column should contain a single value with no arrays and no nested data. This eliminates the repeating groups. So in the second normal form, which is 2NF, says that every non-key column should depend on the entire primary key. This eliminates the partial dependencies. And the third normal form, which is 3NF, says that every non-key column should depend only on the primary key with no transitive dependencies. In practice, what a normalized design looks like is 3 separate tables. A customers table where each customer data is stored once, and with the customer ID, name, and email. A products table where each product's data is stored once with the product ID, name, and price. And then an orders table where that contains only the relationships and the order specific data with an order ID, customer ID as a foreign key, and product ID as a foreign key as well, and quantity and timestamp. Now, Alice's email exists in exactly one row. Updating it means updating one row, not hunting down through the entire database. This is clean, correct, and maintainable. But as we see next, sometimes production systems deliberately break these rules for good reasons. So let's cover that in the next slide. And this is exactly where denormalization comes in. Denormalization is a deliberate introduction of redundancy into a database schema to improve read performance. It is the opposite of normalization, and it's a trade-off. You accept duplicate data and increase storage in exchange for faster queries. Now let me show you why you would do this. Imagine you would want to answer a simple question, which is how many followers does user ID 123 have? With a normalized schema, you would run select count from follows, where follower ID is equal to 123. If user 123 has 10 million followers, this query scans 10 million rows. Even with an index running count over millions of rows, that will take hundreds of milliseconds. On a profile page that gets loaded millions of times per day, this is pretty unacceptable. The denormalized approach is to store the count directly in the users table as a follower count column. Now the query is actually just select follower count from users where user ID equals to 123. That is a single row lookup less than 1 millisecond. And this count is pre-computed and stored redundantly. Now this pattern is used extensively in production. Follower count is stored in the users table and incremented or decremented on every follow or unfollow. Like count is stored in the post table and updated on every like or unlike. Comment count is stored in the post table and updated on every comment creation or deletion. Post count is stored in the users table, and even things like author name are sometimes duplicated in the post table or cached so that the rendering of feed does not require an extra join back to the users table. So the key insight is that denormalization is not a sloppy design. It's a deliberate trade-off made after you understand the access patterns and determine that read performance is more important than write simplicity. Now let us look at the trade-offs in detail. Now let me lay out the trade-offs between normalization and denormalization side by side because understanding when to use each is very important for the interviews. For data redundancy, normalization has none because each fact is stored once. Denormalization has intentional redundancy with the same data in multiple places. For write complexity, normalization is simple because you update one place. Denormalization is complex because you have to update multiple places and keep them in sync. For read performance, normalization is slower because it requires joins or aggregation, whereas denormalization is faster because values are pre-computed and available with a single lookup. For storage, normalization uses less, whereas denormalization uses more. For data consistency, normalization guarantees it through the schema, but denormalization consistency must be maintained by the application code. And normalization is best for write-heavy or mixed workloads, while the denormalization is best for read-heavy workloads. Now let me address the consistency challenge that comes with denormalization. Now imagine the scenario. Let's say user A follows user B, so we need to increment users B's follower count. But the application crashes after inserting the row into the follows table, but before incrementing the follower count. Now the follower count shows 999, but the actual number of followers is 1000. So the data has now become inconsistent. Now there are three solutions to this. The first is wrapping both operations in a database transaction, which guarantees atmosity. The second is running an async reconciliation job that periodically recalculates the actual counts from the source of truth table. And the third is simply accepting eventual consistency, knowing the count will be corrected on the next event. Most production systems they use the third approach with the periodic reconciliation as a safety net. So Instagram's follower count is eventually consistent. If you gain a follower, the count might take a few seconds to update. That is acceptable because the exact real-time counts are not really critical for a social media platform. Now here is the system design interview approach that I would recommend. Start with a normalized schema because that shows you understand proper database design. Then identify specific columns that should be denormalized for performance. And then explain the trade-off explicitly. So that for example, you can say I would denormalize follower count into the users table to avoid a count over 1,000,000 rows. The trade-off is that the count may be slightly stale, which is acceptable for a social media platform. That demonstrates the mature engineering thinking. Now let us move to on how databases they handle scale beyond a single machine, starting with replication. Let us talk about database replication, which is one of the two fundamental techniques for scaling databases beyond a single machine. The other is sharding, which we'll cover after this. Replication creates copies of a database on multiple servers. It serves two primary purposes. The first is increased read throughput. So if you distribute reads across multiple copies so that no single server is a bottleneck. The second is fault tolerance. If one server dies, then the copies survive and the system will keep running. Now let me show you why replication is necessary. A single database server can handle roughly 10,000 read queries per second. Instagram's read load is approximately 100,000 queries per second. That's 10 times the gap. A single server simply cannot keep up. Beyond throughput, a single server is also a single point of failure. If it crashes, the entire application will go down. If the disk fails, data is lost as well. No redundancy means unacceptable risk for any production system. Now let me quickly define the key terminology here. The primary, also called the master, is a database that accepts the write operations. A replica, also called a read replica, is a copy that receives data from the primary and serves read queries. Replication lag is a time delay between when a write occurs on the primary and when that data appears on the replica. The WAL or write ahead log is a log of all changes that the primary uses to replicate data to the replicas. And failover is the process of promoting a replica to become the new primary when the current primary fails. Now let us look at how the architecture works in practice. Common replication setup is called primary replica replication. The architecture works like this. You have one primary database and multiple replicas. All write operations, meaning insert, update, and delete, go to the primary. All read operations, meaning select queries, are distributed across the replicas. Let me walk you through the write path. First, the application sends an insert, update, or delete to the primary. The primary executes the query. Then the primary writes the change to the write ahead log. Then the primary sends the WAL entries to all replicas asynchronously. And finally, each replica applies those changes to its own local copy of data. The read path is pretty simpler. The application sends a select query to one of the replicas, typically chosen by the round robin. The replica executes the query against its local copy and returns the result. In terms of read distribution, the primary handles all writes plus roughly 10% of the reads, specifically for cases where you need read after write consistency, which we'll explain next. Each of the three replicas handle about 30% of the remaining reads. This gives you a total read capacity of approximately 4 times what a single database can provide. Now, a typical per shard configuration is one primary and 3 read replicas. The write capacity is up to 10,000 writes per second handled by the primary only. The read capacity is up to 40,000 reads per second, distributed across the primary and 3 replicas. The cost is 4 database instances per shard at roughly $500 per month per instance, so about $2,000 per month per shard. The architecture solves the read throughput problem, but there is a subtle consistency issue that arises from asynchronous replication, and you need to understand it for interviews. So let's cover that in the next slide. Now, replication is asynchronous. That means there is a delay, typically 100 to 500 milliseconds between when a write occurs on the primary and when it appears on the replicas. This creates a real consistency problem that you need to be able to explain in interviews. Now, let me walk you through the scenario. At time 0 milliseconds, a user creates a post. The write goes through the primary. At times 50 milliseconds, the user refreshes their profile page. Then the read goes through replica 2 at time 200 milliseconds. The primary then sends the replication data to replica 2. But at the time 550 milliseconds, when the user refreshed, replica 2 did not have the new post yet. So the user just created a post but does not see it on their profile. They could feel like, okay, this might be a bug, even though the system is technically working correctly. The solution is a pattern called read after write consistency. And here how it works. When a user creates a post, you write to the primary as usual, but you also set a flag in the cache, something like recent underscore write : followed by the user ID with a TTL of 5 seconds. Then when fetching the user's post, you first check the cache for that flag. If the flag exists, means the user wrote something in last 5 seconds, you read from the primary, which is guaranteed to have the latest data. If the flag does not yet exist, read from a replica as usual. The key insight here is pretty powerful. You only need strong consistency for the user who just wrote. Every other user can read from replicas with eventual consistency and they will never notice the lag. A user checking their friend's profile 200 milliseconds after a friend posted will not notice about the slight delay. But a user who just clicked post and does not see their own content will think, okay, the app might be broken. Now there are 3 types of replication to be aware of. Asynchronous replication has a lag of 100 to 500 milliseconds and provides eventual consistency. The write performance is fast because the primary does not wait for replicas. This is the default for most systems. Synchronous replication has zero lag and provides strong consistency, but write performance is slow because the primary waits for all replicas to confirm before acknowledging the write. This is used for financial systems where consistency is non-negotiable. And semi-synchronous replication is a compromise where the primary waits for just one replica to confirm, giving near zero lag with moderate write performance impact. Now we have covered how to scale reads replication, but what about when a single database cannot hold all the data, or when write throughput becomes a bottleneck? This is where the sharding comes in. Okay, now let us talk about database sharding, which is the technique that enables databases to scale horizontally to handle truly massive data volumes and write loads. Sharding splits a single large database into multiple smaller databases called shards. Each shard holds a subset of the total data. Instead of one massive machine trying on to hold everything, you use many smaller machines, each responsible for a portion of the data. So why do we need sharding? A single PostgreSQL instance has practical limits. Storage capacity is roughly 10 to 16 terabytes. Write throughput is roughly 10,000 writes per second, and the connection limit is about 5,000 concurrent connections. Instagram generates roughly 36 terabytes of metadata per year, and that is growing each year. So historical data accumulates over time. And 500 million daily active users are all generating the queries simultaneously. A single database simply just cannot handle or serve all the data. So let me walk you through how sharding works, and then we can dive more deep into it. So now you have a shard router that sits between the application server and the shards. The router uses a function to determine which shard a particular piece of data belongs to. For example, with 4 shards, the formula might be shard ID equals user ID modulo 4. So user 0, 4, 8, and 12, they will all go to shard 0. And then user 1, 5, 9, and 13 will go to shard 1. And just like that, user 2, 6, 10, and 14 will go to shard 2, and so on. The critical decision in any sharding strategy is the shard key. The shard key is a column used to determine which shard a record belongs to. The formula is shard ID equals the hash of the shard key modulo the number of shards. For example, with user ID as a shard key and 4 shards, user 12345 maps to shard 1 because 12345 mod 4 equals 1. Then user 67890 maps to shard 2 and user 99999 maps to shard 3. Choosing the right shard key is the most important decision you will make in a sharding strategy. So now let's look at two most common approaches. So there are two main sharding strategies, hash-based and range-based. Let me walk you through each one. Hash-based strategy uses the formula shard ID equals hash of user ID modulo number of shards. The advantages are the data distribution is even because the hash functions spread data uniformly. It is simple to implement and there are no hotspots from sequential IDs. The disadvantages are that range queries become pretty expensive. So a query like find all users created in January has to hit every single shard because there is no way to know which shards contain users from January. And resharding is complex because changing the shard count moves the most of the data. Now range-based sharding assigns ranges of the shard key to each shard. Shard 0 handles user ID 1 through let's say 1 million. Shard 1 handles user ID 1,000,001 through 2 million and so on. The advantages are that the range queries are now much more efficient. So query like find users 500,000 through 600,000 that will go to shard 0 only. It is also simple to understand, but the disadvantages are that the data distribution can be very uneven. All new users will go to the latest shard, creating an imbalance. Hotspots are pretty common. For example, if a celebrity happens to be in shard 0, it gets disproportionate load, and you would need to manually rebalance when the shards become uneven. Now let me compare them across the key criteria. For data distribution, hash-based is even, while range-based can be uneven. For range queries, hash-based is expensive because it hits all the shards, while range-based is efficient because it hits a single shard. For hotspots, hash-based rarely has them while range-based commonly does. For resharding, hash-based is complex while range-based is simpler because you can just split a range. And for implementation complexity, hash-based is moderate while range-based is simple. So which should you choose? Hash-based is the default for most systems. Instagram, Discord, and Uber all use hash-based sharding. Range-based works well for time series data like logs, partitioned by date range. In system design interviews, hash-based by user ID should be your safe default choice unless there is a specific reason to do otherwise. Let us now work through a complete sharding example at real scale to see how all of that fits together. Now let me walk through the sharding at Instagram scale with real numbers because this is exactly the kind of analysis you would want to display in interviews. We start with the given parameters. Let's say Instagram has 2 billion users that generate 36 terabytes of metadata per year, handles 100,000 read queries per second and 1,000 write queries per second as well. Now here's the shard configuration. We use 1000 shards. The shard key is user ID mod 1000, so this means each shard holds about 2 million users, which is 2 billion divided by 1000. And then each shard holds approximately 36 gigabytes of data, which is 36 terabytes divided by 1000. Each shard is a PostgreSQL instance with 1 primary and 3 read replicas, giving us 4 instances per shard. The total number of database instances across all shards is 1000 times 4, which is 4000 database instances. Now let us verify the read capacity. Each shard has 4 instances, each capable of 10,000 reads per second, giving 40,000 reads per second per shard. Across 1000 shards, the total read capacity is 40 million reads per second. So the required load is now 100,000 reads per second. That gives us about 400 times headroom for growth and traffic spikes. For write capacity, each shard has 1 primary capable of 10,000 writes per second. Across now 1000 shards, the total write capacity will be 10 million writes per second. So the required load is 1,000 writes per second. That gives us 10,000 times headroom. Now there is one more critical concept here, which is data collocation. So when you shard by user ID, all of users' data lives on that shard. User 12345 maps to shard 345 because 12345 mod by 1000 equals to 345. And on shard 345, you will find users 12345's profile from the users table, all of their posts from the post table, which is also sharded by user ID, all of their fellow follow relationships, where 12345 is a follower, and all the likes and comments on their posts. This co-location is extremely important because it means get users profile and their post is now a single shard query. No cross-shard communication is needed now, but sharding is not without its problems as well. So let's understand that, in the next slide. Now here are the challenges with sharding that you should definitely mention in your system design interviews. There are mostly four main challenges, and so let's cover them one by one. The first challenge is cross-shard queries. Let's say consider the query where something like, okay, who follows user 12345? The followers of user 12345 can be on any shard because each follower is stored on their own shard based on their own user ID. So this single query has to go to all 1000 shards, and that is extremely expensive. The solutions include denormalizing by storing a reverse mapping from followee to their list of followers, caching the result in Redis so you only compute it once, or designing a schema so that the common queries stay within one shard. The second challenge is hotspots. Imagine a celebrity user with 600 million followers. The shard where that celebrity lives get disproportionate load whenever they post, and millions of users requesting their content. The solutions include dedicating a shard specifically for celebrity accounts, adding extra replicas specifically for hot shards, caching celebrity data aggressively in Redis, or using a fan-out strategy which we covered earlier in one of the previous YouTube courses. The third challenge is joins across shards, so you simply cannot join data across shards in a single SQL query. Imagine you need get posts from all users you follow, so that will require multiple steps. Let's say like query shard 345 to find who user 12345 follows, then query the shard 999 to get users 999 recent posts, then query shard 888 to get user 88 recent posts, and then merge the results in application code. This is why feed generation at scale uses caching through Redis rather than real-time database joins. And now the fourth challenge is resharding. When an individual shard grows too large, you need to increase the shard count. Growing from 1000 shards to 2000 shards means a user ID that used to be mapped to shard 345 with modulo 1000 might now map to shard 345 or shard 1345 because that will be modulo 2000. Roughly 50% of data must be migrated to the new shards, and that is a very complex and risky operation. A technique called consistent hashing significantly reduces the amount of data that moves during resharding, and we'll cover that in one of the future sections as well. So the takeaway is that sharding is powerful, but it does come with real operational cost. You should only shard when you generally need, when a single database cannot handle all your data volume requirements or throughput requirements, and you should be prepared to discuss these challenges in your system design interviews as well. Now let us bring together everything we have covered in this section. We started with relational databases, which organize data in tables with fixed schemas and SQL queries and provides ACID guarantees. Then we walked through schema design and defined tables, columns, types, and constraints. Then we covered primary keys and foreign keys, which gives you unique identity and cross-table relationships. And then we explored joins, which lets you combine data from multiple tables in a single query. And then we went deep on indexes, which are B-tree structures that can speed up reads by 10,000 to 100,000 times. Then we discussed the index write penalty, the fact that every index slows write operations and you should choose indexes based on your access patterns. Then we covered asset properties, which are atomicity, consistency, isolation, and durability for transactions. Then we moved to the NoSQL world, where we covered key value stores like Redis and DynamoDB for simple key to value lookups that are extremely fast. Then we covered document stores like MongoDB for flexible JSON documents with no joins. Then we covered wide column stores like Cassandra for write-heavy partition data with linear scaling. And then we built a decision framework for choosing between SQL and NoSQL. After that, we covered normalization, which eliminates redundancy by storing each fact once, and denormalization, which deliberately adds redundancy to speed up reads through pre-computed counts. Finally, we covered the two scaling techniques. Replication creates copies of database for read scaling and fault tolerance, with replication lag of 100 to 500 milliseconds that you can solve with a read after write pattern. And then we covered sharding, which splits the database across machines by shard key, with hash-based sharding for even distribution and range-based sharding for efficient reach queries. Before we move on, let me highlight the most common interview mistakes. The first is saying that, okay, I will just use a database without specifying which type or why. The second very common mistake is designing a schema without indexes. So you make sure when you're designing a schema, at least you need to consider building indexes as part of your interview answer. The third common mistake I've seen is that choosing NoSQL because it just like quote unquote scales better without justifying the choice based on the actual access pattern. The fourth common mistake is not mentioning replication or sharding when designing for millions of users. And the fifth very common mistake is that storing images or files in database instead of object storage. So that's also, database is not for storing ideally binary data. So it's better to, you mention that in the interview answer as well. The sixth very common mistake is using arrays in SQL columns instead of junction tables. And the seventh very common one is that not considering cross-shard query implications when choosing a shard key. Now here are the key numbers you should have in your back pocket when doing interviews. A B-tree index lookup is O of log n and it takes less than 1 millisecond even for billions of rows. A full table scan is O of n and it takes seconds to minutes to at scale. A single PostgreSQL instance handles roughly 10,000 queries per second with a 10 to 16 terabyte storage limit. And then Redis and get and set operations take 0.1 to 0.5 milliseconds with 100,000 to 500,000 operations per second per node. And then asynchronous replication lag is roughly 100 to 500 milliseconds. And that at a very large scale, let's say at Instagram scale, you can fit roughly 2 million users per shard. So that completes the section 4 on databases. In the next section, we're going to build on these foundations and explore how systems communicate with each other, which brings us to APIs and communication protocols. So every system works fine for like small number of users. So for example, like 10 or up to 1,000 users. You could run an entire application on a single laptop and nobody would actually notice. The real challenge starts when you start to go and scale from 10 to 100 to 1,000 to like 100,000 and then up to a million users. When you start this process scaling, it's actually, it's evolving your system's architecture as traffic will grow and it will follow a surprisingly predictable progression. So in this section, we're going to cover two things. First, the scaling strategies themselves, meaning vertical scaling, horizontal scaling, caching, sharding, and how they build on each other in a specific order. Second, we'll cover the capacity estimation math that will tell you when you actually need to apply each strategy. There is a back of envelope estimation that interviewers like to see in system design interviews. But before we get into those strategies, let us understand what actually happens when a system cannot handle its load, because there is a failure mode that we are trying to prevent. So it happens in 3 stages. Stage 1 is slow responses. Your server CPU climbs past 80%, the request queue starts building up, and your P50 response time goes from 200 milliseconds to 2000 milliseconds. Users start noticing that pages are loading slowly, but the system is technically still kind of working. The stage 2 is timeouts and errors. The CPU is now pushing past 95%, memory pressure builds, and now some requests are timing out completely with 504 gateway timeout errors. About 5 to 10% of requests have now started failing outright. Stage 3 is cascading failures, and this is where things get really bad. Database connections, they start to get exhausted. Application servers, they start crashing and restarting, and the load balancer detects the health check failures and shifts traffic away from the crashed servers to the remaining ones. But now those remaining servers are receiving even more traffic than before, so they fail now even faster. And then the next step is that the entire system will essentially start going down. Now this progression can happen in minutes during a traffic spike, not hours, not days, actually in minutes. When let's say there's a huge traffic spike, let's say a Black Friday sale or like Amazon's big sale event. Now the goal of scaling is to make sure you never even reach stage 1. And the core principle to internalize here is that scaling is not about building for 1 billion users on day 1. It's about knowing what breaks next and having a plan for it when it does actually break. Over engineering is just as wasteful as under engineering, so the right architecture depends on where you are right now and how fast you are growing. Now let us talk about the two fundamental scaling strategies, starting with vertical scaling. Now vertical scaling is the simplest scaling strategy that exists. It means just upgrading your server to a much more powerful machine. More CPU, more RAM, more disk, a faster network card. Your application code does not need to change at all, and you just run the same thing just on better hardware. Let me give you a concrete example with real numbers. Say your current server is AWS M5.large with 2 vCPUs, 8 GB of RAM, and a 500 GB SSD. That handles about 500 requests per second and costs you about roughly $70 per month. Now, if you vertically scale to an M5.4x large, you now have 16 vCPUs, 64 GB of RAM, and 1 TB of SSD. That handles about 4,000 requests per second and costs roughly $560 per month. So you have got now 8 times the capacity for 8 times the cost. That is linear cost scaling, which is actually pretty good. The advantages of vertical scaling are pretty significant. The first one is simplicity. There are no code changes required, no architecture changes, so that's a pretty big plus. The second big advantage with the vertical scaling is that you can avoid all the distributed systems complexity. You have a single machine with no network calls between servers, so you just scale that up. The third advantage is that asset properties are preserved naturally. You have a single database, so transactions just work. And the fourth is the speed of implementation. You resize the instance, restart it, and then you're done. But then vertical scaling does have some hard limits. The biggest cloud server available as of 2024 is AWS U24TV1.metal instance. That machine has 448 vCPUs, 24 terabytes of RAM, and it costs roughly $200K per month. And even this machine has a ceiling. A single CPU has a clock speed limit, a single disk has an IOPS limit, a single network card has a bandwidth limit, and a single machine is always a single point of failure. There is no server on the planet powerful enough to power websites like YouTube or Instagram just by itself. At some point, you must distribute across multiple machines. So now, where does vertical scaling make sense? It works well for small to medium traffic under, let's say, 10,000 requests per second. It is often the right choice for database servers because databases are easier to scale up than to shard. It works as a quick fix while you're building out a horizontal scaling solution, and it works for applications that are hard to distribute like legacy monoliths. But when vertical scaling hits its ceiling, you need a fundamentally different approach, and that is horizontal scaling. Horizontal scaling takes the opposite approach. Instead of upgrading to a bigger machine, you add more machines and distribute traffic across all of them using a load balancer. Let me compare these side by side with numbers. With the vertical approach, you get one server with 16 vCPUs and 64 GB of RAM handling 4,000 requests per second for roughly $5,000 per month. With the horizontal approach, you have say 8 servers, each with 2 vCPUs and 8 GB of RAM handling 500 requests per second each. That is 8 times 500, which equals to the same 4,000 requests per second. 8 times $70 equals the same $560 per month. Same capacity, same cost. But horizontal scaling actually gives you 3 things that vertical scaling cannot. The first thing is the fault tolerance. If one server dies, you'll still have 7 servers running, which is not possible in vertical scaling. The second big advantage is that the linear scaling path. If you just need more capacity, just add more server numbers, let's say 9, 10, 11, and so on. And the third is that there is no upper ceiling actually. You can keep adding machines pretty much for a very long time. And this is how the architecture looks like. Clients they send requests to a load balancer, and the load balancer distributes those requests across your pool of servers: server 1, server 2, server 3, server 4, and all the way up to server n, which is like the number of servers you have. All of these servers connect to a shared database. But here's a critical requirement that your application must meet for horizontal scaling to work, which is that your application must be stateless. That means any server should be able to handle any request. Session data should be stored in something like Redis, not in server memory. Authentication should use JWT tokens that can be validated by any server. File uploads, they go to a shared storage like AWS S3, not to local disk. And if your application actually, stores anything in local memory or local disk that another server would need the access, horizontal scaling will at that point will break. So this is exactly why we have emphasized stateless server design back in section 3. Now that we understand both the approaches, let me put them side by side and compare them directly. Let me walk through this comparison across 7 dimensions. The first is approach. Vertical means a bigger machine, horizontal means more machines. The second is complexity. Vertical is low complexity because there are no code changes. Horizontal is higher complexity because it does require stateless design and a load balancer. The third is upper limit. Vertical has a hardware ceiling, which is the biggest available server. Horizontal has no ceiling because you can add machines for a very long time. The fourth is a cost curve. Vertical gets expensive fast because premium hardware has premium pricing. Horizontal scales linearly because you are just using commodity hardware and then you're just like, you're going to keep adding them behind the load balancer. The fifth is fault tolerance. So the vertical has none because it is a single point of failure, whereas horizontal has fault tolerance built in because machines are redundant. The sixth is downtime for scaling. Vertical requires downtime because you must restart to resize. Horizontal requires no downtime because you just add a new server and start receiving the traffic. The seventh point is database support. Vertical works well because you can just scale up the database server. Horizontal is more complex for databases because it does require sharding or read replicas. In practice, in production systems, you actually use both the strategies together. Application servers should be horizontally scaled. You run 10 to 1000 or more stateless servers behind a load balancer with autoscaling adding and removing servers based on CPU usage. The database should be vertically scaled first and then horizontally. You start with a large instance, add read replicas when reads exceed capacity, and shard when storage or write throughput hits the limits. Then you add caching layers like Redis, which should be horizontally scaled using a Redis cluster with multiple nodes and data partitioned across them. The real world answer is never purely one or the other. It is a combination that matches each component to the scaling strategy that works best for it. And this is exactly what the scaling progression looks like in practice. So let us walk through it stage by stage, starting from 0 users all the way up to a billion users. Now let us start at the very beginning. Stage 1 is a single server setup, and this covers roughly 0 to 100 users. At this point, everything actually runs on this one machine. Your application code, your database, your web server, all on the single box. There is no redundancy, no caching, no CDN. The capacity is about 100 to 500 requests per second and it will cost you roughly $50 to $100 per month. The bottleneck at this stage is that CPU and RAM are shared between the application and the database, and they are competing for the same resources on the same machine. Now stage 2 is where you separate the database, and this covers roughly 100 to even 10,000 users. The database moves to its own machine. Now the app server and the database server can be sized independently. The database gets more RAM for caching query results, and the app server gets more CPU for processing the requests. Capacity jumps to about 1000 to 5000 requests per second, and the cost is now roughly between $150 to $300 per month for the two servers. The bottleneck at this stage shifts to the single app server, which becomes CPU limited. And that tells you exactly what the next step should be: adding a load balancer and add more app servers. Now this is a pattern you should internalize. At every stage there is one bottleneck, and the next stage specifically addresses that bottleneck. Now let us continue this progression into stages 3 and 4. Now stage 3 introduces the load balancer and multiple application servers. This covers roughly 10,000 to 100,000 users. Now a load balancer sits in front of your application tier and distributes traffic across multiple app servers. The app servers themselves are stateless, with session data stored in an external store. You can add or remove servers based on traffic, and if one server fails, it does not take down the system. Capacity is now 5,000 to 15,000 requests per second at a cost of $500 to $1,500 per month. But the bottleneck has shifted again. It is now a single database handling all the reads and writes. Stage 4 solves this with database replication covering roughly 100,000 users to 1 million users. You introduce read replicas. The primary database handles writes only, and read replicas handle read traffic. Since reads typically make 80 to 90% of all database queries, this is a massive improvement. Read capacity is now multiplied by however many replicas you add. Capacity now reaches 15,000 to 50,000 requests per second at roughly $2,000 to $5,000 per month. But now the new bottleneck is that you're still hitting the database for every single request, even for frequently accessed data that rarely changes. And that bottleneck is exactly what the next stage addresses with the caching layer. Stage 5 adds a caching layer, and this covers roughly 1 million to 10 million users. A Redis cache sits between your app servers and the database. Hot data, things like popular profiles and trending posts, get served directly from the cache. A cache returns data in about 0.5 milliseconds because it is served from RAM. A cache miss takes roughly 5 to 15 milliseconds because it has to go all the way to the database. With an 80% cache hit rate, that means 80% fewer queries hitting your database. That's a very big thing and very big improvement. Now the capacity jumps from 50,000 to 200,000 requests per second, and this architecture will cost you roughly around $5,000 to $15,000 per month. However, the bottleneck now shifts to static assets. Images, CSS, JavaScript, files, they're all being served from your origin servers. So that's the next thing we try to optimize as we try to scale for even larger user traffic. Now stage 6 solves this with CDN and object storage covering roughly 10 million to 100 million users. Images, videos, CSS, and JavaScript are now served from the CDN edge servers located around the world. User uploaded media goes to the object storage like S3. A CDN cache hit takes about 30 milliseconds from an edge server near the user. Your origin servers no longer serve static content directly, and over 80% of your bandwidth gets offloaded to the CDN. Capacity reaches 200,000 to 500,000 requests per second, but that cost is now the cost of the architecture now becomes $15,000 to even $100,000 per month because CDN bandwidth is pretty expensive. The bottleneck at this stage is now the database itself. The single primary database actually cannot handle the right volume of the storage growth anymore for the traffic that goes beyond this limit. And that leads us to the final two stages of this progression. It introduces database sharding, covering roughly 100 million to 1 billion users. Your database gets split into 100 to 1000 more shards. Each shard holds a subset of users and their data. The shard key is typically something like user ID modulo the number of shards. Each shard has its own primary and its own replicas. Write throughput now scales linearly with the number of shards. Capacity reaches 500k to 5 million requests per second, and the cost of this architecture to your company would be roughly 100k to $1 million per month. The bottleneck at this point is no longer technical in the traditional sense. It is the monolithic application itself, which becomes hard to scale, hard to deploy, and hard to maintain when you have large engineering teams. Now stage 8 solves this by decomposing into microservices with message queues. This is a 1 billion plus user territory. The monolith gets split into independent services, for example, a user service, a post service, a feed service, a media service, and so on. Each service scales independently, so asynchronous processing happens through message queues like Kafka or SQS. A service mesh handles the inter-service communication, and multiple teams can deploy independently without stepping on each other. At this stage, the capacity is about 5 million plus requests per second, and the cost of this architecture to your company is roughly more than $1 million per month. This is the level where YouTube, Instagram, Netflix, and Amazon operate. At this stage, you also need additional infrastructure like a service mesh with Envoy or Istio for service discovery, distribute tracing with Jaeger or Datadog for debugging, feature flags for gradual rollouts, circuit breakers for fault isolation, and autoscaling groups for each service independently. Now let us zoom out and look at all the 8 stages together. Here's a complete progression in one view. Stage 1, single server with app and database on one machine, handles 0 to 100 users at 100 to 500 requests per second for $50 to $100 per month. Stage 2, separate database server, handles 100 to 10,000 users at 1,000 to 5,000 requests per second for $150 to $300. Stage 3, load balancer with multiple app servers, handles 10,000 to 100,000 users at 5,000 to 15,000 requests per second for $500 to $1,500 to your company. At stage 4, database read replicas handles 100K to 1 million users at 15,000 to 50,000 requests per second for $2,000 to $5,000 and to your company for this architecture. At stage 5, we added the Redis caching layer, which handles 1 million to 10 million users at 50,000 to 200,000 requests per second for $5,000 to $15,000 as the cost for the architecture. At stage 6, we added the CDN and object storage, which handles 10 million to 100 million users at 200K to 500K requests per second for $15,000 to $100,000. And at stage 7, we added the database sharding, which enables us to handle even more users. For example, 100 million to 1 billion users at 500,000 to 5 million requests per second for $100,000 to $1 million in cloud computing costs to your company. And after that, in the last stage, at stage 8, we added microservices message queues, handles over 1 billion users at 5 million plus requests per second for over $1 million per month in compute costs. There are the 4 key observations to observe here. First, each stage solves a specific bottleneck from the previous stage. CPU contention leads to database separation, single server limits lead to replicas, database load leads to caching, static asset delivery leads to CDN, storage and write limits lead to sharding, and team and deployment complexity leads to microservices. Second, cost grows roughly in the proportion to user count. It is about $0.01 per user per month at stage 2, whereas it becomes $0.1 per user per month at stage 5 and $0.1 per user per month at stage 8. Third, you do not need all the 8 stages from day 1, so most startups live comfortably at stage 3 and 4 for years. Only a handful of companies ever reach stage 7 or 8. And fourth, each stage adds complexity. You should only move to next stage when the current one actually breaks. Premature optimization wastes both engineering time and money. For system design interviews, when you're designing a system, you should be asking the interviewer about the scale. If they say to, let's say, design for about 10,000 users, you do not need sharding or microservices. If they do say that, okay, design for 500 million users, you skip straight to stage 6 through 8 and explain why. Matching architecture to the actual scale demonstrates practical engineering judgment. Okay, now so that we know the scaling strategies, but how do we actually figure out which stage do you need? How do you translate 500 million users as a number into concrete infrastructure requirements? This is where capacity estimation comes in, so let's cover that. Now, back-of-envelope estimation is a practice of calculating approximate infrastructure requirements using simple arithmetic. In system design interviews, interviewers actually use it to test whether you can reason about scale and translate user-facing requirements into actual infrastructure needs. It's actually not about precision, it is about order of magnitude and how you can actually roughly estimate the scale and translate that. Now, there are 4 things that you should estimate. The first is QPS or queries per second, which tells you how many servers and database connections you need. The second is storage, which tells you how much disk space you need, what kind of database to use, and when to shard. The third is bandwidth, which tells you your CDN requirements, network costs, and potential bottlenecks. And the fourth is memory for caching, which tells you the Redis cluster size and the impact of your cache hit rate. Now there are some ground rules to follow. First, round aggressively. Precision does not matter, so order of magnitude does. There are 86,400 seconds in a day, but for estimation purposes, you can just say 100,000 is a perfectly acceptable rounding. Second, show your work. The calculation process matters more than the final answer. Third, state your assumptions explicitly, saying that, okay, I will assume 20% of the users are active daily users is far better than guessing silently. And fourth, you should be using powers of 10 for speed. 1 kilobyte is 10 to the power 3 bytes, 1 megabyte is 10 to the 6, 1 GB is 10 to the 9, 1 TB is 10 to the 12, and 1 PB is 10 to the 15. Now let us start applying these rules with the most important metrics, which is QPS. QPS estimation starts with a simple formula. Read QPS equals your daily active users times reads per user per day divided by the number of seconds in a day. Write QPS uses the same formula but with writes per user per day. And peak QPS equals your average QPS times the peak multiplier, which is typically 2 to 5x. Let me walk you through this with Instagram as a concrete example. Let's say in a system design interview, we are given that Instagram has 500 million daily active users, 20 posts viewed per user per day, and 0.2 posts created per user per day because not everyone is posting daily. Now for read QPS, we'll take 500 million times 20. We divide that by 86,400 seconds in a day, but we round the 86,000 to 100,000 for speed. That gives us 100,000 read QPS. For write QPS, we take 500 million times 0.2, which gives us 100 million writes per day. When we divide that by 100,000 seconds per day, that gives us 1,000 write QPS. For peak, assuming a 3x multiplier, peak reads are 300,000 QPS and peak writes are 3,000 QPS. The read to write ratio is 100,000 to 1,000, which simplifies to 100 to 1. This tells you that Instagram is a heavily read skewed system. Now, what do these numbers actually tell you about the infrastructure? A single server handles about 5,000 QPS. 100,000 divided by 5,000 means you need at least 20 app servers. With 3x headroom for peak traffic, that is 60 app servers. For writes, a single database handles about 10,000 writes per second. And 1,000 writes per second, that fits comfortably on a single primary. So you do not need sharding for writes alone. The storage growth will eventually force sharding regardless, and that 100 to 1 read to write ratio tells you to invest heavily in read optimization, which is caching, read replicas, and CDN. The write path can be much more simpler. Now let us estimate how much storage all of this data will require. Now storage estimation uses another straightforward formula. And daily storage equals new records per day times the average record size. Annual storage equals daily storage times 365. Continuing with Instagram, let us start with photo storage. There are 100 million posts per day and the average photo size after compression is 2 megabytes. That gives us 100 million times 2 MB, which equals to 200 terabytes per day. Over a year, that is 200 terabytes times 365, which is equals to 73,000 terabytes, which is 73 petabytes per year. Now for metadata storage, post metadata is about 1 kilobyte per post. That is 100 million times 1 kilobyte, which equals to 100 GB per day. So over a year, that is 36.5 terabytes. Now let's look at the comparison. Now media, meaning the photos, is 73 petabytes per year. That is 99.95% of total storage. Metadata in the database is 36.5 terabytes per year, which is just 0.05%. Media storage completely dominates. This means your architecture must optimize for media delivery using CDN and object storage. Database storage for metadata is negligible by comparison. So what do these numbers mean concurrently? 73 petabytes per year of photos means you cannot store them in database. You need object storage like S3 or Azure Blob. You must use a CDN for delivery because the origin servers cannot handle that much egress bandwidth. You need lifecycle policies to move older photos to cheaper storage tiers. And at S3 standard pricing, that is 73,000 TB times $23 per TB per month, which equals to $1.68 million per month just for photo storage. 36.5 terabytes per year of metadata, that fits comfortably on a handful of shared PostgreSQL instances. With 1,000 shards, each shard holds about 36 GB. That is well within PostgreSQL's limit. Now let us estimate the bandwidth required to serve all of this content. Now bandwidth estimation has two components. Ingress, which is upload bandwidth, equals writes per second times average write size. And then the second one is egress, which is download bandwidth, equals reads per second times average read size. For Instagram, ingress is 1000 writes per second times 2 MB per photo. That equals 2000 MB per second or 2 GB per second. Egress is 100,000 reads per second times 2 MB per photo. That equals 200,000 MB per second or 200 GB per second. Now let's look at the ratio. Egress is 200 GB per second. Ingress is 2 GB per second. that is 100 to 1 egress to ingress ratio, and it makes CDN absolutely non-negotiable. No origin server cluster can sustain 200 GB per second of outbound traffic. Let me put that cost into perspective. Without a CDN, you need 200 GB per second of origin bandwidth at $0.09 per GB, that is $18 per second, which means it comes down to $46 million per month. With a CDN at an 80% cache hit rate, your origin bandwidth drops to 40 GB per second because 80% of requests are now being served from CDN edge servers. CDN bandwidth is also much more cheaper than origin bandwidth, so total cost drops significantly. So CDN is not just a performance optimization at this scale, it is a cost requirement, and the math makes it unavoidable. Now that we have walked through QPS, storage, and bandwidth estimation using Instagram, let's apply all three of these to have a completely different kind of system to see how this analysis changes. Now let us do a complete capacity estimation for a WhatsApp scale chat system. Let's say in the system design interview, these are the numbers given to you by the interviewer. Assume that there are 2 billion monthly active users, 1 billion daily active users at 50% daily engagement, 40 messages sent per user per day, an average message size of 100 bytes for text only, and an average group size of 5 members, meaning each message gets delivered to 5 people. Starting with the QPS, write QPS, the message sent is actually 1 billion times 40 divided by 86,400, which is the number of seconds in a day. So that is 40 billion divided by roughly 100,000, which gives us 400,000 messages per second being sent. Read QPS, which is the messages being delivered, is 400,000 times 5 for the average group size, which equals to 2 million messages per second being delivered. At peak with the 3x multiplier, that is 1.2 million writes per second and 6 million reads per second. Now here's the key insight. Unlike Instagram, which had a 100 to 1 read to write ratio, this system has a much smaller ratio. It's actually a write heavy system. That means write optimization is critical, and you should be thinking about write optimized databases like Cassandra rather than PostgreSQL. For storage, daily text message storage is 1 billion users times 40 messages times 100 bytes. That is like a very big number of bytes per day, or which comes down to actually 4 terabytes per day. Annually, that is 1.46 petabytes per year. But when you add media messages, the picture changes dramatically. If 5% of the messages include media like photo or voice notes, and the average media attachment is, let's say, 500 kilobytes, that is 2 billion media messages per day times 500 kilobyte, which is equal to 1000 terabytes per day or 1 petabyte per day. Over a year, that is 365 petabytes for media versus 1.46 petabyte for text. Media storage dominates again, just like Instagram. For bandwidth, text bandwidth is 2 million messages per second times 100 bytes, which equals 200 MB per second. That is trivial, but media bandwidth is 100,000 media messages per second times 500 kilobytes, which equals 500 GB, 550 GB per second. That is pretty significant and requires a CDN. Now let me walk you through the architecture implications of these numbers. A write QPS of 400,000 per second means you need a write optimized database like Cassandra, not PostgreSQL. A read QPS of 2 million per second means you need aggressive caching and read replicas. Text storage of 1.46 petabyte per year means a sharded database with TTL policies for old messages. The media storage of 365 petabytes per year means object storage with CDN. And media bandwidth of 50 GB per second means CDN is required. Notice how the estimation drove us to a completely different architectural decisions than Instagram. Now that is the power of capacity estimation. The numbers actually tell you what architecture you need, and you should be doing that in interviews as well. Now let me talk about the mistakes that people most often make when doing these estimations. There are 5 mistakes that come up over and over, both in interviews and also in real-world capacity planning. The first mistake is forgetting to distinguish between read and write QPS. Saying QPS is like 100,000 without specifying whether those are reads or writes is actually a problem because they have completely different implications. 100,000 reads per second means you need caching and replicas. 100,000 writes per second means you need sharding and write optimized databases. So you need make sure that you always state both separately. The second mistake is not accounting for peak traffic. Saying, let's say, average QPS is 100,000, so we need servers for 100,000 is a dangerous statement because traffic is never evenly distributed. Peak hours can be 3 to 5 times the average, so you need to be prepared for that. If you just provision for the average, your system will go down during peak. So always calculate peak QPS as average QPS times 3, at least 3. Now the third mistake is prioritizing the precision over magnitude. Saying QPS equals, let's say, 10 billion divided by 86,400 equals to 115,740 actually wastes valuable interview time on long division. You don't need that, and you don't need to spend that in time during the interview. The correct approach is to round numbers because your goal is to show that you can do the estimation and mathematics without actually being completely precise. So the correct approach is, for example, in this case would be 10 billion divided by 100,000, which is approximately 100,000 QPS. That is pretty close enough. The reason is that the interviewers actually they want to see you reason about scale, not to do exact arithmetic. The fourth mistake is ignoring the difference between metadata and media storage. Saying we need 73 petabytes for database is wrong because the 73 petabytes is media, which goes to object storage. The database stores metadata, which is about 36 terabytes per year for Instagram. Mixing these up leads to completely wrong infrastructure decisions. And the fifth mistake is hand waving with, okay, we will scale horizontally. With that statement, let's say, when the interviewer asks you, okay, how will you handle 500 million users? And if you just respond with a blank statement that, okay, we'll just scale horizontally, that is not a good answer. You need to be more specific with answer things like, okay, what component will you be scaling? How many servers? What is the shard key? How many shards? So you have to always follow with specific numbers. For interviews, you should be spending about 3 to 5 time minutes in your 45-minute interview on capacity estimation. You should be writing the numbers on the whiteboard as you calculate. The interviewer is watching your reasoning process, not checking arithmetic. So round the numbers aggressively, state your assumptions clearly, and draw concrete conclusions like, okay, this means we need roughly 20 app servers and CDN is mandatory. And with that, let us wrap up everything we have covered in this section. Now let us review the key concepts from this section. Vertical scaling means a bigger machine. It is simple but it has a ceiling. Horizontal scaling means more machines which requires stateless design but has no ceiling. The scaling stages, follow a predictable progression from single server all the way to microservices. Background envelope estimation lets you approximate QPS, storage, and bandwidth from user requirements. Read versus write QPS ratios require different optimization strategies. You should always provision for peak traffic, which is typically 3 to 5 times the average. The scaling decision tree should be straightforward. If the system is slow and you're on a single server, separate the database from the app server. If the app server is overloaded, add a load balancer and more app servers. If the database is overloaded with reads, add read replicas. If reads are still slow for popular data, add a Redis caching layer. If static assets are slow to deliver globally, add a CDN. If the database is too large or write throughput is too high, shard the database. And if the monolith is hard to scale, deploy or maintain, decompose into microservices. There are a few key numbers worth remembering as well. Now, seconds in a day is approximately 100,000. A single web server handles about 1,000 to 5,000 QPS. A single database handles about 10,000 QPS with a practical storage limit of 10 to 16 TB. Redis handles 100,000 to 500,000 operations per second per node. CDN cache hit rate target should be 80% or higher. Peak multiplier should be 3 to 5 times the average. And at Instagram scale, you are looking at roughly around 100,000 read QPS, 1,000 write QPS, and 73 petabytes of media per year. So now let us talk about caching. If there is one single optimization that has the biggest impact on system performance, this is it. Caching is the reason your favorite apps feel fast on your phones, and the absence of caching is the reason slow apps feel slow. So now what exactly is a cache? A cache is a temporary storage layer that holds frequently accessed data in a faster medium so that the future request for that data can be served without going back to the slower origin source. In most systems, the slower origin source is a database reading from disk, and the faster medium is RAM. Here's what that looks like in practice. Now, without a cache, every request follows the same path. The client sends a request to the app server, the app server queries a database, the database reads from the disk and returns the result. That disk read takes anywhere from 5 to 50 milliseconds. Every single request now pays that cost. Now, if you include that cache, the path actually changes. The client sends a request to the app server, and the app server checks the cache first, and if the data is there, it returns immediately. That RAM read takes only 0.5 milliseconds. Only when the data is not in the cache, which we call a cache miss, does the request then fall through to the database. So we are talking about a 10 times to even 100 times speed improvement for every request that hits the cache. And this is where the numbers get really compelling. Let us say you have a system handling 100,000 requests per second and you achieve cache hit rate of 80%. That means 80,000 of those requests are now being served from the cache and never touch the database. Now your average response time drops from 50 milliseconds down to about 10 milliseconds. The number of database servers that you would need actually now drops from 10 down to 2. And your monthly database cost will also drop from $5,000 to $1,000. So caching does not just make things faster, it fundamentally reduces infrastructure costs by taking the load off the most expensive component in your system, which is the database. So why does caching work so well? It works because access patterns in real systems are not random. In almost every system you encounter, a small percentage of data receives a disproportionately large percentage of requests. This is known as the 80-20 rule or Pareto distribution, and it is the fundamental reasoning caching is so effective. Now let us look at some real examples. On Instagram, roughly 20% of posts receive 80% of all the views. A viral post from a celebrity might get millions of views, while a post from a private account might just get 50. If you cache just the top 20% of the post, you handle 80% of all read traffic from the cache. Now YouTube is even more extreme. About 10% of the videos account for 90% of all the views. A video like Baby Shark has 14 billion views, while the vast majority of videos have under 1000 views. And on Amazon, 20% of the products generate 80% of the page views. Similarly, like for example, if you look at the iPhone listing, will get millions of views per day, whereas some like industrial part on Amazon will get like 3 views per day. Now there are specific types of locality that explain these patterns. The first is temporal locality, which means recently accessed data is likely to be accessed again soon. Think of a user viewing their own profile multiple times per session. The second is the spatial locality, which means data near recently accessed data is likely to be accessed next. If a user views post number 100, they are likely to scroll and view posts from 101 and 102. And the third is frequency-based locality, where some data is simply accessed far more often than the other data. For example, celebrity profiles might be viewed 1000 times more than the average user profile. So now, what should you be actually caching? Good candidates for caching are data that is read frequently and written rarely, like user profiles. Then data that is expensive to compute, like feed ranking results, that's also a good candidate for caching. Data that does not change often, like a product catalog or configuration settings, is also a very good option to cache. And data where slight staleness is acceptable, like follower counts, is good for caching as well. Now, bad candidates for caching are data that changes on every read, like real-time stock prices with microsecond precision. Data that is unique per user request, like a one-time password, that should not be cached anyways, just because even for security purposes. Data that must always be perfectly consistent, like a bank balance during a transfer, should also not be cached. And large data that is rarely reassessed, like log entries, that also should not be cached. So understanding what to cache and what not to cache is just as important as understanding how caching works. Okay, now let us talk about the two possible outcomes of every cache lookup, a cache hit and a cache miss. A cache hit means the data was found in the cache. The system returns it directly. This is a fast path taking about 0.5 milliseconds. A cache miss means the data was not in the cache. The system has to fall through the original source, which is usually the database, fetch the data at a cost of 5 to 50 milliseconds, return it to the client, and optionally store it in their cache so that the next request for the same data will be a cache hit. The flow works like this. A request comes in, let's say, get users 1 to 3's profile. The application first checks the cache. If the data is there, then there's a cache hit, return it immediately. If it's not there, cache miss, then it queries the database, get the result, store it in the cache for future requests, and then it returns to the client. Now, the metric that actually most is is the cache hit rate. The cache hit rate, is simply cache hits divided by the total requests times 100. So if you have 100,000 requests per second and 80% of them are served from the cache, you have a hit rate of 80%. Now let me walk you through the math on how hit rate affects the average latency. And because this is where it gets pretty interesting. At 70% hit rate, your average latency is 0.7 times, 0.5 milliseconds plus 0.3 times 50 milliseconds, which comes out to be 15.35 milliseconds. At 80% hit rate, it drops to the 10.40 milliseconds. At 90%, it drops to 5.45 milliseconds. And at 95%, it is just 2.98 milliseconds. So every 10% improvement in cache hit rate roughly halves your average latency. And here is the actual counterintuitive insight. Going from 80% to 90% actually has much more impact on per request latency than going from 0 to 80%. So now, what determines your cache hit rate? The first factor is the cache size. A larger cache means more data fits, which means a higher hit rate. The second is TTL, or time to live. A longer TTL means data stays in the cache longer, which improves the cache hit rate, but the trade-off is that the data can become more stale. The third is your access pattern. Skewed patterns like 80-20 distribution we talked about naturally produce higher hit rates than uniform access. The fourth is the eviction policy, meaning the algorithm that decides what to remove when the cache is full. A better eviction policy keeps the right data in the cache. And the fifth is your working set size. If your entire working set fits in the cache, your hit rate will be near 100%. This is exactly where caching layer comes in. Caching does not happen at just one point. It can happen in multiple layers along the request path, and production systems typically use several of these layers simultaneously. The four layers are browser cache, CDN cache, application cache, and database query cache. Let us walk through each one. The first layer is the browser or client cache. So this lives on users and device itself. It stores static assets like CSS, JavaScript, and images, as well as API responses. The TTL is controlled by HTTP cache control headers. It typically holds 50 to 500 megabytes per user, and the latency is literally 0 milliseconds because no network request is made at all. The browser just reads from the local storage. The second layer is the CDN cache. This lives on the edge servers distributed worldwide, often in hundreds of locations. It stores static files, images, videos, and sometimes API responses. TTLs range from minutes to days. The total capacity is petabytes across all edge nodes, and the latency is 5 to 30 milliseconds because the request only has to travel to a nearby edge server instead of all the way back to your data center. Now the third layer is the application cache, which is typically Redis or memcached. This lives in your data center on dedicated cache servers. It stores database query results, computer data, and session state. In this case, the TTLs are typically 1 to 15 minutes. The capacity ranges from 10 gigabytes to 10 terabytes per cluster, and the latency is 0.1 to 1 millisecond because it's an in-memory and is in the same data center. Now the fourth layer is the database query cache. This lives on the database server itself in its memory. It caches the results of repeated identical queries. It is invalidated whenever there is the underlying table is modified. The size is limited by the database server RAM, and the latency is 0.1 to 1 millisecond because it avoids the disk read and serves from the buffer pool. Now in terms of which layer handles what, CSS, JavaScript, and fonts should be in the browser cache and CDN. User uploaded images should be in the CDN or object storage. API responses like user profiles should be in the application cache using Redis. Database query results should be in the application cache or the database query cache. Session data and computed feed should be in the application cache using Redis. The key insight is that you want to cache as close to the user as possible. Browser cache is faster than CDN, CDN is faster than the application cache, and application cache is faster than the database cache. Now that we understand where to cache, now let us look at how to cache actually. And the most important caching pattern to understand is cache aside, also called lazy loading. This is the most common caching pattern you will encounter in production systems. In cache aside, the application manages the cache explicitly. The application checks the cache first. On a hit, it returns the cache data immediately. On a miss, it fetches from the database, stores the results in the cache, and then returns it. Let us walk through the code. The function here takes a user ID. In step 1, it constructs the cache key like user colon, followed by the user ID, and checks the cache. If the cache value is not none, that is a cache hit, so it deserializes the JSON and returns immediately. In step 2, if it is a cache miss, it queries the database with the select statement for that user ID. In step 3, it stores the results in the cache using a setx command, which sets the value with a TTL of 300 seconds, which is 5 minutes. Then it returns the result. The next time any request asks for this same user, it will be a cache hit. The key characteristics of cache asides are these. So cache population happens on demand, meaning only when the cache data is actually requested and missed. Write responsibility stays with the application, which writes to the database, and the cache only gets updated on the next read. There is a staleness risk because data can be stale until the TTL expires or the cache is explicitly invalidated. And on restart, you have a cold cache, meaning all the requests hits the database until the cache warms up. Now, the advantages of cache aside are that it only caches data that is actually requested, so you do not waste memory on unused data. It is simple to implement, and if the cache goes down, the system does not break. It just falls back to reading from the database directly, which is slower but still functional. The disadvantages are that the first request for any data is always slow because it isn't guaranteed to be a cache miss. The cache and database can be inconsistent because the data is stale until the TTL expires. And then you have the cold start problem, which is after a cache restart, all the traffic hits the database simultaneously. Okay, now let us look at two other caching patterns that handle writes differently from cache aside, which is write through and write behind. In write through, every write goes through both the cache and the database. The cache is always up to date. So now let us walk through the code. When we update a user profile in step 1, writes to the database with an update statement. In step 2, we immediately write the same data to the cache with the setx command and a 300-second TTL. Because both writes happens together, the cache is immediately consistent with the database. Write behind, which is also called write back, works differently. In write behind, writes go to the cache first, and the cache asynchronously flushes to the database later. In the code here, step 1 writes only to the cache, and step 2 enqueues the write to the message queue. A background worker picks up the message and writes it to the database at some point later. The write returns immediately after the cache is updated, so from the caller's perspective, the write is very fast. Now, the fundamental trade-off between these two patterns is consistency versus speed. Write-through gives you strong consistency but slower writes because every write has to wait for both the cache and database. Write behind gives you fast writes but only eventual consistency and introduces a data loss risk. If the cache crashes before the background worker flushes into the database, those writes will be lost. These strategies side by side and talk about when to use each one. Cache aside gives you a miss on the first read, does not involve the cache on writes at all, and has stale data until the TTL expires. It is low complexity and has no data loss risk. Write-through always hits the cache on reads, and slower writes because it writes to both cache and the database, gives you strong consistency, is medium complexity, and it also has no data loss risk. The write behind approach always hits the cache on reads, has fast writes because it only writes to the cache, gives you eventual consistency, but it's high complexity and does have a data loss risk if the cache crashes before the message queue, the background worker flushes the data to the database. So when should you actually use each one? Cache aside is the most common and should be your default. Use it for read-heavy workloads like social media feeds and user profiles, for data where style staleness is acceptable and when you want simplicity. Write through is actually should be used for data that must be immediately consistent in both cache and database. For read after write scenarios where a user updates their profile and immediately views it, and when your write volume is moderate. Write behind should be used for write heavy workloads like analytic events and counters, when write latency must be minimal, when you can tolerate potential data loss on a cache crash, and when the database cannot keep up with the write throughput. In practice, most production systems use cache aside for majority of their data, combined with write through for critical paths where read after write consistency matters. For example, when a user just updates their display name and needs to see the change reflected immediately. Now let us talk about what happens when the cache gets full. Caches have limited memory, so when the cache is full and new data needs to be stored and an existing entry has to be removed. The algorithm that decides which entry to be removed is called eviction policy. And why does the eviction policy matter so much? Let us now think about this with real numbers. Say your cache can hold 10 gigabytes and each user profile is about 1 kilobyte. That means your cache can hold roughly 10 million user profiles. But your system has 2 billion users, so only 0.5% of all users can fit in the cache at any given time. The eviction policy determines which 0.5% user stays. A good policy keeps the most frequently accessed profile in the cache, giving you an 85% cache hit rate. A bad eviction policy will evict popular profiles and keep rarely accessed ones, dropping your cache hit rate to 40%. The difference is 4.5 times more database load with a bad eviction policy. There are 5 common eviction policies, as you can see on the screen here. So the first one is LRU, which is least recently used, which evicts the entry that has been not accessed for the longest time. This is the most common and the best for general purpose use. The second is LFU, which is the least frequently used. And then which means that you evict the entry that has been accessed the fewer total of times. This is best for workloads with stable popular items. The third is FIFO, which is first in first out, which simply evicts the oldest entry. This is the simplest and works for time-based expiry. The fourth is TTL, which is time to live, which removes entries whose expiration time has passed. This is best for data with known freshness requirements. And the fifth is random eviction, which removes a random entry. It's only useful when access patterns are truly uniform, which is rare. Now let us go deeper on LRU, because it's the most widely used eviction policy and something you should be able to explain in detail. LRU evicts the entry that has not been accessed for the longest time. The intuition is pretty simple. If you have not used for something recently, you are unlikely to use it soon. Let me walk through how it works, with a cache that has a capacity of 4 items. We start with an empty cache, we get A, that is a miss, so the cache state is now get A. So we get B, that is a miss as well, so cache state is now B, A. The next step is, let's say there's a request for getting C, that will be a miss, so now cache state is C, B and A. Now let's say we get the operation D, again that's a miss, so the cache state is D, C, B, A. And now the cache is full. Then we get an operation which is get A again. This time it's a cache hit, so A moves to the front. The cache is now A, D, C, B. Then we get E, which is a miss. The cache is full, so we evict the least recently used entry, which is B. Now the cache becomes E, A, D, C, and then we get C, which is a cache hit. So C moves to the front. So now the state of cache is C, A, E, D. Finally, we get F, which is a miss. So D, which is evicted, as is the least recently used, and the cache state now is FCEA. Now, the implementation of LRU uses 2 data structures together, a hash map and a doubly linked list. The hash map provides overfun key lookup, mapping each key to a pointer to its node in a linked list. The doubly linked list maintains the order by recency, with the most recently used item at the front and the least recently used item at the tail. Moving a node to the front is overfun, and evicting the tail is also overfun. For a get operation, you look up the key in the hash map that is overfun, and if you find you move the node to the front of the list, which is also overfun. For a put operation, if the key already exists, you upgrade the value and move to front, which is OF1. If the key is new and the cache is full, you evict the tail, which is OF1, and then you insert the new node at the front, which is OF1 as well. Every operation is essentially OF1. This is exactly why LRU is practical at a very large scale. Yeah, one important detail that you should keep in mind is that Redis uses an approximate LRU rather than a true LRU. Instead of tracking the exact access order of every key, which would require significant memory overhead, Redis samples a subset of keys and evicts the least recently used among the sample. This is close enough to true LRU for production use and saves memory. Now let us briefly cover the other eviction policies that you should know as well. LFU, which is the least frequently used, evicts the entry with the fewest total accesses. The advantage over LRU is that constantly popular item will not be evicted just because it was not accessed in the last few minutes. If an item has been accessed 10,000 times, LFU will not evict it just because it had a brief quiet period. This makes LFU better for workloads with stable hot data. The disadvantage is that new items start with low access count and can get evicted quickly, even if they would eventually become very popular. You also need to track the access count per key, which adds more memory overhead. LFU is a good choice for CDN caching where popular content tends to stay popular for weeks at a time. The FIFO approach, which is the eviction policy, which is the first in first out, simply evicts the oldest entry regardless of access pattern. The advantage is that it's the simplest to implement because it is just the queue. So the disadvantage is that it ignores the popularity entirely. A very popular item, for example, will get evicted just because it was inserted first. FIFO is only useful for simple TTL based caches where age is the only factor that matters. Then there is TTL, which is time to live. Each entry has an expiration timestamp and entries are removed when that timestamp is reached. For example, you might set a user profile cache entry to expire in 300 seconds. TTL is not strictly an eviction policy on its own. It is typically combined with another policy. For example, LRU with TTL has an eviction policy. So TTL handles the staleness problem, making sure the data does not get too old. LRU handles the capacity problem, making sure the most relevant data stays when the cache is full. When it comes to choosing TTL values, session data should be around 30 minutes. User profile caches should be 5 to 15 minutes. Feed caches should be 1 to 5 minutes. Configuration data can go 1 to 24 hours, and product catalog data should be about 1 hour. The trade-off is always the same. Longer TTL gives you higher hit rate but more stale data. This brings us to one of the hardest problems in caching, and honestly one of the hardest problems in computer science, as they say, cache invalidation. Cache invalidation is the process of removing or updating stale data from the cache when the underlying source data changes. There is a famous saying that there's two hardest problems in computer science, which are cache invalidation and naming things. Now let me show you why this is so hard with a concrete timeline. At time 0, let's say our user profile is cached with the name John and the bio engineer with a 5-minute TTL. At the 1-minute mark, the user updates the bio to senior engineer in the database. At the 2-minute mark, then let's say another user views the profile, but the cache still has old bio, say engineer. That data is now stale. It will stay stale until the 5-minute mark when the TTL expires. At that point, the next read fetches from the database and gets corrected bio. So now the user's update was invisible for 4 minutes. Now let's say if you think about it, is that acceptable? Now it depends entirely on the use case. Now here's why solving this is such a hard problem. Option A is to invalidate immediately on every write. This guarantees freshness, but it requires knowing every cache key affected by every write. A single database write might affect 10 different cache keys: the user profile cache, the feed cache, the search cache, the follower list cache. Coordinating all of those invalidations correctly is extremely error prone. The option B is to use short TTLs. That is simply because you don't need any invalidation logic. But short TTLs means frequent cache misses, which actually reduces your hit rate, and the data is still stale for up to the TTL duration. Option C is to actually never invalidate and always serve stale data. This gives you the highest hit rate, but it's completely unacceptable for most use cases. Now, none of these options are perfect, and this is exactly why cache invalidation is considered one of the hardest problems to solve. So, how do production systems actually handle cache invalidation? There are three strategies, and understanding the trade offs between them is pretty important. The first strategy is TDL based, which is time based expiry. You set an expiry on every cache entry, and the data is automatically removed when the TDL expires. For example, using a setx command with the key of, let's say, user colon 123, a TDL of 300 seconds, and the profile data. The pros are that it is simple, predictable, and requires no coordination between services. The cons are that the data can be stale for up to the full TDL duration. This strategy is best for data where slight staleness is acceptable, like follower counts or feed data. Now, the second strategy is event-based, also called the active invalidation. When the underlying data changes, you explicitly delete or update the cache entry. In the code, after updating the user profile in the database, you immediately call a delete on the cache key for the user. The next read will trigger a cache miss and fetch the fresh data from the database and repopulate the cache. You can even be more aggressive and do a write through. So after the database update, immediately write the new data into the cache instead of just deleting it. The pros are that the data is fresh immediately after a write. The cons are that you must identify and validate all affected cache keys, and if you forget to invalidate one, the stale data still persists. This strategy is best for data where freshness matters, like user profiles and permissions. Now, the third strategy is hybrid, which combines TTL and event-based invalidation. You use event-based invalidation for critical writes, so the cache is updated immediately, and you also set a TTL as a safety net. So if the event-based invalidation fails for any reason, the TTL will eventually cache it. This is the most common production approach. Event-based handles the common case for intermediate freshness, and TTL handles the edge case when the invalidation event is missed. To compare them side by side, TTL only gives you stale data for up to TTL duration, low complexity, and high hit rate. Event-based only gives you immediate freshness, high complexity, and a low hit rate due to frequent invalidation. And hybrid gives you immediate freshness, the safety net, medium complexity, and high hit rate. For most production systems, hybrid is the right answer. Let us talk about Redis, because when we say application cache and system design, we almost always mean Redis. Redis stands for a remote dictionary server. It's an in-memory key value data store, and it's the most widely used caching technology in production systems. But it is more than just a cache. It supports multiple data structures and can serve as a cache, a session store, a message broker, a leaderboard engine, and a rate limiter. Let us walk through the key characteristics for Redis. Redis stores everything in RAM with optional disk persistence. Its latency is approximately 0.1 to 0.5 milliseconds per operation. Its throughput is 100,000 to 500,000 operations per second on a single node. For data persistence, it offers RDB snapshots and AOF, which stands for Append Only File. For replication, it supports primary replica with automatic failover through Redis Sentinel. For horizontal scaling, Redis cluster partitions data across multiple nodes, and max memory per node is limited by the RAM, typically 225 to 256 gigabytes. So now let's talk about why Redis is so fast. There are three reasons. First, all the data lives in RAM. A RAM read takes about 100 nanoseconds, and SSD read takes about 150 microseconds, which is 1,500 times slower. And HDD read actually takes about 10 milliseconds, which is even actually 100,000 times slower. Second, Redis uses a single-threaded event loop. There's no locking through overthread, no context switching. It processes the command sequentially at extreme speed. Third, Redis uses optimized data structures like hash tables, skip lists, and compressed lists, all purpose built for fast in-memory operations. Now for production deployments, the sizing depends on your scale. For a small deployment with a single app and under 10,000 users, a single Redis instance with 1 to 4 gigabytes of RAM is more than sufficient. For a medium deployment with microservices and 100,000 to 10 million users, you should use Redis Sentinel with one primary and two replicas for automatic failover with 16 to 64 gigabytes of RAM per node. For large scale deployments, let's say at the scale of Instagram or Twitter scale, you would use Redis cluster with 100 to 400 nodes, data partition across nodes by key hash with a total memory of 1 to 10 terabytes across the cluster. One of the things that make Redis so powerful is that it's just not just simple get inside operations. It's actually much more than that. Redis supports multiple data structures, each optimized for specific access patterns. The first is a string type, which supports operations like get, set, incr, and dscr. So in system design, strings are used for basic caching, encounters, and also rate limiting. The second is the hash type, which supports edgeget, edgeset, and edgegetall. Hashes are perfect for storing user profiles and objects because you can get to send individual fields without fetching the entire object. The third is the list type, which supports lpush, rpush, lpop, and lrange. Lists are used for recent items, activity feeds, and even for simple message queues. The fourth is the set type, which supports sadd, serr, smove, smembers, and sinter. Sets are used for tags, tracking unique visitors, and computing mutual friends. And the fifth is the sorted set, which supports zadd, zrange, zrange by score, and zrank. Sorted sets are used for leaderboards, feed ranking, and priority queues. Now let me walk through 4 real-world examples. For rate limiting, using a string with incr, you create a key like rate limit :user :123 : post, and you increment it with each request. You set an expire of 3600 seconds, so it resets after every 1 hour. If the count exceeds 10, then you reject the request with a 429, which is too many request response. For feed caching using sorted set, you create a key with feed :user :123 and add post IDs with their timestamps and scores using zadd. You get the 20 most recent posts and you use the z rev range from index 0 to 19, which returns the newest first. For a session storage stored like using a hash, you create a key like session :abc123 and use its set to store the user ID, the card contents, and the login time all as separate item fields. You retrieve the full session with edgegetall and set a 30-minute ETL with expire. And for the leaderboard using the sorted set, you create a key like leaderboard game :456 and add players with their scores using zadd. To get the top 10 players, you use zrev range from 0 to 9. To check any individual player's rank, you use the zrank command. Now let us talk about what happens when caching goes wrong. This is important because when caching fails, it does not just fail to help, it can make things worse than having no cache at all. There are 3 failure modes every system designer should know. The first is cache stampede, also called thundering herd problem. Here's the scenario. Let's say a popular cache entry expires, say a celebrity's profile hits its TTL, and then 10,000 concurrent requests arrive from the same key. All 10,000 requests, they see a cache miss. All 10,000 query the database simultaneously. Now the database will get overwhelmed, and then you will see a cascading failure. Walking through the timeline, at time 0, the cache entry expires. At 0.1 milliseconds, request 1 caches checks the cache, gets a miss, and then queries the database. At 0.2 milliseconds, request 2 does the same. At 0.3 milliseconds, request 3 does the same. By 10 milliseconds, all 10,000 requests are hitting the database simultaneously. By 50 milliseconds, the database connection pool is exhausted and queries are failing. So now one cache miss on one key has just took down the entire database. Now the second failure mode is cache penetration. This is when the requests come in for data that does not exist in the database at all. The cache will never have the data because there is nothing to cache. Every single request becomes a cache miss followed by a database miss. And an attacker can exploit this intentionally by querying millions of non-existent IDs. For example, a request for user ID, let's say a very big number, which does not exist. It is a cache miss, then a database miss, and then a 404 response. By that, requests hit the database every single time. So at 1000 such requests per second, that is 1000 unnecessary database queries per second as well. So now let's talk about the third failure mode, which is the cache avalanche. This happens when a large number of cache entries expire at the same time, causing a massive spike in cache misses. The database suddenly receives all the traffic and the cache was absorbing and cannot handle the spike. The system degrades or crashes now, and the typical cause is that the setting the same detail for all entries that were loaded at the same time. For example, if you warm your cache at the startup and give every entry a read of 300 seconds, All of them expire exactly at 300 seconds later all at once. To prevent these failure modes, let us go through the mitigations for each one. For cache stampede, these are two solutions. The first is locking, also called a mutex. When a cache miss happens, the first request acquires the lock, fetches the data from the database, populates the cache, and releases the lock. All the requests that arrive during that time wait for the lock, and once it is released, they read from the cache instead of hitting the database. In the code, the function first tries to get the value from the cache. If it is a miss, it tries to acquire a lock using a set command with an NX flag, which means set only if it not exists, and an NX of 5 seconds so the lock auto expires. If the lock is acquired, it queries the database, stores the result in the cache, reads the lock, and returns. If the lock was not acquired, meaning another request is already fetching the data, it waits 50 milliseconds and then it reads from the cache. The second solution is early refresh. So for example, instead of the waiting for the TTL to expire, he refreshes the cache entry before it expires. If the TTL is 300 seconds, he refresh at 270 seconds. The entry never actually expires, so the stampede never happens. So now for cache penetration, there are also two solutions. The first is to cache null results. If the database results no result for a key, you cache a null or empty value with a short ETL. For example, setting user with a very large number for non-existent key to null with a 60-second ETL. For the next 60 seconds, request for that non-existent user will hit the cache and get the null result instead of failing through the database every single time. The second solution is a Bloom filter. Before checking the cache or the database, you check a Bloom filter. A Bloom filter is a probabilistic data structure that can tell you definitely does not exist or might exist. If the Bloom filter says the key definitely does not exist, you skip the lookup entirely. Bloom filters use minimal memory, about 1 byte per entry, and have a 0 of 1 lookup time. For cache avalanche, there are three solutions. The first is randomized TTL. Instead of setting TTL equals 300 for all keys, you set TTL equals 300 plus a random value between 0 and 60. This way, entries expire at different times, spreading the load across a 60-second window instead of all at once. The second is the staggered warm-up. So when restarting the cache, you do not load everything at once. Instead, you load entries gradually over 5 to 10 minutes. And the third is multi-layer caching. If the application cache misses, you fall back to the secondary cache or the CDN cache before hitting the database, which absorbs some of the spike. Now let us look at how caching works at real-world scale, because these numbers really put everything we have discussed into perspective. Netflix has over 200 million subscribers. Their caching architecture uses EVCache, which is based on Memcached, as a distributed caching layer. They perform approximately 3 trillion cache operations per day. The cache hit rate for user profiles and content metadata is above 99%. They run over 1,000 cache nodes across multiple AWS regions, and the impact is pretty staggering. Without caching, Netflix would need approximately 100,000 database servers. With caching, they would need roughly 1,000 database servers. That is a 99% reduction in database infrastructure. Now, if you look at Instagram, which has over 2 billion users, they use both Redis and Memcache for different use cases. Their feed cache stores pre-computed feeds per user in Redis. Session data goes into Memcache. They run hundreds of cache instances for their feed caching strategy. Specifically, the cache key is the feed : followed by the user ID, and the value is a sorted set of post IDs, and the TTL is 5 minutes, and the hit rate is about 80%. Loading a feed from the cache takes 50 to 100 milliseconds, while loading from the database takes 300 to 500 milliseconds. Now, there are some important lessons from these production deployments. First, cache hit rate is the most important metric. You should track it, alert on drops, and optimize it relentlessly. Second, you should be using different caches for different data. Redis for complex data structures and Memcache for simple key value lookups. Third, cache as close to the user as possible. Browser cache is the fastest, then CDN, then application cache, then database cache. Fourth, monitor cache memory and eviction rate. A high eviction rate means your cache is too small. And fifth is that you should warm up the cache before traffic hits it. Pre-populate after deployment so the cache restarts, so that the users do not have to experience a cold cache. Now, before we close this section, let us go over the 5 most common interview mistakes people do, when they are discussing caching in system design interviews. Understanding these will immediately improve the quality of your answers. Mistake number one is that some people say that okay, we'll cache everything. Caching has costs, like for example, memory, invalidation, complexity, staleness. So not everything can be cached. A better answer would be that okay, candidates should say something like, I'll cache the user profile and feed data because they are read heavy with a 100 to 1 read to write ratio, and slight staleness is kind of acceptable. So, I will not cache the payment status because that must be consistent. Mistake number two is not mentioning cache invalidation. Saying that, okay, let's say your candidate says, we'll just use Redis to cache without it explaining how, stale data is handled shows incomplete thinking during the interview. So please don't do that. A better answer from the candidate would be, okay, that, we'll use cache aside with a 5-minute TTL. On profile update, we'll invalidate the cache key immediately. The TTL acts as a safety net if the invalidation fails. Mistake number three is ignoring cache failure scenarios. Not considering what happens when the cache goes down is a gap. A better answer from the candidate would be that okay, if Redis goes down, we fall back to the database reads. Response times will increase from 1 to millisecond to about 50 milliseconds, but the system will at least remain functional. We'll use Redis, Sentinel for automatic failover to minimize cache downtime. And the mistake number four is using cache for data that needs strong consistency. Caching bank balances or inventory counts with a 5-minute TTL is a very big red flag. A better answer would be like, okay, for inventory counts, we read it directly from the database within a transaction. Serving a stale inventory count would be, overselling, so we should not be do that. And mistake number five is not specifying TTL values. Saying in an interview that, okay, we'll cache it with a reasonable TTL is too weak. A better answer would be giving specific numbers like, okay, feed cache with 5-minute TTL, user profile 15-minute TTL, configuration data 1 hour TTL, session 30-minute TTL, and so on. Specific numbers will show your practical experience in the interviews. Summary of everything we have covered. We started with why caching works, and the answer was the 80-20 rule. A small amount of data serves the majority of requests. Then we covered the cache hits and misses, where a hit returns from the cache is about 0.5 milliseconds, and a miss falls through the database at about 50 milliseconds. Then we walked through the 4 caching layers, which is browser, CDN, application cache for Redis, and database query cache. We covered 3 caching strategies: cache aside, where you read from the diff cache first and populate on a miss, which is the most common pattern; write through, where you write to the cache and database together for a strong consistency; and write behind, where you write to the cache first and flush to the database later for fast writes with a data loss risk. We covered LRU eviction, which evicts the least recently used entry when the cache is full; TTL, which provides automatic expiry after a set duration; and cache invalidation using TTL-based, event-based, or hybrid approaches, with hybrid being the most common in production. Well, we also cover Redis as a primary, like application level cache, supporting strings, hashes, lists, sets, and sorted sets. And we also covered the 3 failure modes: cache stampede, where many requests for the same expired key overrun the database; cache penetration, where requests for non-existent data bypass the cache every time; and cache avalanche, where the mass expiry causes a sudden database load spike. And here are the key numbers to remember. Redis get and set latency is about 0.1 to 0.5 milliseconds. Redis throughput is 100,000 to 500,000 operations per second per node. Your target cache hit rate should be about 80% or higher, with production systems often achieving 90 to 99%. Typical TTLs are 1 to 15 minutes for application cache and hour to days for CDN. Cache versus database speed is roughly 10 to 100 times faster, and Netflix, they achieve a very high cache hit rate. In section 5, we talked about horizontal scaling and how we add more servers to handle more traffic. But we left an important question unanswered. If you have 10 servers running your application, how does the client know which one to talk to? And what happens when one of those servers goes down? This is exactly the problem that load balancers solve, and that is what the section 7 here is all about. A load balancer is a component that sits between your clients and your server fleet. Its job is to receive every incoming request and decide which backend server should handle it. Without a load balancer, the client has to know the IP address of a specific server. If that server goes down, the client will get an error. If that server is overloaded, the client will get slow responses. And if you want to add or remove servers, you would have to change the client configuration, which is not practical at any real scale. With the load balancer, the client only knows one address, the address of the load balancer itself. The load balancer picks a healthy, available server. Servers can be added and removed behind the load balancer without any client ever knowing, and traffic gets distributed evenly across all of your servers. In this section, we're going to cover what a load balancer does and where it sits in your architecture. Then we'll go through the major load balancing algorithms like round robin, least connections, and IP hash. We'll also look at the difference between layer 4 and layer 7 load balancing, and then we'll cover health checks and how load balancers detect failures. We'll also talk about load balancer redundancy because the load balancer itself can become a single point of failure. And finally, we'll cover global server load balancing, which is how traffic is distributed across data centers in different parts of the world. So the key idea for this section is pretty straightforward. Load balancing is what makes horizontal scaling actual work in practice. Without it, adding more servers does not help you. Let us start by looking at what a load balancer actually does. Load balancer does more than just distribute traffic. It is responsible for a set of functions that keep your system reliable, secure, and performant. The first is traffic distribution. This is a core job. The load balancer spreads incoming requests across multiple backend servers so that no single server gets overwhelmed. The second is health monitoring. The load balancer continuously checks whether each backend server is healthy, and if a server goes down, the load balancer stops sending traffic to it automatically. The third is TLS termination. Instead of every backend server handling the overhead of decrypting HTTPS traffic, the load balancer can decrypt it once at the edge and forward plain HTTP to your backend servers. This offloads a significant amount of CPU work from your application servers. The fourth is session persistence, sometimes called sticky sessions. In some cases, you want requests from the same user always go to the same server. The load balancer can be configured to do this as well. The fifth is connection management. The load balancer maintains the persistent connections to your backend servers, which reduces the overhead of creating new TCP handshakes for every request. And the sixth is DDoS absorption. The load balancer can also act as a shield, absorbing connection floods before they ever reach your application servers. Now let's look at how this works in practice. Imagine that you have a load balancer sitting at lb.youtube.com with public IP of 203.0.113.1, and behind it you have 4 servers. Servers 1, 2, and 3 are healthy, and server 4 is unhealthy. When client 1 sends a request, the load balancer routes it to server 1. Client's 2 request goes to server 2, and client's 3 requests will go to server 3. And server 4 gets no traffic at all because the load balancer has directed that it's unhealthy. From the client's perspective, the client connects to lb.youtube.com. The client has no idea how many backend servers exist, so the client does not even know which server handled the request. From the server's perspective, the servers have private IPs in the range of, let's say, 10.0.1.x. They are not exposed to the internet, and they only receive traffic from the load balancer, and they can be added or removed without any downtime. So in terms of technologies, there are several common options. Nginx is the most common general purpose software load balancer and is open source as well. HTTP proxy is also another open source option known for high performance TCP and HTTP load balancing. On the managed service side, AWS has ALB and NLB, Azure has the Azure load balancer, and Google Cloud has its own Google Cloud load balancer as well. For enterprise on-premise deployments, F5 Big IP is a well-known hardware and software option. For most modern applications, you will be using either Nginx or a managed cloud load balancer. Now that we understand what a load balancer does, let us look at where it actually sits in the production architecture. A production architecture does not just have one load balancer. It typically has load balancers at multiple layers, and understanding these layers is important both for building real systems and also for your system design interviews. The first layer is the edge layer, which is the global load balancer. This is DNS based, and its job is to route the user to the nearest geographic region. If a user is, let's say, in Mumbai, the global load balancer routes them to the Mumbai data center. If the user is in London, they go to the London data center. We'll cover this in much more detail in the section where we talk about GSLB. The second layer is the regional load balancer. This is an L7 HTTP or HTTPS load balancer that sits within a region and distributes traffic across your application servers. This load balancer most people think of when they hear the term. Technologies here include Nginx, AWS ALB, and HTTP proxy. The third layer here is the internal load balancer. So in microservices architecture, your application services, they need to communicate with each other like let's say user service, a post service, or a feed service. The internal load balancer handles the service to service routing. Technologies here include Envoy, internal NLBs, and service mesh solutions. So now the flows, it kind of works like this. A client makes a request, the global load balancer routes them to the nearest region, the region load balancer routes them to one of the application servers in that region, and when the application server needs to call another microservice, the internal load balancer routes that call to the appropriate service instance. In a system design interview, you typically draw one load balancer between clients and application servers, which is the regional layer. That is perfectly fine for most interview scenarios, but if the interviewer asks you about global distribution, you should be mentioning the global DNS base layer. And if they ask you about microservices communication, you should be mentioning the internal layer as well. Okay, now let us talk about the load balancing algorithms, starting with the simplest one, which is round robin. Round robin is the simplest load balancing algorithm. Requests are distributed to servers sequentially, one after another, and after the last server gets a request, it cycles back to the first server. So let's say if you have three servers, A, B, and C. Request 1 will go to server A, request 2 will go to server B, request 3 will go to server C, request 4 will go to server A, and then the cycle continues. Each server gets exactly 1/3 of the traffic. Round robin works well when all servers have identical hardware specs, when all requests take roughly the same time to process, and when you do not need session affinity. In those conditions, it gives you perfectly even distribution with zero complexity. But then, round robin fails as well sometimes. So for example, when your servers are not equal, then it's not an ideal scenario. Now let's say a server A has 16 vCPUs and 64 GB of RAM. Servers B and C have 4 vCPUs and 16 GB of RAM. Now round robin will give each server 33% of the traffic, but server A has 4 times the capacity of server B and C. So server A ends up underutilized while server B and C are overloaded. This is a real problem in production because server fleets are almost never perfectly homogeneous. You might have older and newer machines or different instance types from the cloud provider. Now this is exactly where the weighted round robin comes in. Weighted round robin assigns a weight to each server proportional to its capacity. A higher weight means the server gets more traffic. So in our example here, you would give server A a weight of 4 and servers B and C and each a weight of 1. Now out of every 6 requests, server A gets 4 of them, server B gets 1, and server C gets 1. Requests 1 through 4 will go to server A, request 5 will go to server B, and request C will go to server C. And then the cycle restarts. In this way, server A will handle 67% of the traffic, which matches its 4 times the capacity advantage over the other servers. So the takeaway here is that round robin is the default starting point because of its simplicity, and weighted round robin is a natural extension when your servers have different capacities. But both of these algorithms, they do share a limitation. They do not account for what is actually happening on each of the server right now. Now least connections take a different approach from round robin. Instead of distributing requests in a fixed sequence, it routes each new request to the server with the fewest active connections at that moment. This makes it dynamic. It responds to what is actually happening on each server in real time. Now let us walk through why this matters. Imagine server A has 12 active connections, server B has 3, and server C has 8. A new request arrives. Least connections approach will now send it to server B because server B has the fewest active connections. Now let us see why this is better than the round robin approach where requests have variable processing times. With round robin, suppose 3 requests arrive. Request 1 goes to server A, request 2 will go to server B, and request 3 will go to server C. Now request 1 is an image upload that takes 10 seconds. Request 2 and 3 are API calls that complete in 50 milliseconds. When request 4 arrives, round robin will send it to server A, but server A is already busy processing that image upload. Meanwhile, servers B and C are completely idle. With least connections approach, the request 4 would ideally go to server B, which has 0 active connections, and that is a much better distribution. Now let us talk about IP hash. IP hash route requests, from the same client IP to the same server every time. It does this by hashing the client's IP address and using modulo arithmetic. The formula is server index equals hash of client IP modulo the number of servers. So the client, let's say 192.168.1.1, always goes to server A. Client 192.168.1.2 will always go to server C. And client 192.168.1.3, let's say they'll all goes to server B. Every request from the same IP address will hit the same server. Now these are the two main key use cases for IP hash. The first is server-side caching. So if server A caches the data for its assigned clients and a client always goes to server A, the cache hit rate should be very high. If the client bounces between servers with round robin, each server has a cold cache for that client. The second use case is the stateful applications, typically legacy systems where the application stores sessions data in local memory instead of in external storage like Redis. In those cases, the client has to go to the same server to find their session. But IP hash also has a very notable problem. Distribution can be very uneven. Some IP ranges produce far more traffic than others. If a corporate office with one public IP sends, let's say, 10,000 requests, one server will get 10,000 of them. And the better long-term solution for session management is always stateless design with an external session storage, which we covered back in section 3. IP hash for session affinity should be treated as a workaround for legacy systems, not as a default choice. Now let us look at all of these algorithms side by side. Now let us compare all of the load balancing algorithms we have covered, plus 2 more. A round robin gives equal distribution with the lowest complexity. It is best for identical servers with uniform request costs. A weighted round robin gives distribution proportional to assigned weights with low complexity. It is best for mixed server capacities. Least connections approach gives dynamic distribution based on the current load with medium complexity. It is best when request durations vary significantly, like when you have a mix of file uploads and quick API calls. IP hash approach gives deterministic distribution by client with low complexity. It is best for session affinity and server-side caching. Least response time gives dynamic distribution that favors the fastest server with high complexity. It is best when server performance varies and you have the monitoring infrastructure to measure response times. And random gives a statistically equal distribution with the lowest complexity. It is best for very large server fleets where simplicity matters more than precision. Now in terms of a decision framework, the default choice should be round robin or weighted round robin if your servers have different capacities. This works for about 90% of the use cases. It is simple to configure and simple to understand. You should choose least connections approach when request processing times vary significantly, when some requests are fast API calls and others are slow file uploads, or when your servers handle live, long-lived connections like WebSockets or streaming. You should choose IP hash when you need session affinity without an external session store or when servers maintain local caches that benefit from consistent routing. And you should choose at least the least response time when the server performance varies due to different workloads and you have the monitoring infrastructure to actually measure response times. For interviews and the most system design interviews, for example, saying something like round robin load balancing is pretty sufficient, but if the interviewer presses you for more details, you should mention that you would switch to least connections if the request durations vary significantly or weighted round robin if the servers have different capacities. That level of depth signals that you understand the trade-offs without overcomplicating the discussion. Now that we understand the algorithms, let us talk about something equally important. Where in the network stack does the load balancer actually operate? So now this brings us to layer 4 versus layer 7 load balancing. Load balancers can operate at different layers of the network stack, and the layer determines what information the load balancer can see and use for routing decisions. A layer 4 load balancer operates at the transport layer, which is the TCP layer. It can see the source IP address and the port, the destination IP address and the port, and the TCP or UDP protocol. That's it. It cannot see the HTTP method, whether it's get or post. It cannot see the URL path like API users versus API/feed, and it cannot see HTTP headers like cookies or authorization tokens. And it also cannot see the request body as well. Its routing decision is based entirely on IP address, port number, and simple algorithms like round robin or least connections. When it forwards traffic, it passes raw TCP packets to the backend server without inspecting or modifying the content. This makes it very fast because there is no HTTP parsing overhead. Now, at a layer 4, layer 7 load balancer, it operates at the application layer, which is the HTTP layer. It can see everything layer 4 sees, plus the HTTP method, the URL path like let's say /API/user/123, HTTP headers including host, authorization, cookie, and content type, and also query parameters like let's say page equal to 2 or sort equal to newest. And it can also see the request body including the JSON payloads. This means that the layer 7 can make much more intelligent routing decisions. It can route based on URL path, sending APIs/user request to the user service and sending let's say a request for endpoint API/feed request to the feed service. It can route based on HTTP headers as well. For example, routing based on API version or an AP testing group. It can do sticky sessions based on a session ID and a cookie, and it can handle different content types differently as well. The key difference in how they forward traffic is that a layer 7 load balancer terminates the HTTP connection from the client and parses the request and then makes a new connection to the backend. This means that it can modify headers, rewrite URLs, and add new headers before forwarding. A layer 4 load balancer just passes the packets through without understanding what's inside them. Now let us now look at the specific trade-offs to understand when you should choose each one. Now let us compare layer 4 and layer 7 across several dimensions. In terms of speed, layer 4 is faster because it does not need to parse HTTP. In terms of throughput, layer 4 can handle millions of connections per second, while layer 7 handles hundreds of thousands per second. For routing intelligence, layer 4 can only route based on IP and port, which is basic, while layer 7 can route based on URL, headers, cookies, which is pretty advanced. For TLS termination, layer 4 can either pass through or terminate, while layer 7 terminates and inspects. Layer 4 cannot do content-based routing or URL rewriting, while layer 7 can do both. Both support WebSockets, but layer 4 does it via pass-through, while layer 7 requires upgrade handling. And layer 4 is generally lower cost than layer 7. So now let's talk about when we should be using layer 4 and when we should be using layer 7. You should be using layer 4, for high throughput TCP services like database proxies or game servers when you do not need content-based routing, for internal load balancing between services, and where the raw speed matters, and when your backend servers handle the TLS themselves. AWS NLB, the network load balancer, operates at layer 4. And when should you use layer 7? So you should use it for HTTP and HTTPS web applications, which is the most common case. For microservices routing, where you need path-based routing to different services. For A/B testing, where you want to route 10% of the traffic to a new version based on a header. For API gateway functionality like auth rate limiting and URL rewriting. AWS ALB, the application load balancer, operates at layer 7. Nginx also operates at layer 7. In practice, most production web applications use layer 7 load balancers because they need content-based routing. The performance difference between layer 4 and layer 7 is irrelevant for most workloads. At extreme scale, when you're dealing with millions of connections per second, you might use layer 4 for the first hop to distribute raw TCP connections, and then layer 7 behind it for intelligent routing. But for the vast majority of systems, layer 7 is the right choice. Now that we understand how load balancers route traffic, let us talk about how they know which servers are actually healthy enough to receive that traffic. This brings us to health checks. A load balancer has to know which backend servers are healthy and which are not. A healthy server can serve requests. An unhealthy server might be down, overloaded, or malfunctioning. Health checks are periodic probes that the load balancer sends to each server to verify its status. Now let us walk through how this works with a concrete configuration. The load balancer is configured with the health check endpoint of get /health. The interval is 10 seconds, meaning it checks every 10 seconds. The timeout is 5 seconds, meaning if the server does not respond within 5 seconds, that check is considered a failure. The healthy threshold is 3 consecutive successes, meaning a server must pass 3 checks in a row before being marked as healthy. And the unhealthy threshold is 2 consecutive failures, meaning 2 failed checks in a row marks the server as unhealthy. So every 10 seconds, the load balancer sends get slash health to every server. So server A returns, let's say 200 OK healthy. Server B returns 200 OK. That means that's healthy as well. Let's say server C times out and there's no response. And 10 seconds later, server C times out again. That is 2 consecutive failures, which means the unhealthy threshold. Server C is now marked unhealthy and removed from the rotation. No more traffic will be going to server C. Now there are different types of health checks. The simplest is a TCP health check, which just checks whether it can open a connection to the server on a specific port like 8080. Then there is an HTTP health check, which sends an actual HTTP request and checks whether the endpoint returns a 200 status code. Then there is a deep health check, which goes further and checks whether the application is fully functional, including its database connection, cache connection, and disk space. And finally, there are custom health check-in points, that implement application-specific logic like checking queue depth, memory usage, or error rate. Now, this brings up an important distinction between shallow and depth health checks. A shallow health check, typically at the slash health endpoint, simply returns 200 OK. All it confirms is that the process is running. It does not confirm that the application can actually serve real requests. A deep health check typically checks at, let's say, slash health slash deep, which will be doing much more. It checks the database connection, checks the Redis connection, checks that disk space is above 10% free, checks that memory usage is below 90%, and only returns 200 OK if all those checks pass. If any of the checks fail, it returns 503 service unavailable. The trade-off is that for shallow checks is that they are fast and have low overhead, but they do miss real problems. The deep checks, they catch real issues, but they are much more expensive to run. The common approach in production is to run shallow checks every 5 seconds and deep checks every 30 seconds. That way you get fast detection of servers that are completely down and periodic detection of servers that are running but not truly healthy. Now let us talk about server recovery. When server C comes back after a restart or fix, the load balancer does not immediately send traffic to it. It needs to pass the healthy threshold first. So the load balancer sends get slash health and the server C returns 200 OK, that is the first success. Then another check 200 OK, second success. Then another 200 OK, third success. And then the threshold has met. Now server C is marked healthy and added back to the rotation. So why require multiple consecutive successes? To prevent flapping. A server that responds once and then fails again should not receive real traffic. Requiring 3 consecutive successes ensures that the server is stable, healthy, before it starts handling any user requests. Now this is a great mechanism for keeping backend servers healthy, but there is an important question we have not addressed yet. What happens if the load balancer itself goes down? The load balancer itself is a single point of failure. If it goes down, all traffic stops, even if every single backend server is perfectly healthy. Production systems solve this with redundant load balancers, and there are 2 main approaches. The first is the active-passive failover. In this setup, you have 2 load balancers that share a single virtual IP or VIP. Let us say the VIP is 203.0.113.1. The active load balancer then handles all the traffic. The passive load balancer sits in standby and monitors the active one by sending heartbeats every 1 to 2 seconds. If the active load balancer stops responding and the heartbeat times out, the passive load balancer takes over the virtual IP. Traffic automatically routes to the new active load balancer. Failover time is typically 5 to 30 seconds. The client sees the same IP address throughout. The failover is invisible to the client. The second approach is active-active. So in that case, in this setup, both load balancers handle traffic simultaneously. DNS returns both IPs or a hardware device distributed between them. Active-active has several advantages over active-passive. Both load balancers are utilized, so there is no idle standby wasting resources. You get higher total throughput when you have 2 load balancers handling traffic instead of 1. And failover is faster because the other load balancer is already warm and serving traffic. ActiveAct is used by AWS ALB, which is managed in multi-availability zone, Cloudflare and other large-scale deployments. In practice, if you are building, on a cloud provider, you should almost certainly use a managed load balancer. So, for example, AWS ALB and ALB, for example, are deployed across multiple availability zones. They provide automatic failover if one availability zone goes down. They auto-scale to handle our traffic spikes as well, and there is no single point of failure. And the cost is roughly $20 per month plus about $0.008 per GB process, which is very reasonable for what you get. The key takeaway is that for most systems, using a managed load balancer is the right choice. Building your own redundant load balancer setup is only necessary for extreme customization needs that a managed service cannot satisfy, and it's not needed for most companies. So far, everything we've talked about has been with this single data center or region. But what happens when your users are spread across the globe? This is where GSLB comes in. Server load balancing, or GSLB, distributes traffic across data centers in different geographic regions. While a regional load balancer distributes traffic within a data center, GSLB operates at a global level using DNS. Let us walk through how this works. A user in Mumbai types, let's say, youtube.com. Their DNS query will reach the YouTube's authoritative DNS server. The DNS server checks the user's location using IP geolocation. Based on that location, it returns the IP address of the nearest data center. So the Mumbai user gets the IP address of the Mumbai data center. Let's say it's 34.93.150. Similarly, a London user gets IP address of the London data center. A Virginia user will get the IP address of Virginia data center. The result is that each user connects to the closest data center. Latency for Mumbai users should be 5 to 20 milliseconds instead of 100 to 300 milliseconds if they had to do cross-continent connection to the London data center. Now there are several routing policies you can configure with the GSLB. The first is the geographic routing, which sends users to the nearest data center by location. This is best for latency sensitive applications. The second is latency based routing, which sends users to a data center with the lowest major latency. This is useful when geographic proximity does not necessarily equal the lowest latency because network paths can be unpredictable. The third is weighted routing, which splits the traffic by percentage across regions. This is useful for gradual migration to a new region for A/B testing. And the fourth is failover routing, which sends all traffic to a primary region and only switches to secondary region on failure. This is used for disaster recovery. Now let us talk about what happens, when a data center actually goes down. In normal operation, let's say Mumbai users, they go to Mumbai data center and London users go to London data center. If the Mumbai data center goes down, GSLB detects the failure through the health checks. DNS is updated so that Mumbai users can now get routed to the Singapore data center, which is the next closest. The TTL, or time to live, of one of the DNS records determine how quickly clients pick up the change. With a TTL of 60 seconds, most users reroute within 1 to 2 minutes. With a TTL of 300 seconds, it takes 5 to 10 minutes. This is why DNS TTL matters for failover. A lower TTL means faster failover, but it also means that more DNS queries hitting your DNS infrastructure. You need to balance failover speed against DNS query volume. Now, in terms of technologies, the major options are Route 53 from AWS, which supports geolocation, latency-based, and weighted and failover routing. Azure Traffic Manager for Azure is another option, and Cloud DNS from Google Cloud and Cloudflare DNS are also major technologies and options that can be used. So that covers the complete full picture of load balancing, from algorithms to layers to health checks, redundancy to global distribution in this section. Now let us look at the most common mistakes engineers make when discussing load balancing in system design interviews. Now let us go through 4 common mistakes people make when discussing load balancing in system design interviews. The first mistake is forgetting the load balancer entirely. You draw a direct line from client to a single server with no load balancer in between. The problem here is that you have a single point of failure and no path to do horizontal scaling. Even if you only draw one server behind the load balancer, you should always include a load balancer between clients and application servers. It signals to the interviewer that you're designing for scalability from the start. The second mistake is not explaining what happens when a server fails. For example, if you say in the interview that okay, we have 3 servers behind a load balancer, and then the interviewer asks, okay, what happens if the server 2 goes down? A not good answer will be okay, the server system degrades. Much better answer will be the load balancer will detect the failure via health checks within 10 to 30 seconds, remove the server 2 from the rotation, and distributes this traffic to server 1 and 3. User experience no ideally downtime, and once server 2 recovers and passes 3 consecutive health checks, it is added back to the rotation. That answer demonstrates that you understand health checks, failure detection, and recovery, which is exactly what the interviewer is looking for. Now, the third mistake is actually using sticky sessions as a default. For example, if the candidate says, okay, we'll use IP hash so each user goes to the same server. The problem of saying that in the interview is that it implies your servers are stateful, which is a very big red flag. A better answer to say in the interviews is like, okay, our servers are stateless, all session data is stored in Redis, any server can handle any request, and we use round robin for event distribution. Stateless servers with an external session store should be the default design. IP hash and sticky sessions should only come up if you have a specific justified reason for them. And the fourth mistake is not addressing load balancer redundancy. Let's say the interviewer asks you in the interview that, okay, what if the load balancer itself goes down? A weak answer would be that, okay, ideally you should not go down. And if you don't prepare for this answer, you might go blank. So the better answer is actually we use active passive failover. So with a shared virtual IP, if the active load balancer fails, the passive takes over within 10 to 30 seconds. In practice, we would use a managed service like AWS ALB, which handles redundancy automatically across availability zones. And if you give that answer in the interview, that will show to the interviewer that you understand the load balancer itself is like a potential single point of failure, and you already know how to address it. So these are very specific, concrete responses that demonstrate depth of understanding. Now let us close out this section with a summary. Let's recap everything we have covered in section 7. We start with the load balancer's role, which is to distribute traffic, detect failures, and terminate TLS. We talked about placement and how production systems have load balancer at 3 layers: the edge for global routing, the regional layer for HTTP distribution, and the internal layer for service-to-service communication. We covered the core algorithms as well. For example, round robin for equal distribution has the simplest starting point, weighted round robin for when servers have different capacities, least connections for when the request durations vary, and IP hash for when you need the same client to always reach the same server. We also covered layer 4 load balancing for fast TCP level routing without content inspection, and layer 7 load balancing for HTTP aware routing by URL, header, and cookies. We also covered health checks for both shallow and deep, but for detecting unhealthy servers, and then we also covered redundancy through active passive and active setups to eliminate the load balancer as a single point of failure. And then we covered the GSLB for DNS-based routing to the nearest data center globally. Now here are the key numbers that worth remembering. Health check intervals are typically 5 to 30 seconds. The unhealthy threshold is ideally 2 to 3 consecutive failures. The healthy threshold is 3 consecutive successes. Active passive failovers take 5 to 30 seconds. A managed load balancer costs roughly $20 per month plus per GB charges. Layer 4 can handle millions of concurrent connections per second. Layer 7 can handle hundreds of thousands of requests per second. So back in section 2, we talked about a fundamental constraint, which is the speed of light in fiber optic cable is approximately 200 kilometers per second. And a round trip from Mumbai to San Francisco will take a minimum of about 136 milliseconds in theory and 200 to 400 milliseconds in practice. That is just physics. No amount of code optimization, no amount of server tuning, nothing you can do at that application layer can change the speed of light. So now the question becomes, okay, if you cannot make the data travel faster, what can you do? The answer is that you move the data closer. This is what a content delivery network does. A CDN places copies of your content on servers distributed around the world so that the users fetch the data from location nearby instead of crossing continents to reach your origin data center. Let us make this more concrete. Think about YouTube. YouTube's origin servers are in the United States. Without a CDN, a user in Mumbai who requests a video thumbnail has to send that request all the way to US and wait back for the response all the way to come back. That round trip takes about 300 milliseconds just for the network before any processing ever even begins. And a single page does not load a single asset. A page with 50 assets, every image, every CSS file, every JavaScript file, each one pays that latency penalty. Even loaded in parallel, you are looking at painfully slow experience. Now with the CDN, the same video thumbnail is cached on an edge server right there near your city. So a request that goes from the user, let's say, to the Mumbai edge server and back, the round trip will just be about 10 to 20 milliseconds. So the difference will be enormous. And if we talk about the scale of the CDN infrastructure today, it's massive. Cloudflare operates in over 300 cities with over 209 like Tbps of capacity, which is quite huge. Akamai has over 4,000 locations with over 300 Tbps. AWS CloudFront has over 450 points of presence with over 150 Tbps. Azure CDN has 190 locations, and Fastly has over 90 locations with over 260 Tbps. These are some of the largest distributed networks ever built, and they exist for one reason: to get content physically closer to the people who need it. In this section, we are going to cover CDN architecture and how the request flow works, and the difference between push and pull CDNs, cache control, and invalidation, and also the CDN cost structure and when a CDN is actually unnecessary. So let us get started. Okay, now let us talk about the two types of servers that make up a CDN. The first is the origin server. This is the actual server, the one where the original content lives. It could be your application server in US East 1, it could be your object storage in like a AWS S3 or Azure Blob, or it could be your database. The origin is the source of truth. The second is the edge server, also called as point of presence or POP. These are CDN servers distributed around the world that cache copies of your content. There might be one in Mumbai, might be one in London, might be one in Tokyo, might be one in Sao Paulo. When let's say a user in India makes a request, they hit the Mumbai edge server. When a user in the UK makes a request, they hit the London edge server. Each edge server serves users in their geographic region. When an edge server has content the user is requesting, that is called a cache hit. The edge server serves it directly and the user gets a response in 10 to 30 milliseconds. When the edge server does not have the content, it is called a cache miss. The edge server then has to go all the way back to the origin to fetch it and cache it locally and then serve it to the user. The first request is slower, but every subsequent request from that region is fast. There are two or more terms you should know. The first is TTL, which stands for time to live. This is how long the edge servers will keep a cache copy before it considers it stale, and then it will refresh from the origin. The second is the purge or invalidation, which is when you manually remove the cache data from all the edge servers because something changed or you cannot wait for the TTL to expire. Now, not everything actually should be cached on a CDN. Static images like profile photos and post images are excellent candidates, and they should have TTLs of hours in 2 days. CSS and JavaScript files are also great candidates, especially when you use version file names, let's say like styles.abc123.css, because you can set TTLs of days to weeks, and the file name changes whenever the content changes. Videos, pre-recorded video content should be cached with TTLs of days to months. HTML pages are sometimes cacheable as well if they are mostly static like landing pages or blog posts with details in minutes range. API responses are also rarely cached, so only when that they are public and non-personalized data with very short details of seconds to minutes. And then there's personalized content like let's say user specific feed or dashboard that should never be cached on a CDN because it is different for every user. The key takeaway here is that CDN is essentially a globally distributed cache layer and the rules of caching apply. You cache what is read heavy, rarely changes, and is the same for many users. And that is exactly what we are going to see when we look at how the request flow works in the next slide. And this is exactly where the CDN request flow comes in. Let us walk through what actually happens when a user in Mumbai requests a resource like a YouTube thumbnail. Step 1 is DNS resolution. The user's browser needs to resolve cdn.youtube.com due an IP address. But this is not normal DNS lookup. The CDN's DNS server uses geolocation to look at where the request is coming from and returns the IP address of the nearest edge server. So a user in Mumbai gets the IP of the Mumbai edge. A user in London gets the IP of the London edge server. This is how the CDN routes users to the closest server. Now step 2 is the connection to the edge server. The user's browser connects to that edge Mumbai server because it geographically nearby. This connection takes about 10 to 20 milliseconds. Step 3 is the edge cache check, which is the edge server looks in the local cache and asks, okay, do I have the specific file cache or not? But here there are two paths. Path A is the cache hit, and for popular content that happens over 90% of the time. The edge server has a file, the DTL is not expired, and the edge server returns the image immediately. The total latency is about 10 to 30 milliseconds. Now if you look at the response headers over here, you would see a X cache, which means hit, which tells you that the content was served from the cache. You would also see an age header showing how long it has been cached, and a cache control header indicating the max age of the origin specified. Now path B is cache miss. This happens on the first request for a piece of content at a given edge location or when the cache copy has expired. The edge server does not have the file, so it fetches it from the origin. The request goes from the Mumbai edge server all the way to the origin server in the US and back. The edge server then caches the response for future requests and serves it to the user. The total latency for this first request is going to be about 200 to 500 milliseconds. In the response headers, you would see X cache as miss. Now here's the important thing to understand. After the first cache miss, all the subsequent requests from users near Mumbai are served from the edge. A popular thumbnail might be requested millions of times, but only fetched from the origin once per edge location, and that is the power of the CDN model. Now let us put concrete numbers on the difference the CDN makes. Without a CDN, latency for users on the same continent as your origin is about 50 to 100 milliseconds. Cross-continent latency is about 200 to 400 milliseconds. Now with a CDN and even with the modest 80% hit rate, the latency drops to 10 to 30 milliseconds for edge hits regardless of where the user is in the world. But the latency is only part of the story. Without a CDN, your origin service bears the full bandwidth load. At Instagram level scale, that is 200 GB per second and 100,000 queries per second. With the CDN at an 80% hit rate, your origin only handles 20% of that load. 40 GB per second and 20,000 queries per second. The CDN absorbs 80% of the traffic. And there's a cost in dimension too. Serving all the bandwidth directly from your origin costs about $18 million per month at Instagram scale. Without a CDN, that drops to roughly $5 million per month because CDN edge delivery is cheaper per GB than origin egress. We will also dig into the CDN cost in detail in a few slides. Let me walk you through a concrete example. Let's say you take the YouTube homepage without the CDN. The HTML itself comes from the origin at about 200 milliseconds. Then you have 50 static assets, images, CSS files, JavaScript files, and each one of them has to be fetched from the origin as well. Even loaded in parallel with limited connections, you are looking at literally 1 to 3 seconds total. With the CDN, the HTML still comes from the origin at 200 milliseconds because it is personalized and not yet cached. But those 50 static assets come from the nearby CDN edge at about 20 milliseconds each, so total drops to about 300 to 500 milliseconds. The difference is the 1 to 3 seconds versus 3 to 500 milliseconds, and that matters enormously. Google's research has found that 50% of mobile users abandon sites that take longer than 3 seconds to load. So CDN is not just a performance optimization, it directly impacts whether users stay or leave. And that brings us to the question of how content actually gets onto those edge servers in the first place. Okay, now let us talk about the two models for how content gets from your origin server to the CDN edge servers. The first is a pull CDN, and that is the most common model by far. In a pull CDN, content is fetched on demand. A user requests an image from the CDN edge. The edge server does not have it, so that is a cache miss. The edge server pulls the image from the origin, caches it locally, and serves it to the user. Every subsequent request from that same image at that edge is now served from the cache. The key characteristics of a pull CDN are the content only gets cached after the first request, so that first request is slower. But it's simple to set up because you just point to the CDN at the origin URL. And it is storage efficient as well because content that nobody requests never gets cached. The second model is push CDN. When in a push CDN, your application proactively uploads content to the CDNS servers before any users request it. You create or update content, your application pushes it to all the edge servers, and when the first user requests it is already there. Every request is a cache hit from the very beginning. The downside is that it's much more complex because the application has to manage the upload pipeline to the CDN. It can also waste storage if you push content that nobody ever actually ends up requesting. So, when do you choose one over other? So, push CDN is actually, should be a default for general web content, images, and videos. The first required latency penalty is pretty acceptable for, because after that one miss, everything is pretty fast. Setup complexity is low. Storage efficiency is pretty high because you only cache, what people actually request. And content freshness is handled automatically through TTL expiry. Now, push CDN is for specific cases where you need guaranteed availability on the very first request. Think firmware updates where you want every device in the world to get a fast download the moment you release. Think app binary downloads, think critical launch assets for a product launch page where millions of people will hit it in the moment it goes live and you cannot afford a cold start. In practice, the vast majority of web applications use pull CDN. Push CDN is the exception for specialized use cases. Now that we understand how content gets to that servers, now let's look at how you control how long it stays there. Now, cache behavior on a CDN is controlled by HTTP headers that the origin server send along with the response. These headers tell the CDN how long to cache content and under what conditions. The most important header is cache control. Let me walk through the three main patterns. The first pattern is cache control, public, max age equal to 86,400. Public means both the CDN and the user's browser is allowed to cache this content. Max age, which is 86,400, means the cache for 86,400 seconds, which is 24 hours. And the second pattern is cache control. So private, no cache. Private means only the user's browser can cache it, not the CDN. No cache means the browser must check with the origin server and revalidate before serving a cache copy. The third pattern is cache control, no store. This means do not cache this content at all anywhere. This is for sensitive data and personal responses. Now let us look at how you match these headers to different types of content. For static images and CSS or JavaScript files with version URLs, like for example styles.abc.css, you should set public max age equal to 315.360.0.0, which is 1 year. This is safe because the URL itself changes whenever the content changes. A new hash means a new URL, which means a new cache entry. For user uploaded photos, you should set public max age equal to 86,400, which is 1 day. The content does not change, but a moderate ETL is good safety margin. For API responses that contain the public data, you should set public / max age equal to 60, which is 1 minute. The data changes periodically, so you want a short ETL. For personalized feeds, you should set private, no store, because it's different for every user and should never be cached by CDN. And for authentication tokens, since you should also set no store because they're sensitive and they should never be cached anywhere due to security reasons. Okay, but what happens when the content changes and you cannot wait for the TTL to expire? This is where CDN invalidation comes in. Imagine your company updates its logo and the old logo is cached on over 300 edge servers around the world. You have two options. Option A is to wait for the TTL to expire, but that could be hours or days. Option B is to purge the cache URL across all edges. A CDN purge is an API call where you specify the URLs to invalidate. All edge servers delete the edge copy and the next request for that URL fetches a new content from the origin. Different providers have different purge propagation times. Cloudflare propagates in about 30 seconds globally. CloudFront takes about 1 to 5 minutes. Akamai takes 5 to 10 minutes. But there is even a better approach, which is version URLs. Instead of purging, let's say logo.v1.png, you simply upload logo.v2.png. It's a new URL, so it's a new cache entry. The old URL eventually expires on its own. No purge is needed now, and it's pretty clean and simple. This is why you see file names like styles.abc123.cs in zip production. That hash in the file name, is the version. So when the content changes, the hash changes, the URL changes, and the CDN treats it as entirely new content. So the key insight here is that the best cache invalidation strategy is to avoid needing invalidation in the first place. You should be using inversion URLs whenever you can. Now let us look at what CDN operations look like at a truly massive scale. So let us put some real numbers on this and see what CDN operations look like at Instagram scale. Instagram has 2 billion monthly active users, 95 million photos and videos uploaded every single day. The average image size after compression is about 2 megabytes, and on average, each image gets viewed about 100 times, though this varies widely from image to image. Now let's do math on daily egress without a CDN. There's about 10 billion image views per day multiplied by 2 MB per image, which gives you 20,000 TB per day. If you spread that over 86,400 seconds in a day, you get 231 GB per second of continuous bandwidth. That is physically impossible to serve from a single data center. Even if you had 10 data centers, each one would need to sustain 23 GB per second continuously. And this is why CDNs are not optional at this scale, they are mandatory. With the CDN at 80% cache hit rate, the origin only serves 20% of that traffic, which is 46 GB per second. The CDN edge network absorbs the remaining 80%, which is the 185 GB per second, distributed across hundreds of edge locations globally. No single location handles more than a small fraction of the total load. There are 5 key CDN performance metrics you should know for production systems and for interviews. The first is the cache hit rate. So the target should be above 80%, and in production you often see 90 to 99%. This is the percentage of requests served directly from the edge without going back to the origin. The second is the time to first byte or TTFB. For an edge hit, this should be under 50 milliseconds. This measures how quickly the first byte of the response reaches the server. The third is the purge propagation. This should be under 60 seconds, and this is how fast content updates reaches all the edge servers after you issue a purge. The fourth is origin offload, so this should be above 80%. This is the percentage of total bandwidth handled by the CDN rather than the origin. The fifth is availability, so major CDN providers guarantee 99.99% or higher uptime. Now these numbers give you a concrete framework for evaluating CDN performance in both production operations and system design interviews. So now let us talk about what all of this actually cost in real world cost scenarios. CDN pricing is primarily based on bandwidth, specifically the amount of data transferred from edge servers to users. At scale, CDN bandwidth is often the single largest infrastructure cost for media-heavy applications. Let me walk you through AWS CloudFront pricing, for example. For the first 10 TB per month, you pay about $0.085 per GB. For the next 40 TB, it drops to about $0.08 per GB. For the next 100 TB, you pay around $0.60 per GB, and so on. And if you have over 500 TB, you negotiate custom pricing directly with the cloud provider. Now let us see what happens. Looks like at the Instagram scale. So monthly egress through the CDN is roughly 600 petabytes, which is 600,000 TB. At a negotiated enterprise pricing of about, let's say, $0.02 per GB, that works out to $12 million per month. That sounds like a lot, but compared to serving the same traffic directly from the origin, that will be hugely expensive. At typical AWS EC2 egress pricing is about $0.09 per GB. That same 600,000 TB would actually cost you $54 million per month. The CDN actually saves you $42 million per month, which is $504 million per year. So at that scale, a CDN is not just a performance tool, it's a cost reduction tool. Edge delivery is fundamentally cheaper than origin egress. These are the 4 cost optimization strategies that are worth knowing. The first is maximizing your cache hit rate. So higher hit rate means less traffic goes back to the origin, which means lower total costs. Improving from 80% to 90% cuts your origin traffic in half. The second is, the moment you realize that, that's a huge improvement, so you should please consider that. The second point is compressing the content. Enabling gzip or throttling operation for text-based assets like HTML, CSS, and JavaScript typically gives you 60 to 80% size reduction. Smaller files means less bandwidth, which means lower cost. Third is serving appropriate image sizes. A mobile device does not need a 4K image. Use 6040px image instead and reduce the bandwidth by 50 to 75% for mobile users. The fourth is using version URLs with long TTLs. If you set styles.abc123 with a max age of 1 year, there are no unnecessary revalidation requests. So when the content changes, you change the file name and the old cache header entry simply expires on its own. This reduces the origin request to near zero for static assets. So the takeaway on the CDN cost is that it is a significant line item at scale, but it's dramatically cheaper than the alternative, and there are well-established strategies to optimize it further. Now let us talk about when you should not use CDN at all. CDN is not always the right solution, and knowing when to not use one is just as important as knowing when to use one. Adding a CDN introduces complexity. You now have a cache invalidation to think about. You have to debug cache behavior when things go wrong, and you have an additional vendor dependency. Plus, now there is a cost. For some systems, the benefits simply do not justify these trade-offs. Here are the 5 scenarios when you should skip the CDN. The first is when you have a small user base, let's say like fewer than 10,000 daily active users. Traffic is low enough for your origin to handle directly. The second is when all of your users are in one geographic region. Let's say if everyone in the same city or the same country as your servers, there is no cross-country latency to solve. The third is when your content is mostly dynamic and personalized. A CDN cannot effectively cache personalized responses because they are different for every user. The fourth is enterprise applications where users are on the corporate network and are already close to the servers. The fifth is the systems that deal exclusively with real-time data like stock trading and dashboards, where you need millisecond freshness and cacheness would actually be harmful. On the other hand, there are 5 scenarios where CDN is the right call. The first is a global user base, users on multiple continents where latency varies widely. The second is when your application is heavy on static content like images, videos, CSS, and JavaScript. The third is a high rate volume where the same content is requested millions of times. Fourth is any media platform, for example YouTube, Instagram, Netflix. CDN is not just optional, it's actually mandatory. And the fifth is cost optimization at scale, because CDN egress is much more cheaper per GB than origin egress. Now for system design interviews, here's a guideline. You should be including a CDN in your architecture whenever the system serves static content into a global user base. If the interviewer specifies a single region system or a purely dynamic API, you can note that CDN is optional for that specific use case. Showing that you know when not to use the technology is just as valuable as knowing when to use it. Okay, now let us bring together everything that we have covered in section 8. We start with the fundamental problem CDN solves, which is the physics of distance. Light and fiber cables move at about 200k kilometers per second, and no amount of code optimization changes that. CDN solves this by serving content from edge servers near the users, reducing latency from 200 to 400 milliseconds down to 10 to 30 milliseconds. After that, we looked at the CDN architecture, the origin server where original content lives, and the edge servers that cache copies nearby. We covered the cache hits where the edge servers can content directly, and cache misses where the edge hasn't to go back to the origin. We covered the 2 models for getting content to the edge as well. Pull CDN fetches the content on demand on the first request and is the most common approach. Push CDN pre-uploads the content to edges before a user requests it and is used for specialized cases like firmware updates and launch assets. Then we went deep on the cache control headers. There should be a mechanism that tells the CDN how long and whether to cache different types of content. And then we talked about the invalidation, how you purge stale content when it changes, and why version URLs are the better approach because they avoid the invalidation problem entirely. After that, we looked at the CDN cost. Pricing is bandwidth based, and at scale, CDN delivery is 4 to 5 times cheaper per GB than origin egress. For example, Instagram scale, that difference is $42 million per month. And as we discussed, when a CDN is also necessary. So for example, small user bases, single region deployments, mostly dynamic content, internal applications, and real-time data systems are all cases where a CDN adds complexity without proportional benefits. So the key number, to carry into the interviews are So the edge server latency is of 10 to 30 milliseconds, target cache hit rate above 80%, purge propagation of 30 seconds to 10 minutes, CDN cost of $0.02 to $0.085 per GB, and Instagram level CDN egress of roughly 600 petabytes per month.